Hello. Check. Check. Good morning, everybody. Today is the last day of the conference, InPAC2025. This session will be chaired by Dr. Mangesh Borage, and it is my pleasure to introduce Dr. Mangesh Borage. He did his MTech Electrical Engineering from IIT BHU Varanasi, and then he did his PhD, as you can see in the slides. And he has received several awards. University Merit Certificate from Shivaji University, Kolhapur, India in 1993. Dr. Homi Bhabha Award at BRC, Mumbai, India in 1995. DAE Scientific and Technical Excellence Award for the year of 2012, and many other several DAE Group Achievement Awards. And he has more than 100 publications in journal and conference proceedings. It is my, let us welcome our session chair, Dr. Mangesh Borage, the dais. Thank you.
Thank you, Subrat Das. So as he just mentioned, we are into the final day of INPAC 2025. And this this session, technical session 9, we have in all 4 talks. The first talk is for the 30 minutes, and rest 3 talks are for 20 minutes. And general request for our speakers to please adhere to the times so that we can start with the proceedings and continue on schedule as we go towards the end of this program. So to start with, I invite Dr. KP Singh, Head Reactor Physics Design Division of Bhabha Atomic Research Center. And it's my pleasure to read a brief introduction. You can see that it's on the screen. He is PhD in specialized in accelerator-driven subcritical systems from HBNI. He is recipient of several DAE Group Achievement Awards with more than 100 publications and reports. He has vast experience in reactor physics design of research reactors and advanced reactors. With this brief introduction, may I request Dr. KP Singh to please proceed with his talk.
Thank you, Dr. Rajay, for kind words. Distinguished seniors and delegates of INPAC, good morning, everybody. My topic today, which I am going to deliberate upon, is accelerator-driven subcritical system for nuclear energy. This topic, in fact, used to be very, very popular during 1990s. Rush for ADS design, accelerator-driven system design, was so very high. It was because one Nobel laureate and particle physicist from CERN, and he was, in fact, former director CERN also. He introduced a very, very noble concept of accelerator-driven system. And it was so called as that fast energy amplifier. And another scientist, Dr. Bowman, who was also working with similar ideas. So based on these two pioneering scientists, that novel idea of accelerator-driven subcritical system came. But somehow, in fact, maybe because of sluggish growth in nuclear energy, or maybe the very, very complex design, complex engineering challenges in developing such system, that is accelerator-driven system. In fact, that not more good attention was given to such system. But now we are living in now nuclear renaissance. We can say that nuclear energy is now getting very, very high importance in change scenario. So in this change scenario where we are saying that we are living in the nuclear renaissance, this system again now getting importance. And I will, in fact, during the course of my presentation, I have in fact outlined my talk this way. First, I will give a brief about growing need of nuclear energy, why nuclear energy has become so important recently, and then the challenges, spent fuel and requirement for transmutation, and then the transmutation basics and accelerate ADS as a dedicated transmuters. Then I'll deliberate upon a principle of accelerator driven system, and R&D needs and international efforts. And then, in fact, I'll describe theoretical developments which has taken, theoretical as well as experimental studies which have taken place in the recent time at BARC, and then few of the preliminary design which are based on accelerator-driven subcritical system, and then I'll summarize my talk. So this is now quite known. Everything is obvious these days that growing need of nuclear energy. Why is it so? I'll just read. Transitioning towards low carbon energy sources is now essential to mitigate the impacts of greenhouse gases. And in fact, the power which we demand these days, which is very high and it is growing very fast also, but the requirement as the energy which you are going to use should be green, so that impact of carbon in the climate should be minimal. So there are many alternatives also which can produce green energy, that is called windmills, tidal, solar power and all. But these power, in fact, cannot fulfill the base load, because base load is a constant need of energy which is required. But these alternative sources like windmill, tidal power, they are intermittent source of energy. In fact, they don't give a power continuously. So the base load cannot be fulfilled by these sources. So nuclear energy is the only alternative which can fulfill the base load. Why? What are the benefits of nuclear energy? Because it is very, very high density energy. And the capacity factor of these nuclear plants is more than 90%. Whereas if you see the solar energy plants, they have an installed capacity of several gigawatt, but they run at only 40%. So actual power production is only 40% of installed capacity. And in case of nuclear energy, the capacity factor of 90%, more than, because we say that our PSWR operate 2 years continuously. VVR is operating 18 months continuously. After that, the fueling takes place. So in nutshell, the capacity factor is more than 90% and negligible carbon footprint. And now I'll just, why that it is so important, because our commitment to net zero carbon, India's commitment at COP26 is that reach non-fuel energy capacity of 500 gigawatt by 2030, 50% of the energy requirement from renewable sources, reduce total projected carbon emission by 1 billion tons till 2030, and by 2070, India will achieve a target of net zero carbon emission. And I'll just see what is the nuclear energy mission of Viksit Bharat, which was very clearly elaborated in budget 2025-26. The Union budget 2025-26 outlines a significant push towards nuclear energy as a part of India's long-term energy transition strategy. I'll just quote budget speech by Honorable Finance Minister. Development of at least 100 gigawatt of nuclear energy by 2047 is essential for energy transition efforts. For an active partnership with the private sector towards this goal, amendments to the Atomic Energy Act and CLND, Civil Liability for Nuclear Damage Act, will be taken up. So Government of India is very serious. In fact, all the governments around the world, they are very serious for nuclear energy. So now what is the present status of our nuclear energy in our country? There are 24 reactors are operating. In fact, there is an additional 700 megawatt electrical, which is now RAP7. Suppose if you add that power also, so around 8,800 of megawatt electricity is being generated as of January 2025. And there are several types of reactor types, BWR, PWR, PSWR. So all combined together, we are generating 8,800 megawatt of electrical. But our target is by 2047 is 100 gigawatt electrical. That is in fact 12 times of the present operational capacity. So now coming to the challenges, what are basically assumed challenges? What are the challenges? That is implementing disposal of high level waste with growing share of nuclear power. That is the biggest challenge, because PSWR, PWR, in fact, a lot of spent fuel or storage in SFSP, they have to be reprocessed if you are having a closed cycle. So it is a challenging thing. And next is continuing to assure the highest level of safe operation of plant, which necessitates the need for passive safety and highly reliable reactor safety feature, because it is every day that nuclear regulators are stressing that nuclear safety should be a prime importance. And then next is achieving consensus on effects of small doses of radiation, because public perception is very much against the nuclear power because of high harmful effect of radiation. But that is not the correct case, because all the principle of doses are harmful effect of radiation based on LNT model, that is linear, not threshold, but which is a flawed principle. Now we have to convince the people that small doses of radiation is not harmful as envisaged by our regulators these days. So, but you have to build the consensus among the public. And now another last thing is the proliferation concern. That is a known usual that if high radioactive material or fissile material goes to rogue hands or rogue states is a problem. So this is the proliferation concern. So now coming to the management of spent fuel, look at this slide. If you take the one reactor which is 100 megawatt electrical LWR, every year with this operation, if you consider around 45 gigawatt days of per ton of discharge burn up. So every year we are discharging 25 tons of spent fuel, which is having actinide oxide and fission products. And whereas the heavy metal content of this discharge fuel is 21 ton, 1 ton is a fission product. And that fission product, there are fission products which are having around 30 years of half-life. Their concentration is very high, but half-life is around 30 years. So they can be managed even 100 years and all, 200 years, their impact will be minimal. But the fission product, if you say technetium 99, zirconium 93, and cesium 135, they are having very, very long half-life, that is of million years. So their impact will be seen after even for a very, very long time. Now, the total actinide which was shown in the previous slide, that is 21 ton. If you close the cycle, means you separate uranium and plutonium used for fast reactors, or uranium which is left in PWR you use for PSWR or for any purposes, then still what is left is neptunium 10 kg, americium 6 kg, and curium. These are in fact minor actinides which have to be handled. Even if you close the cycle, these are very long-lived minor actinides. Now, with the targeted 100 gigawatt watt of electrical nuclear energy installation by 2047, this amount will be in fact 12 times per year production. So this is a very highly ambitious target of nuclear energy, which will generate a lot of spent fuel and actinides. So how to deal with this actinide? India has been dealing with very, very safe. What is our management policy in India? Safe management of radioactive waste have been accorded high priority right from the inception of our nuclear power program. The closed fuel cycle, which is very, very noble concept, significantly reduces the decay heat load in the waste, reduces waste volume, and mitigate radiotoxicity. India's closed fuel cycle option is based on recycling of plutonium in fast reactor, and then again recovering plutonium from fast reactor using the same fuel to be used in a new fast reactor. And another, that we are generating wealth from waste, which I have said around 30 years of half-life, like cesium 137, ruthenium 106. Recently, these have fission products which are used for societal or cancer treatment application. These have been retrieved successfully. So fission products are now still being used in India for societal purposes. But still, we need a deep geological isolation even if with a closed fuel cycle also, because you have to deal with minor actinides which are having very long half-life. So what is an option? We have to reduce the burden of our deep geological facility. How to do it? So one concept is that transmutation of minor actinides is an effective solution to reduce the long-term radiotoxicity of nuclear waste. How it is done? By successive capture of non-fissile minor actinides can transmute the fissile, fertile to fissile isotopes, which further fissions and produce a fission product and energy also. But it is known that maximum transmutation or viable transmutation, effective transmutation for a fixed power, reactor power, is obtained only when whole fuel is made of minor actinides, because large quantity of this type of material should be kept in neutron flux to get effective transmutation. So you have to have a dedicated transmuter which will have only minor actinides or very, very low content of uranium or plutonium. Look at this graph. If you see that, if you plot that, what is the probability of fission to absorption for these minor actinides, it increases as you increase the neutron energy, it increases exponentially. So what does it mean? That we need high neutron energy to effectively transmute these minor actinides. The efficiency of transmutation depend on neutron energy spectrum of a reactor. Another, isotopes are more likely to fission than capture, which in fact by capture it will take again higher actinide. So isotopes are more likely to fission than capture for high neutron energy. And that means that what is the conclusion? That we should have a fast reactor to transmute effectively these minor actinides as compared to thermal reactor. But what are the challenges using transuranic as a nuclear reactor fuel? We know, everyone of DAE, in fact, they know that this reactor control is very much dependent on delayed neutron fraction. Delayed neutrons, in fact, controls the reactor. And if you look at this chart, the delayed neutron fraction for uranium or thorium are very high. But if see the delayed neutron fraction for minor actinide, it is very less. So if you put this material as a fuel in the reactor, the control becomes very, very challenging. Now, another factor is Doppler constant, which in fact makes the reactor stable. That is feedback. If you increase that, or power of the reactor increases, the temperature of fuel also increases. So it gives a negative impact so that you do not go runaway of situation of power. So that is a feedback. Now, if you see that normally in a fast reactor, 80% is uranium, plutonium 20 or 75-25, that ratio, the Doppler constant is -810. But if you mix, the time you mix is americium, it reduces to -20. So even apart from delayed neutron fraction, which is not very good in this type of fuel, the Doppler constant also reduces. So intrinsic safety is largely degraded. Difficult to control a reactor designed with minor actinide as a fuel. Cannot put minor actinide in large quantity in conventional critical reactors. So for this reason, ADS has been proposed for ADSS, accelerator driven subcritical system, has been proposed for effective transmutation of minor actinides. Now, another advantage of ADSS is in fact effective utilization of large thorium reserves in country. See, there is a growing interest in the thorium as a nuclear fuel, and incorporating accelerators into a fuel cycle. There is huge demand because uranium resources are limited as compared to thorium, and thorium uranium cycle produces a very, very small quantity of minor actinides, and thorium uranium fuel is also considered proliferation resistant. So now there is a concept that deploying thorium energy, we have three approaches. First is a thorium fuel in the solid form, as in conventional critical reactor, you can put in PSWR or PWR also, even fast reactor, conventional critical reactor in the form of solid rods or cluster. And thorium, which is now getting most promising attention, which is molten salt reactor. Thorium is a very, very benign fuel for a molten salt reactor. And the next is, which we are going to talk about, that accelerator-driven subcritical reactor. So now coming to the what is accelerator-driven, principle of accelerator-driven system. In fact, we have a target which is now produces lot of neutrons by spallation reaction with the help of proton having very high energy of 1 GeV energy. And these neutrons, in fact, now interact with the subcritical core, and then number of neutrons get multiplied and produces fission energy and lot of neutrons also. So we have major subsystem of ADS is high proton accelerator, spallation target, and then the subcritical core, which we are going to talk about. In fact, we will be concentrating on this fast neutron. Whether the reactor can be a fast reactor or thermal reactor or a combination of both. So what are the advantages of accelerator-driven system? As I have said, this reactor remain subcritical. So enhanced safety means there is no concern of prompt criticality, and thorium utilization, effective transmutation of minor actinide, and non-self-sustained chain reaction. That is, in fact, reactor remains subcritical whether it is operating or shut down. The state of a reactor always is a subcritical, and it is driven by an accelerator. So convenient, it is very convenient. An accelerator is the control mechanism. Normally in a critical reactor, you require control rod and shut-off rod. Their reliability is questioned, quality control has to be there. So, but in this case, we don't have a control rod. Accelerator itself is a control. If you switch off the accelerator, the power will go down. And then neutron economy of such type reactor is better because you don't have a control rod. Control rod eats neutron. Here there is no, so neutron can be used for breeding purposes. So, and this type of reactor accept any fuel, minor actinide, higher plutonium content. And in such type of reactor, the importance of delayed neutrons, void reactivity, and temperature coefficients, they are not of very concern because reactor is always maintained in a critical state. Even if their reactivity swings, so reactor remains critical, subcritical. So there is an illustration of one how the energy is amplified. Suppose you have 1 GeV of proton energy and our reactor subcriticality is K.98. So spallation neutron which will be produced with 1 GeV of proton with one lead or lead bismuth target is around 25 neutrons per proton. And if you consider the thermal efficiency, that is because you are producing thermal fission power, you have to change it to electrical, and then electrical energy has to be fed to accelerator. So efficiency, there are two efficiencies, one thermal to electrical and then accelerator efficiency. If you take account of all these things and take this K.98, we get a final energy gain of 12. Another factor is their source importance, means normally in ADS sources are kept at the center, and this formulation is based on point. If you do a spatial calculation, three-dimensional calculation, then another factor comes source importance if you are putting, and that is more than 1. So, but I have considered here source importance 1 for just to illustrate it. So you will get a gain of 12 times of nuclear energy.
Dr. Singh, 5
Yes.
minutes, please.
5 minutes time. Okay. So if you take 1 milliampere of current, then and take vary or K effective. So and with various proton energy, that energy gain is or reactor power gain is this way. So now how thorium can be utilized? So extra neutrons are there, that I have already told, and because of parasitic absorption is control rod is minimal, so we get. Now there are two types of reactor we can think. One is a thermal ADS or a fast ADS, but both should be molten salt reactor, which we are considering. So, but what are the challenges for accelerator-driven system? We have to have very, very high power, high current of the order. For any industrial application, we need very high power, and spallation target development and reactivity monitoring. Reactor physics is concerned because reactor remains subcritical. To find out how subcritical it is, that is 0.98, to measure it is very challenging, because in a critical reactor, you make the reactor critical by making it supercritical. So you know the state, but this reactor will remain subcritical. So it is difficult to get the reactivity monitoring and devising the method for reactivity monitoring. So the physics is different because in a normal critical reactor, we have a vessel function, sinusoidal, cosine function, but here the power distribution will be centered around the reactor because source is kept there. So the distribution is highly asymmetric here. So normal reactor calculation methods are not cannot be used in such type of reactor analysis. So you have to develop new reactor physics for these systems. So what are the world scenario? Many countries have done many experiments across the world, and India has also conducted a lot of experiment, very small power experiment in Brahma subcritical facility, that is a natural uranium facility, polythene moderator, and DT neutron source generator. We did a lot of experiment to find out what is the subcriticality of reactor, indirect measurement. And there are various experimental demo ADSs around the world. I will just, this is the Brahma facility. We did a lot of experiment, measurement of source multiplication, neutron flux profile. And then we did some study for our benchmarking code, which we have developed for ADS analysis. So thorium utilization also, we carried out a lot of theoretical studies to how thorium can be utilized even once through cycle or multi-processing cycle. So and this is another basic novel concept because accelerator requirement for ADS is very high, 10 milliampere current or 10 megawatt. So suppose we have a one-way coupled, means the center of the reactor where the target is kept is a fast system. So the spallation target which is multiplied by this fast system, and there is a separation and there is an absorber lining, and this outer system is a thermal reactor. So without getting higher K effective, because K effective cannot be more than 0.98 because it is a subcritical reactor. Without getting K effective more than 0.98, we are able to, in fact, multiply the source by 5 times, hence 5-fold lesser requirement of accelerator current for a same power. And this is a molten salt reactor. We, in fact, without adding any fissile material, we can start the cycle with thorium itself. So if you have a 12 milliampere of current and 8 MeV of proton energy, you can start with thorium only, and in course of time of 4-5 years, you can get 400-500 megawatt of power without any fissile material. But of course, current requirement is 12 milliampere and energy requirement 8 MeV. So this is the conceptual design which we have been worked out in BERC. It is 100,000 megawatt thermal reactor, where that K effective is a 1000 megawatt thermal, but it is a fast reactor, lead cooled, and criticality is chosen as 0.95. So in this reactor, the doubling time means uranium 233 gets doubled in 24. Sorry, month it should not be there. Doubling time is 24 years, and around 115 kg of uranium 233 gets generated every year. Apart from, maintaining the reactor critical. Initial feed, uranium 233 feed is 1.9 ton, and the reactor remains critical, and every year more than that what is consumed, 115 kg of uranium 233 is a breeder reactor. Another design which we have worked is a, this is a basic reactor which is being worked in BRC that will be in fact installed at Vizag. So it is a basically MSR demo ADS, that is molten salt reactor. It's a demonstration ADS. This is a molten salt reactor which you are using a fluoride salt, uranium or plutonium based fluoride salt, and fuel salt loading it 1.6 tons. And then what is simple model based on MSRE consisting of 231 channels. Fuel channels are rectangular in shape, circular hole at the center. Molten fuel coolant mixture flows through these channels, and graphite blocks help in neutron moderation. What we have simulated that in the plenum region that salt remains for some time. We have not considered any real-time fission product separation. So this reactor will run for 200 full power days at 5 megawatt, and with a in fact tuning of 200 microampere of current, and within 200 to 300 microampere of current, and energy of considered is around 600 MeV of proton energy. So many computer cores we are challenging to analyze these reactors we have developed, that is MAC-1 Monte Carlo based Bernoulli code, PAT-MOC which is a recent development, and deterministic as well as stochastic codes have been developed because these reactors are very highly heterogeneous because you are putting accelerator target in the center, so and core is outside. So this very heterogeneous core demands a different kind of code. And obviously, FLUCA is also being used to get neutron spectrum from spallation target. So to summarize it, accelerator-driven subcritical system offers an advantage option for the transmutation of nuclear waste. It will be very important to support growth of nuclear energy. And molten salt ADS has a superior breeding characteristics, hence suitable for thorium utilization. It can be said, it can aid the sustainability of our nuclear power program. But the one is challenging conclusion. ADS employs high intensity proton linear accelerator to produce spallation neutrons for a subcritical reactor. And for any high power application or any industrial application, beam current requirement is of 10 milliampere current. So rigorous theoretical and experimental studies have been carried out in BARC. Many codes have been developed for analyzing the physics of accelerator-driven system. Many publications based on this in our division or in BARC have happened. Thank you.
Thank you, Dr. Singh, for bringing out the relevance of ADS systems, particularly in the context of recent commitments. The talk is open for a few questions, 1 or 2 questions. Yes, please. You have a question?
Major challenge is type of reactor. One is that your target, another is window actually, which separates the reactor and high temperature reactor side to the vacuum side of this thing. So what is the present situation? Because I read that China and few countries are going rigorously in this direction. These are the major engineering.
Yeah. In fact, we have a separate target development group in BRC. They are working on window or windowless targets. Lot of development. In fact, many of people are around here also. They can give the details. One, Pramod, you can speak about that. Very dedicated development group. They are working for the targets.
Yes, so ADS target group is working on that development, and one of the cyclotron beamline also is being utilized for the initial experiments, 30 MeV proton beam, and later on, as with MAHIPA and HAHIPA comes, the same design capabilities can be extended and experimentally validated.
So we are working very seriously on that. This target is very challenging because it has to sustain very high energy density and all. So there is a separate group continuously for the last, I think, 20 years on that.
So since I have a mic, so I will also take opportunity to ask a question. Thank you,
Yes.
sir, for a very good talk. So just I want to ask, considering our ADS is still at least 10 to 15 years away, in Indian nuclear energy scenario, how are we targeting the subcritical cores? Whether in the initial stage, we would need pure burners or transmutation strategy only, or the energy amplification for power purpose when we are meeting the requirements with the nuclear reactors also?
Very good question. Yes, we have a different, in fact, stages of our program in ADS development. First, obviously, we will be doing experiment, because experiment which we have done in Brahma facility, that reactor was very highly subcritical, 100 milli subcriticality, which is not the case in actual reactor. Actual reactor will have 20 milli subcriticality or 50 milli subcriticality. But the reactor where we did an experiment, it was very highly subcritical, and overall it was a thermal system. So first is that we are going to increase the subcriticality, or decrease the subcriticality and do an experiment. We have well designed many experimental program that will be carried out while developing this 5 megawatt that thermal MSR. We will do first with zero power experiments, but right now we are concentrating only for power development, and that also molten salt reactor based on thermal reactor, because in a fast reactor, to make the reactor subcritical of 0.98 or 0.95, we require very large quantity of fissile material itself. So in fast reactor, which requires 5 times more fissile material as compared to thermal reactor, so we are concentrating, which is molten salt reactor. It is a graphite moderated a molten salt reactor. 5 megawatt is ultimate power. In fact, with 200 microampere, it can achieve 5 megawatt. But as the proton energy of the order of 200 MeV is getting developed in the second stage from 20 MeV LiPA to 200 MeV, we will be able to generate sufficient power to do lot of experiment and spallation experiment also, because 200 MeV is there for spallation. So there are significant many stages to achieve a breeding. 5 megawatt power reactor will not have a breeding because it will be a small reactor, and it will not have a breeding, but still it will have many characteristics of accelerator, many characteristics of target, as well as a reactor. So this is the, in fact, we have to go gradually in the steps.
Okay,
And in course of time, if that proton energy comes to 800 MeV or 1 GB and current, then only you can have industrial scale application for a power or even in transmutation. Well,
Yes, sir.
I mean,
Thank you,
effective
sir.
transmutation.
Yes, sir. Thank you, sir. I think younger generation has a lot to contribute to the
Yes.
programs.
Thank you. Let us thank the speaker once again for this lucid and very informative talk. And on behalf of the organizers, it's my pleasure to offer you a memento. The next talk is on advanced manufacturing techniques for accelerator components by Shri Abhay Kumar. I request Abhay Kumarji to. Okay. So we'll take up the next talk. That the talk is on IRFL operations for high average power and its first user experiments. Many of you may know that the IRFL facility at RRCAT is now a user facility. So I invite Shri Bhaskar Biswas to deliver the talk, and Dr. Bhaskar Biswas is basically a physicist by training, and his areas of research work are free electron lasers and magnet designs, numerous publications, and group achievement awards to his credit. Bhaskar Biswas, please finish your time presentation in 15 minutes so that we can have 5 minutes of question and answers. Thank you.
Good morning, all of you. This is a theme talk, but it will try to cover the status of IRFL since last reported in the previous InPAC in 2 years back. So I'll straight away proceed with the talk without going through the scheme of the talk. So what happened? Something wrong? I'm sorry. F5 पहले दबाओ. Yes. Okay. So sorry for the glitch. So you see this slide is being missed time again. But anyway, I will skip that slide. Everybody knows how the basic field works. So it's jumping to the third slide. So basically what I would say is that in an undulator, if a single electron is passed through an undulator, and this is the kind of spectrum you get, if a bunch of electrons pass through an undulator, you get n times the flux what you get from one electron. But if all those electrons are somehow longitudinally bunched in a space which is smaller than the gap between the lambda, then there is a coherent emission as well as stimulated emission, and you get n square theoretically if all these electrons in a Dirac delta kind of thing. But what we get practically is something between this and this. So this is a typical simulation where electrons are sent through an undulator in an optical cavity of a electron laser, and So you get bunching, and these parts add coherently to the lasing, and you get significant growth in lasing. Even if the number of electrons is 10 to the power 17 and this factor is 1.3, you will get a growth of 10 to the power 8, which is huge growth. So this is a typical picture. So this is how the FEL power starts from background noise and it grows and saturates. This is the spectrum initially, which is a short noise, lot of frequencies, but then after the saturation, you get only one frequency. So two things happen simultaneously. One is the growth, exponential growth in power of an FEL. Secondly, there is a growth in coherence of the FEL. And note that whenever the FEL saturates, there is still some background short noise left in the FEL. That is the basic nature of FEL. It's not like a quantum laser, which is very stable. So this is the picture of the FEL. This is the gun, then the injector, then the dipoles, and there's the optical cavity. And this is another picture from the downstream side. So here the output cavity mirror, and this is the input cavity mirror. This is the undulator. So this is a brief sketch of our FEL, just for the sake of those who are attending first time. So we have a gun, which is a pulse gun, which gives you 1.5 ampere current in 1 nanosecond, and then we have a bunching section accelerating it to 4 MeV, a Linac section which accelerates depending upon how much power you feed, 15 to 25 MeV. Then we have matching magnets where we select the energy and the energy spread and let it go through the undulator. The purpose is that you should have a good peak current of the charge that you put through the undulator. Otherwise, the lasing will take a lot of time, and then we will not be able to deliver light to the user within the available macro pulse of the FEL. So I'll just go to what we did in the last 2 years. So we had lased much before in 2021 and then progressed in power in up to 23. But some power transfer to the user, which is about 60 meters away, was very less. So we upgraded the whole transport line after doing some simulations. So I'll not go through the details. So what I mean to say is that time was necessary to do this change and learn how to transport this FEL up to the user room. So this is the extended tunability of the FEL project. We wrote a project that we will deliver 12.5 to 50 microns from this FEL, and this year we have been able to go even below 12 microns and up to cross 50 microns also. So I just write extended because we have actually covered the whole range of FEL. So this has been covered using, you see, 1, 2, 3 and 4 kind of beam energies. So and this has been achieved using an undulator chamber, which was a spare chamber given to us from the INDORE project, because we were late on our commissioning stage. So we have now ready with our new undulator chamber, which has larger vertical aperture, and if we replace this in future, we will go much more than 52 microns. We are quite sure about that, and the power will also increase because the longer wavelength needs more diffraction size on the mirror. This is a report on a similar graph was reported 2 years back. So I'll just say that what is different. Last year was the official closing of our project also. So we had to demonstrate the final targets. So one of the targets was to achieve 100 milliwatts, highest power. So what we achieved here is that we operated the electron gun at the second harmonic. It can operate at higher harmonics also, and we adjusted the power and phases of all the injectors. It took us some time, and then we demonstrated the power at 1 Hertz, 2 Hertz, 3 Hertz and 4 Hertz, where occasionally we crossed 85 milliwatts. So it shows that if we can go up to 10 Hertz repetition rate of RF, which was our plan, then we will definitely go more than 100 milliwatts or maybe 150 milliwatts. So, but what the user needs is typically 1 milliwatt at any wavelength on his table to do the basic experiments of material science or spectroscopy. This is the latest run few days back, where we have actually tuned the FEL to its best ever format, where at 2 hertz itself we are getting 40 milliwatts. So typically this is the best performance, but in any case we always get 25 to 30 milliwatts on any given day. This is the FEL laser profile measured using a camera in the tunnel. These are the profiles measured in the user lab. So this is where we refocus the FEL beam and send it to the next user lab. This is a kind of a near normal incidence reflective beam reducer. It's little sounds little complicated, but it's basically a reverse of a beam expander, which we know using lenses, but this is using mirrors. So you have to keep the angles little low. In future, we will go for customized hyperbolic mirrors to improve the efficiency, but this is the present status. So now we are coming to the status of the FEL. So the IR user facility has been developed with stations and ports for IR beam diagnostics. That is where we receive the FEL in the first room in the user building. We diagnose it and we give it to send it to the next room. So in that room itself, we have a port where we will do experiments for biology and chemistry. Then we will send it to the successive rooms where we can do couple it with an FTIR or standalone experiments. Then in the next room we can do Michelson interferometry. This has been developed by our own user group, because IR user facility is not done unless you tell the user what is the frequency, and you have to measure it with good resolution and good repeatability over the years. And recently the facility was inaugurated for outside RRCAT users in December by the visiting Secretary to DA and Chairman AEC. First users were invited after some planning before the actual experiments from a terahertz laboratory in TIFR, Dr. Prabhu's lab, and Dr. Bansal from IIT Bombay, and his students from IIT Indore and some more places. So we operated the LINAC for 3 weeks continuously, at least 10 hours to 11 hours of beam time given to them every day. This is the current layout of the thing, user facility. So this is the first room where at 48 meter point from the tunnel output hole where the beam is received. So we do all those laser profile and power measurements. Then we can give the beam to the next room, and this small diagnostic again lambda measurement room, and lastly to the FEL pump and probe spectroscopy room. Now this is a arrow shows this setup where this is a FTIR, and this can be coupled in future to the FTIR, but before that we have already set up our own Michelson setup here. So we can do the lambda measurement, and the first users who visited us did their experiments here as well as on this port. So P3 and P4 were the 2 ports where they used the. In future, this will go to the next room where we will need to couple it with picosecond and in future femtosecond pump probe spectroscopy FEL. So we have to populate our user facility with more such advanced tools, for which we are going to write a project for the upgrade of user equipments for making this useful to user community, because they will need some advanced kind of facilities to use the FEL, which we are also gradually gearing up to. So this is just we had an NLS few days back, so lot of more details were given there. This is a interferogram, and this is the lambda measured in our Michelson setup. Some user experiments were briefly reported. This is a imaging, and we had a talk yesterday by Tapas that imaging becomes better when you have coherence. So this is a imaging done with a coherent FEL beam. So transmission mode and reflective mode, you have very sharp features, contrast. So this is done with 21 micron. We can even go for 12 micron in future. So that is the status of the FEL, and I'll just briefly touch the operational some share, because we are all accelerator community. We like to share with our working experience. So this is how the FEL works. The thing is that when the electron beam reaches the undulator, there are two things that are important. The cavity length has to be tuned, and the phase, the bunching of the electron has to be best, so that we get the maximum peak current. So here, for example, and here there will be difference of the peak current. So just we observe that sometimes
2 more minutes,
yes.
Dr. Biswas. Thank you.
I am finishing with that. So we have observed that if you play with the strength of these two quadrupoles of the DBA, sometimes you can make it more isochronous, less achromat, and still go away with it to get better lasing. So this is something we will work upon in future. So what FEL cares for is the peak current. So in a matched achromat, you have dispersion 0, but there is some parasitic debunching. But by playing with the quadruples, you can make it 0. So compensate the debunching. You will have some errors here. These can be handled with a pair of steerers again. So this is some interesting thing I just shared. And we have done in there was a poster on emittance measurement, and what we saw that when we have the best power on the FEL, we get almost equal emittances in both planes. So this is also a very recent result. And just to give you a feel, the cavity of the mirror to mirror distances have to be within this range, otherwise we will never get lasing. And it happens on several times that whenever we restart the FEL after some gap, we do not get any lasing. Imagine that the Indus is working with full 200 milliampere and you don't have light. It won't happen in Indus, but it happens here. We get the full beam transmission, but we get 0 FEL light. So that is because either this is wrong, this cavity length is wrong, or we are not having the peak current, properly bunched peak current. So this is the conclusion. The IRFL has been demonstrated tunability beyond the range. It has been running in-house mode for last 1 year and recently opened up for the outside users. And we have characterized, and a footfall of users has happened. And experience gained from every user set prepares it better for the next user experiment. Thank you.
Thank you, Dr. Biswas, for bringing out the present status as well as the future plans for the facility.
Thank you.
The talk is open for a few questions. May I invite few questions from the audience? There's one question.
Hello, sir. Thank you for the nice talk. So I wanted to ask that what is the beam current, what you are talking about? Like it's not lasing when what is the limit of this beam current? Like
The limit is depends upon the wavelength. Shorter wavelength needs like 50 ampere, longer wavelengths need 30 ampere. But if you have the more the merrier. The 30 ampere will give you lasing in say 3 microseconds, and 70 ampere will give you lasing in 1.8 microseconds. So you have more power time available for the user.
so
with
30
higher
ampere
peak current.
means you are saying that this is the peak current. Like what is the pulse width of this?
10 picosecond.
Huh?
10 picosecond.
10 picosecond. So that is the peak current you are talking about.
Yes.
So yeah, okay. Thank you.
In case there are no further questions, let us thank Dr. Biswas once again. Thank you. And Dr. Biswas, I have a presentation for you on behalf of the organizers. इस सत्र के अगले वक्ता श्री संजय चौकसे जी हैं। संजय चौकसी जी RRCAT में सुपर कंडक्टिंग कैविटीज डेवलपमेंट डिवीजन के हेड है, मैकेनिकल इंजीनियरिंग बाय ट्रेनिंग। उनका योगदान टेक्नोलॉजी डेवलपमेंट में तो है ही, बट इनका योगदान खास करके जन पहुंच या पब्लिक आउटरीच जिसको हम कहते हैं उसमें है, जो जिसकी वजह से उन्होंने काफी सारे बेस्ट पैवेलियन अवार्ड्स भी जीते हुए हैं, जितवाए हुए हैं।
इससे भी कर
और
इसे कर लो।
उनके पब्लिकेशंस खूब सारे हैं। दे आर नॉट लिमिटेड टू कॉन्फ्रेंस सिंपोजियम एज वेल एज लाइब्रेरी रिपोर्ट्स। संजय चौकसी जी।
धन्यवाद डॉक्टर मंगेश बोरगे। हाँ, पीपीटी। मैं जो है इस समय सुपर कंडक्टिंग कैविटी डेवलपमेंट डिवीजन का प्रमुख हूँ और कोशिश करूँगा कि अपना जो वक्त है वो थोड़ा कुछ हिंदी में बोलूँ और मतलब हिंदी और अंग्रेजी दोनों में रहेगा। इसमें मैं सुपर कंडक्टिंग कैविटी के बारे में एक्चुअली काफ़ी सारे ऑलरेडी टॉक हो चुके हैं, तो मैं ज़्यादातर जो इसमें नया डेवलपमेंट हो रहा है और हमारा RRCAT डिवीज़न और RRCAT इसमें इस दिशा में क्या कार्य कर रहा है उसके बारे में बताने का प्रयास करूंगा। तो मेरी जो वार्ता है उसकी रूपरेखा इस तरह रहेगी कि अभी DAE का जो रोड मैप है सुपर कंडक्टिंग केवी टेक्नोलॉजी में वो क्या है और भारत का इसमें क्या इन्वॉल्वमेंट है, जो कि PIP2 प्रोजेक्ट फर्मी लैब, जो कि आप लोग कुछ दिनों से इसके बारे में जानकारी भी ले रहे थे और हमारे यहाँ से फर्मी लैब से 2 लोग आए भी थे। और 5 सेल 650 मेगाहर्ट्ज केवीटी की जो ज़रूरत है वो क्या है, और इस दिशा में जो कि हम लोगों ने प्रोसेसिंग और ट्यूनिंग पे काम किया है और आगे की जो भविष्य की टेक्नोलॉजी है इस बारे में वो क्या रहेगा हमारा रूपरेखा। तो ये यदि हम देखें, कल लालजी ने एक्चुअली अपने टॉक में बताया था कि आगे जो है IFSR प्रोजेक्ट, इसमें हम लोग किस तरीके से ये तो हम लोग का जो इसमें खास चीज़ है वो है एलिप्टिकल केवीटी 0.92 हाई बीटा 650 मेगाहर्ट्ज की और लो बीटा। तो इसमें आप देखेंगे कि ऑलरेडी हम लोगों ने इसमें काफ़ी कुछ काम कर लिया है और इसमें हमको बहुत अच्छी सफलता भी मिली है। तो ये जो PIP2 प्रोजेक्ट है फर्मी लैब का, जिसमें हम देखते हैं कि आपको भारत का झंडा प्राय सभी जगह दिख रहा है और इसमें हर दिशा में अच्छी प्रोग्रेस है और स्पेशली जो हमारा हाई बीटा केवीटी 652 उसको हम लोगों ने ऑलरेडी 3 केवीटी 502, 504 और 508 की वो ऑलरेडी हम फर्मी लैब भेज चुके हैं और अभी क्रायो मॉड्यूल पे भी ये हुआ। कल आपको लालजी ने इसमें काफ़ी अच्छे से बताया। तो यदि हम देखें, क्योंकि सुपर कंडक्टिंग केवीटी जो लोग के लिए थोड़ा नया है ये, कि मतलब 2 तरीके से हम बनाते हैं केवीटी स्ट्रक्चर, एक तो नॉर्मल कंडक्टिंग, एक सुपर कंडक्टिंग। और इसमें सुपर कंडक्टिंग में के बहुत ज़्यादा कई फ़ायदे हैं नॉर्मल कंडक्टिंग से और इसी कारण से ये टेक्नोलॉजी भविष्य की टेक्नोलॉजी मानी जाती है। तो आपको पता होगा LHC CERN वगैरह में बहुत ज़्यादा सुपर कंडक्टिंग टेक्नोलॉजी का उपयोग किया गया है। तो मैं क्योंकि समय की कमी रहेगी, मैं केवल आपको 650 मेगाहर्ट्ज सुपर कंडक्टिंग केवीटी के बारे में ज़्यादा फोकस करूंगा और इसमें हम देखें तो करीब 33 कंपोनेंट हैं और इलेक्ट्रॉनिक वेल्डिंग जो इसमें बहुत ज़रूरी चीज़ है, जो कि एक्चुअली धातु जोड़ है, वो करीब करीब हमारी 25 मीटर है और ऐसे 36 जॉइंट्स हैं करीब। ये टेक्निकल रिक्वायरमेंट है कि हमको जो इसका जो मटेरियल है वो काफ़ी शुद्ध, ज़्यादा RRR नाइबियम की आवश्यकता होती है, जिसमें कि इम्प्योरिटीज जो हैं वो दोष कम होने चाहिए। और क्योंकि नाइबियम जो है एक तरह का एक रिएक्टिव मटेरियल है और इसका मेल्टिंग पॉइंट भी अधिक है, लेकिन ये जब लो टेम्परेचर पे मतलब 2K या 4K पे जब हम इसको ऑपरेट करते हैं, उस समय के जो चैलेंज हैं वही सुपर कंडक्टिंग केवीटी बनाने के सबसे बड़े चैलेंज हैं। तो यदि RRCAT में देखें तो इस दिशा में काफ़ी वर्षों से, करीब 1 दशक से अधिक से कार्य हो रहा है, जैसा कि कल लाड़ जी ने भी बताया था। और अलग-अलग आवृत्ति की या फ्रीक्वेंसी की कैविटीज़ बनाई गई हैं, जो सिंगल सेल, 5 सेल या 9 सेल कैविटी भी हैं। और 650 मेगाहर्ट्ज़ की ऑलरेडी कई कैविटी बना चुके हैं। 3 कैविटी आप देख रहे हैं फ़ोटो में, जो कि हम अमेरिका भेज चुके हैं, यूएसए। यदि हम इसका निर्माण देखें तो इसको एक शीट होती है करीब 4 मिलीमीटर थिकनेस की, जिसको कि एक शेप में लाना पड़ता है फॉर्मिंग करके। और उसके बाद इसकी जो चैलेंज है वो इसकी मशीनिंग है। और मशीनिंग के बाद आगे की प्रोसेस भी है, जैसे कि इसको इलेक्ट्रॉन बीम वेल्डिंग से जोड़ना, और इसके बाद केमिकल क्लीन और प्रोसेसिंग। तो हम पिछले दशक में देखें तो ये अलग-अलग धातु, मतलब एल्युमिनियम एलॉय हो या एल्युमिनियम, कॉपर और फिर नाइबियम, इन सभी पे प्रोटोटाइप और फाइनल स्ट्रक्चर बने हुए हैं। ये आपको एक जस्ट फोटो ग्लिम्स मैंने दिखाने का प्रयास किया है। और इसके जो कई वर्षों के अनुभव पे जो इंफ्रास्ट्रक्चर है, जो कि हिंदुस्तान में देखा जाए तो एक ही जगह पर यदि केविटी, यदि मटेरियल केवल नहीं बना सकते, इसके ऊपर का सारा मशीनिंग हो और वेल्डिंग हो, केमिकल क्लीनिंग हो, प्रोसेसिंग हो और टेस्टिंग हो, आरएफ, वीटीएस और एचटीएस, ये सभी की सभी जो बुनियादी सुविधाएं हैं, ये आरआरकैट के पास मौजूद है, जो कि काफ़ी बड़ी टीम के साथ अथक प्रयासों से ये बहुत सालों में तैयार हुई है। ये वीटीएस और एचटीएस है टेस्ट के लिए, मीन्स बेयर केविटी और फिर ड्रेस केविटी के बाद। इसके बारे में भी कल लाड़ जी ने बताने का प्रयास किया था। ये इनकी टेस्टिंग है, और ये वो चित्र है जो कि वहाँ के न्यूज़लेटर में भी आया था कि हम लोगों ने 3 केविटियाँ बनाने के बाद स्ट्रक्चर जो है अमेरिका को सौंपा है सक्सेसफुली। ये कंट्रोल एटमॉस्फेयर ग्लो बॉक्स में इसकी वेल्डिंग किया जाता है, टिग वेल्डिंग। और ईवी वेल्डिंग के लिए एक डेडिकेटेड इलेक्ट्रॉन बीम वेल्डिंग फैसिलिटी भी हमारे पास है। ये इसकी टेस्टिंग परफॉर्मेंस है कि क्यू और इलेक्ट्रिकल फील्ड का कर्व कैसा होता है। और हम हमेशा प्रयास होता है कि जो आइडियल कर्व है उसके पास ही हम केविटी बनाएं, और उसके लिए जितने भी प्रयास किए हैं वो काफ़ी संतोषजनक है। और ये बताने में अच्छा है कि इंटरनेशनल लेवल पे हम लोग जाने का प्रयास कर रहे हैं काफ़ी हद तक, क्योंकि कुछ देशों ने अपनी इंडस्ट्रीज़ को काफ़ी डेवलप किया है और उन्होंने बहुत बड़ी मात्रा में कई बड़े एक्सएफईएल और इस तरह के प्रोजेक्टों में इस तरह की केविटी, जैसे कि यूरोपियन एक्सएफईएल और अभी शाइन प्रोजेक्ट भी आ रहा है चाइना में, इनमें इन्होंने काफ़ी केविटी सप्लाई की है। तो इसके अलावा हम लोग यदि फर्मी लैब प्रोजेक्ट में देखें तो ये एसएसआर 2 केविटिकल, आपको लाड़ जी ने अपने टॉक में बताया था कि क्या क्या कंपोनेंट्स हैं उसमें। सीडीएम को ईवी वेल्डिंग की आवश्यकता थी, तो वो काम हम लोग कर रहे हैं और अभी इसमें सफलता अच्छी मिली है। थोड़ी सी फ्रीक्वेंसी ट्यूनिंग करने के बाद और फीड फ्लैटनेस लाने के बाद ये हम लोग केविटी उनको सौंप देंगे। और हमारा प्रयास है कि अप्रैल के आखिरी में ये केविटी एसएसआर 2 बेयर केविटी भी फर्मी लैब कोलैबोरेशन में शामिल हो जाएगी। इस पे जो भी प्रयास किए गए हैं आरआरकैट में, इसमें एक्चुअली 3 भाग होते हैं। एक तो दोनों साइड के एंड शेल्स कहलाते हैं। इसके अलावा आप देखेंगे स्पोक असेंबली है और बीच में शेल असेंबली। इन सभी को जोड़ के और इनकी फिर आरएफ टेस्टिंग की गई है आरएफ टीम के द्वारा। और हमेशा एक प्रयास होता है कि जब हमको इस आरएनडी से प्रोडक्शन फेस में जाना है तो हमको कुछ इंडस्ट्रीज को डेवलप करना पड़ेगी, और इसी प्रयास में ये काम असाको, लक्ष्मी इंडस्ट्रीज या ब्रह्मोस के साथ करने का प्रयास किया है। और हाल में ही अभी असाको का कल आप लोगों ने यहाँ पे देखा होगा एग्जीबिशन भी है, और ये एक हमारे एक ऑर्डर को अभी आगे क्रियान्वित करेंगे। तो इस तरह की केविटी ये कंपनियां बना चुकी हैं, और यदि सभी कुछ अच्छा रहा तो भविष्य में हम लोग ज़्यादा केविटीज बनवाएंगे इंडस्ट्रीज में। और आज के अभी जो हम देखें कि वर्तमान स्थिति क्या है इस दिशा में, तो एक केविटी हम लोग को अभी जल्दी देना है 505, ये एड्रेस हो गई है। और वीटीएस टेस्ट के बाद इसमें कुछ जो क्यू थोड़ा कम था उसको और आगे बढ़ाने का प्रयास किया जा रहा है। और ये जो चीज़ है जिसमें कि क्या है कि सभी देशों में इस तरह की सक्षम प्रौद्योगिकियों पर काम हो रहा है, जिसमें प्लाज्मा प्रोसेसिंग है, मैग्नेटिक फ्लक्स एक्सपेंशन है, और हम लोग अपनी तरफ से हाई ट्रिपल आर इंडिया में बनाने का प्रयास कर रहे हैं एनएफसी हैदराबाद के साथ, जैसा कल लाड जी ने बताया था। फिर NB3 SN फिल्म बेस्ड केवीटी, और इसमें जो प्लाज्मा प्रोसेसिंग है, जो कि कुछ गैसेस के द्वारा, नेट गैसेस के द्वारा मिला करके एक प्लाज्मा क्रिएट किया है, नियॉन, नोबल गैसेस नियॉन और आर्गन का, और इसमें काफ़ी सफलता मिली है। और डॉक्टर विकास जैन का इस पर अभी वार्ता है आज, तो आप लोग इसके और अधिक डिटेल आपको जानकारी इसमें मिलेगी। अब इसकी ये एक्चुअली जो मैग्नेटिक फील्ड है, जो कि अर्थ मैग्नेटिक फील्ड है, ये केवीटी एक्चुअली क्योंकि बहुत लो टेम्परेचर पे ऑपरेट करती है और इसमें अधिक ग्रेडियंट होता है, तो उसकी ऑपरेशनल एफिशिएंसी को बढ़ाने के लिए और क्वालिटी फैक्टर इंप्रूव करने के लिए उसको अर्थ मैग्नेटिक फील्ड से बचाना पड़ता है। तो इसके लिए हाई निकल बेस्ड एलॉय है, जो कि जिसकी केवीटी जिसका हम लोग ये बनाएंगे। और इस स्टडीज से हमें ये पता चला है कि हम लोग को शील्डिंग एक बनाने का ये चल रहा है काम, तो बहुत जल्दी प्रयास करेंगे। एक इंडस्ट्री को हम लोगों ने ये कार्य दिया हुआ है। ये जो है हाई ट्रिपल आर नेवियम मटेरियल, जो कि चेयरमैन साहब ने अपने आत्मचिंतन में इसका उल्लेख भी किया था, और इसमें आप देखेंगे कि राइट साइड में आपको 3 कर्व दिखेंगी और लेफ्ट साइड में 3 कर्व, बाएं और दाएं में। तो जो राइट साइड की जो कर्व हैं वो ये बता रहे हैं कि एक्चुअली कायदे में देखा जाए तो जब हम हर बार मेल्ट करते हैं इसको इलेक्ट्रॉन बीम मेल्टिंग प्रोसेस से करीब 200 किलोवाट पे, तो ये एनएफसी में ये कार्य चल रहा है, तो वो लोग रिएक्टर ग्रेड का नाइबियम लेके उसको फिर मेल्ट करके ये हर साइकिल में इम्प्रूव करने का प्रयास करते हैं। जैसे अपन गेहूं को पीसते हैं तो कई बार चक्की में बारीक नहीं होता, तो मांस से देखते हैं, फिर उसको दोबारा डाल देते हैं, उस तरह बारीक होता है। इसी तरीके से हम लोगों ने काफ़ी सारे सैंपल्स एनएफसी हैदराबाद से लाके और यहाँ पे उसको एक लैब सेटअप की गई है, जिससे इसका ट्रिपल आर मेजर करते हैं। और फर्मी लैब का एक हमारे पास सैंपल है, जिससे उसका हम लोग तुलना करते हैं, तुलनात्मक, कि हाँ ये जो है सही है। तो आप देखते हैं एक डिप आया है, तो उनके पास जो इलेक्ट्रॉन बीम वेल्डिंग मशीन है, जो कि BRC के उनको दी थी, अर्चना शर्मा मैडम भी यही हैं, जो कि इनका प्रयास था। और अभी वो एक थोड़ा सा वैक्यूम का लीक आने के कारण एक डिप आया था, लेकिन आप अगली मेल्टिंग में देखेंगे तो ये काम बहुत अच्छे से हो रहा है। और हाई ट्रिपल आर जो चाहिए है, मतलब एक कमर्शियल, उसके लिए वो लोग ऑलरेडी अचीव कर लिए हैं, लेकिन ये इनगॉट के रूप में अचीव किया है। इसके आगे इसको 4 mm के आसपास की जो शीट बनाना है, वो DRDL, क्योंकि एनएफसी हैदराबाद के पास फिलहाल इस तरह की फोर्जिंग और शीट रोलिंग फैसिलिटी नहीं है, जो कि बहुत अधिक शुद्धता पे काम करे। तो ये 2 ऑर्गेनाइजेशन के साथ मिलके बहुत जल्दी ही ये लोग शीट बना लेंगे, क्योंकि इन दो डिफेंस लैब में कुछ काम चल रहा है इनका, और हमको लगता है 1-2 महीने में हमको इस फॉर्म में यदि शीट मिली तो हम लोग इंडिजिनस मटेरियल से एक मतलब अपने देश की ही बनाई हुई स्वदेशी विकास से ये बनाने का प्रयास करेंगे। काफ़ी अच्छा एक्चुअली प्रयास है ये, और एनएफसी की काफ़ी अच्छी टीम इस कार्य में लगी हुई है। इसके अलावा जो कि भविष्य की रिक्वायरमेंट है, क्योंकि अभी क्या होता है कि सभी केविटीज़ को काफ़ी लो टेम्परेचर पे चलाना पड़ता है, जिसके लिए भारी क्रायोजेनिक्स की आवश्यकता होती है। तो कुछ वर्षों में, मतलब 1980 या 85 के बाद काफ़ी लोग इस पे काम कर रहे हैं कि क्यों ना केविटीज़ को, सुपर कंडक्टिंग केविटीज़ को थोड़ा अधिक टेम्परेचर पे चलाया जाए, जिससे कि हम काफ़ी ऊर्जा बचा पाएँ क्रायोजेनिक्स की, और टेबल टॉप क्रायो कूलर पे ही इसका काम करें। और आपको पता है कि या शायद पेपर भी है पोस्टर में, और टॉक भी है अबाउट इंडिजिनस डेवलपमेंट ऑफ क्रायो कूलर। और इस में हमारे यहाँ से मनीष बागरे हैं, जो कि अभी काम कर रहे हैं, और उनका पोस्टर भी इस डिटेल पे है, क्योंकि इसमें थिन फिल्म टेक्नोलॉजी और टीसी मेजर करना सबसे इम्पोर्टेंट है। और एक फ्लैट सैंपल पे हम लोगों को सफलता मिल गई है, और करीब 17.545 केल्विन टीसी मेजर भी हुआ है। और ये हम BRC में डॉक्टर राघवेंद्र तिवारी जी के ग्रुप के साथ इस कार्य को कर रहे हैं, क्योंकि थिन फिल्म टेक्नोलॉजी एंड टीसी मेजरमेंट।
चौकसी जी 3 मिनट।
हाँ, ये कई देशों में अभी जेफरसन लैब और के वगैरह में कुछ सफलता मिली है, और चाइना में भी। तो ये लोग करीब करीब 16-17 मेगावोल्ट पर मीटर तक NB3SN बेस्ड केवीटी क्रायो कूलर बेस्ड कर रहे हैं। और फायदा ये है कि इस तरह की केवीटी को हम लोग भविष्य में सुसाइडल एप्लीकेशंस के लिए उपयोग कर पाएंगे, क्योंकि अभी बहुत बड़ा एक प्रॉब्लम आता है कि कहीं भी आप सुपर कंडक्टिंग केवीटी का उपयोग करते हैं क्रायोस्टेट के साथ, तो आपको काफ़ी ज़्यादा क्रायोजेनिक्स की आवश्यकता होती है। इसके अलावा कल लाड जी ने ये बताया था कि इसका डिट्यूनिंग कंपनसेशन के लिए भी हमारे डिवीजन में कुछ काम चल रहा है रूम टेम्परेचर पे, और इसमें अच्छी सफलता मिली है। कुछ पोस्टर भी हैं इसमें, और गत वर्ष BRC में एक कॉन्फ्रेंस में इसके पेपर को बेस्ट पोस्टर अवार्ड भी मिला था। तो हम यदि नेक्स्ट जनरेशन मतलब आगे के त्वरक के लिए अगली प्रणाली के रूप में सुपर कंडक्टिंग केविटीज को देखें, तो हमारी आवश्यकता है कि ये एक पोर्टेबल टाइप होना चाहिए, जो कि अभी आत्म चिंतन में वर्टिकल 6 में इसका जिक्र भी हुआ था। तो एक तो NB3SN फिल्म बेस्ड और कंडक्शन पूल टाइप ऑफ स्ट्रक्चर, जो कि कल इसमें एक पोस्टर भी था हमारे यहाँ से। काफ़ी काम है और काफ़ी काम की आवश्यकता है यदि हमको विश्व स्तर पे इस टेक्नोलॉजी को ऊपर लेके आना है। तो अभी हम लोग का मतलब शुरुआती दौर में है, कुछ 2-3 साल का ही इसमें ज़्यादा कार्य हुआ है, और लेकिन आशा है कि भविष्य में अगली पीढ़ी इस पे काफ़ी जोरों से काम करेगी। तो यदि हम फीचर देखें, तो नाइबियम और नाइबियम की केवीटी की जो परफॉर्मेंस है उसको आगे काफ़ी इम्प्रूव करना है, ताकि उसमें जो किसी तरह के लॉसेस हों या क्वेंच फील्ड है, एक्सपेरिमेंट करना है ताकि उसकी परफॉर्मेंस को और अधिक बढ़ा पाएँ। दूसरा है कि इसमें नैनो इंजीनियरिंग और सरफेस लेयर, जैसे अभी जो हम लोग कर रहे हैं वो DC मैगाट्रॉन स्पटरिंग पे करा है हम लोगों ने, बट वेपर डिफ्यूजन बेस्ड NB3SN का भी काम करना बाकी है। और इसके अलावा मतलब क्योंकि सुपर कंडक्टिंग केवीटी सभी XFEL और आगे के 6GV सोर्सेज में, जैसे अभी चाइना में 6GV सिंक्रोट्रॉन का जो काम चल रहा है, उन्होंने अपने बूस्टर और मेन रिंग दोनों में सुपर कंडक्टिंग केवीटी ही लगाई है, ऐसा हम लोगों ने उनके पेपरों में पढ़ा है। तो इस दिशा में RRCAT को भी अपने आप को विश्व स्तर पर रखना पड़ेगा, जो कि आगे की ज़रूरत है। और नए SRF मटेरियल नाइबियम के अलावा इन पे भी काम हो रहा है, कई लोग कर रहे हैं, मतलब मल्टी लेयर डिपोजिशन के थ्रू। और ऐसी ज्योमेट्रीज और इस दिशा में काम हो रहा है कि हम लोग 70 मेगावोल्ट पर मीटर तक की ग्रेडियंट अचीव कर पाएँ। और मीडियम और हाई बीटा इसमें जो प्रयास हैं एक्चुअली वो काफ़ी अच्छी दिशा में है, और भी अधिक प्रयास की आवश्यकता है। मैं इसमें अपनी सुपर कंडक्टिंग केवीटी SCDD और SCCS, DMTD, PLDD, RF ग्रुप और फर्मी लैब का आभार व्यक्त करता हूँ इन्हीं लोगों के, क्योंकि ये एक पूरा सामूहिक प्रयास है, इस दिशा में विश्व स्तर का बहुत अच्छा काम है। तो इसी के बाद धन्यवाद।
धन्यवाद चौकसी जी। क्वेश्चंस प्लीज।
Good morning. I am TK Saha. I represent Arctic Welders Private Limited. I have, from your talk, I have come to know that you are almost self-sufficient to make full cavities, and that from machining, forming, and cleaning, and electron beam molding. So my question is that if we make an electron beam welding machine, so can you outsource the welding to us? Because we have already developed one machine, which I think we have welded a test coupon for you, and it is encouraging result. You told RRR cavities. So can you outsource the only electron beam welding to us if we make a bigger machine?
This presently actually the problem is for 650 megahertz 5 cell cavity, elliptical cavity, the required size volume EB welding facilities very few are in our country. Mostly it is with defense and ISRO at Bangalore and Trivandrum as well as DLDL Hyderabad. They only have bigger size of this thing because of their project having large size of component, and they have higher beam this power also. But in private industries, except ASACO, nobody has this bigger size EV welding machine, and that is from Tech Meta, France. But as you have told that if this type of development, indigenous development is done and the required parameter, because here in this electron beam welding of niobium, the quality of weld or strength is not important. You have to maintain a triple R at the weld zone region within 10%. That is the international requirement. So meeting that, you should have very clean type of furnace actually, and generally people use these furnace in this EB welding internationally. They keep dedicated for this type of metal joining. So it will welcome and it will be very encouraging if organization like you come forward to make such machines of required size and parameters.
Thank you, sir, for that. We have to collaborate.
Yeah.
Because all the facilities we cannot have, like a MSc or SME, like Arctic Welders Private Limited, they cannot have all the facilities.
Mm.
So if some of them can be outsourced and we can do the welding, only welding, then we'll definitely make a bigger machine, which is having bigger chamber and require power for welding this 5 cell cavities.
This is requirement also for our government of India. These things that as far as possible, most of the technology should be more indigenous actually. But since Staggerwalt or Tech Meta, these companies, various years of lot of R&D, they have made, even in fact, they are working with Fermilab to do internal welding by proper electron beam optics actually. And if these type of things are quickly implemented with proper collaboration when an international machine builder, it can be done actually.
Yeah. Okay, I would like to thank Madam Archana Sharma, because she has encouraged us to make a machine, and we could make a machine within 2 years. Thank you, sir. Thank you, madam. And thank you, sir, for your nice talk.
Thank you. There's one question.
Choksiji, is there any plan to test cavity made of bulk niobium in cryocular based conduction cooled?
Yes, actually, but presently the cryocooler what we have is of low power. We should require cryocooler of that watt.
But you can get.
But once, yeah, because our efforts for doing NB3SN based coating is going on with BRC, and
why not to test this cavity which is made of bulk niobium?
Yeah.
Using maybe commercial.
Only thing presently, I think cryocooler will be of that power actually.
But you can get it commercially.
Commercially we can get.
Have this kind of plan, then we will first test the niobium cavity and later on we will convert NB3SN cavity, which will be.
Yeah,
that is good.
Thank you. And in case there are no further questions, or we can have questions during the tea time, let us thank the speaker once again. And I request organizers to So the last talk of the today's session is on the advanced manufacturing techniques for accelerator components, and it is by Shri Abhay Kumar. Shri Abhay Kumar has many peer-reviewed journal papers as well as awards by IIW, and his areas of research work include engineering computations, material joining, product and process design. So I request Shri Abhay Kumar to please deliver his talk. His talk is for 20 minutes. I request the speaker to complete the talk in 15 minutes so that we can have 5 minutes of question and answer. Thank you.
Arrow up down.
Good morning. My talk was rescheduled because I was away to Bangalore, and this morning only I have arrived. So, one topic which has troubled the accelerator community is when we do any processing with a stainless steel, although it is a paramagnetic material, it becomes shows a lot of ferromagnetism, and the magnetic permeability goes into 1.3 to 1.9. So, lot of processing is to be done with stainless steel so that it does not distort the magnetic field. If there are a couple of so basically we are now when we started our journey in 90s, we also considered 304L, but with time we have learned that 316L material is the best material to use in accelerator. Maybe 316LN is another competitor, but 316LN is not easily available. That is a big problem. So off the shelf, if you want to buy material, then you have to go for 316L material only. So basically it is because of high nickel content. It shows some different properties and it is more austenitic and more stable in maintaining its austenitic character and non-magnetism. So that is why we use 316L. Welding is the biggest problem because the moment you weld it, the ferrite content in the weld increases and the magnetic permeability can go up to 1.3 to 1.8 or 1.9 also. Forming and machining introduces a strain-induced martensite, which again is a hard magnetic phase. So that creates magnetism which is more difficult, and these phases must be converted to austenite phase to maintain its non-magnetic properties. So these are the challenges. So what we have done, so this technology is now deployed in injector microtron, and this commissioning was achieved in 3 hours because there was no distortion of magnetic field, and the vacuum chamber of microtron is completely inside the dipole magnet. So there the magnetic hygiene is extreme. So what we have done here is we have used a filler which is having higher percentage of manganese, and the base material was 316LN because the hygiene requirement was extremely high. So now this technology is already available and we are able to achieve this kind of magnetic permeability 1.003 to 1.005. So when for extreme cases, this is the only technology that we have to use, but it involves use of 316LN material. Now this is what we have developed in last 4 or 5 years. We have worked on this technology where we mix about 2% of nitrogen in the shield gas. So what it does, nitrogen is a very potent austenite stabilizer. So what it does, it makes the weld metal 316LN. So your material is 316L, but the weld metal is 316LN. So you get that kind of magnetic performance. But here you will get about 1.04, 1.03, 1.01. So those things we can achieve. So this binary gas mixer also we developed because that was very expensive component and we had to import this. There was a company in Germany, WIT. So that part now we have developed and this is now being given to an industry. Within 1 year it will be available in market. So all those who are supporting us, all vendors, manufacturing facilities, manufacturers will have this facility with them. This is a very low cost binary gas mixer which will cost about 6 to 7 lakh, whereas the WIT mixture is costing about 20 lakhs. So deployment of technology of at shop floor for the accelerator community will be easier. Now if you compare both the technologies, you can see that this is one which if you require very high magnetic hygiene, then material has to be used 316LN. We are trying to work out with Midhani that whether we can increase more nickel, we can have more nickel and get rid of this nitrogen requirement, because that is more difficult to achieve for a metallurgist when he is melting 316Ln. So that is possible because if you see that Sandvik pipes, they have 14% of nickel. So technologically there is no issue, weldability is not a problem. So if we get that, then we can achieve this performance from 316L also. So this is one automatic TIG welding station which we have developed very recently. So now all the trials we can do where we have a all controls, so in XY plane, also a tubular geometries we can do. So working on welding research towards product development has become easier. And you can see we have this one 15 kilohertz high frequency TIG source, which means we can go for arc constriction, and therefore we can go up to single pass joints up to 10 millimeter in thickness. And single pass joints is one of the ultra high vacuum requirements. So that is what it achieves from power source. Now there are other techniques of single pass joints that also we have worked at RRCAT. We have now completely developed this technology called activated TIG. So this we can do up to 6 millimeter in single pass. Again, all those things which are possible with normal TIG welding can be achieved here. It is ultra high vacuum compatible, and working. Yeah. So if you see comparison of magnetic permeability of various TIG welding technologies, you can see normal TIG will give 1.3 to 1.4 weld metal permeability, and activated TIG, it will give about 1.6 to 1.7, and that high frequency TIG, which uses a keyhole technology, that will give 1.7 to 1.8. But what we have done, this nitrogen mixing technology actually works for all three cases. So you can see for activated TIG, same thing you can we can achieve for HF keyhole, high frequency keyhole TIG welding also. So this work is in progress, but we have already got initial indications that it is following this track. So now if I add nitrogen in the shield gas and do activated TIG, so I can do 6 mm in single pass, and we can still achieve 1.03 and 1.01 kind of magnetic permeability for stainless steel beds. So this work is now complete for activated TIG. We call it AN TIG because we have added nitrogen into this, and this work we have started, but we have got indications that it can be deployed. Now another problem which we have faced a lot during these years at RRCAT is how to get rid of magnetism. When the material has magnetism because of the processes, machining, forming, all those things, how to get rid of that. So on the heat treatment part, we have worked exclusively to understand this phenomena and make a formal recommendation of heat treatment temperature and time. So if it is only delta ferrite, then delta ferrite to austenite conversion takes place at 95 degrees. This is a critical temperature where it starts. Now if you have very thick material, then you will have sigma phase also in 316L, because when we are doing solution annealing, the inner core will see higher temperature in that range where sigma phase is found for a very long time, this temperature range. So you will find lot of sigma phases there. So when you start doing annealing, actually what happens, the magnetism increases. So why? Because sigma first gets converted to delta ferrite. So at times we observed that after doing this heat treatment process, the magnetic permeability has increased where we expected this to decrease. So then we found that is happening because I think Gautam, you remember there was one case, right? So then we investigated why this is happening. So it is because of the sigma phase formation. So then we found that, okay, if this is the case, then this is the temperature where it starts, but initially it is pretty slow. Then strain induced martensite, this is the best temperature where 1000 degrees centigrade where we can convert strain induced martensite into austenite. So this is the temperature. So finally what we have done, that for 1 inch thickness, if we go for this temperature, we can get rid of magnetic permeability altogether. This we have already discussed. But suppose you have no such concerns and only weld is your problem, then 950, see if you look at degassing temperature, that also we have worked on. So based on this requirement, what we have done, that we have increased the degassing temperature itself to 955 degrees centigrade, so that you do not run the cycles again and again. So at this temperature, if we run for 120 minutes, the degassing cycle is complete, but in that process, you are also getting rid of magnetic permeability. Then stress relieving normally we do at 900 degrees centigrade, but that's although we have now modified to 955. In the same process, we can reduce the magnetic permeability also. Then solution handling, normally it is 1040 or 1060 degrees centigrade, so you see a lot of grain growth. So then that also we have reduced to 1000 degrees centigrade for 360 minutes per inch of thickness. There you get the best performance of reducing magnetic permeability. So these are not standard heat treatment procedures that we do in industry with austenitic stainless steel. These are special ones which handle our problems in a better way. Now I come down to joining technology that have been developed or are under development. This is ARPF's X-ray target. So to the best of our knowledge, this is the first metallic target. This is your tantalum material, and this flanges and cooling channel is made of titanium. So this is a simply TIG welding of titanium with tantalum, and this has been now made and has been tested at 3 bar. The operating pressure is only 2 bar, but we have tested 3 bar, 200 rays continuous and about 100 cycles, and pressure testing was done at 6 bar. So no leak is observed here. So this we consider that this technology has been developed, and now we will have very long life X-ray targets. So this technique, what we have done, basically we have shifted our power source, heat source to tantalum side, so that this is a very high temperature material, a refractory metal. So that way we are trying to manage this, and very good support from the phase diagram. They have got very good miscibility. So using this, we have developed, you can see the tensile strength is also pretty good. So we are using all sorts of techniques that we use for titanium welding. So gas lenses and all back purging, all those things that we have used. So this technology is completely developed. When we are going for an industrialization of industrial linacs or mass manufacturing, so in that time this technology can also be transferred to industry.
Now, please conclude in 2 minutes.
Yeah. Okay. So I will skip this because this is another technique which can be used. Now, niobium to stainless steel for our Indian program, I think SSR1 was having this, we supplied to BARC, but now titanium is the helium vessel for that also. And this is niobium to stainless steel joints for elliptical cavities. There are 4 joints between niobium and stainless steel, and 1 welded joint in stainless steel and stainless steel. So this whole thing has been developed and is tested. So this technology is ready. So at times when you need this, at least this know-how is available with us. It depends on the designer which way he prefers. This is with titanium and stainless steel, that also we have developed for the 2-phase pipe of titanium vessel. So whole technology is ready. This is using brazing between stainless steel and titanium. This is about aluminum to stainless steel vacuum brazing. This is a very unique field. I don't see a lot of papers in vacuum brazing of stainless steel and aluminum. That is completely developed here and can be deployed for many cases wherever is the requirement. This is diffusion bonding of aluminum to stainless steel. We have achieved joint strength of 180 megapascal. Now we are trying to do it on the technology front, how to convert this knowledge into making products. This is titanium to stainless steel. This is another technology that is completely developed at RRCAT from scratch. This is a thread filled configuration. So there is a male and female thread in which a third metal is filled. So this is a very high strength, a smart joint where you can design the joint for strength. You increase number of threads and you increase the strength of the joint. This is a aluminum to stainless steel using the same technology, thread filling technology that is developed. And here additional thing is that the temper has been regained, which is a very difficult thing for 6061 alloy. And you cannot use this alloy unless the temper is there. So that also we have done, which takes it to again 500 degrees centigrade. The joint is made at 600 degrees centigrade and the heat treatment is under 500 degrees centigrade. So quite a challenge to do this. So we have done proper fixturing, and at an industry nearby, we have done this tempering process. So this is I think Mangesh, you have already shown this. Huh? I'll skip this. So there only this optical fiber feed through we have developed for measuring temperature, and luckily with this, when we try to prove its HV compatibility, we could prove the UHV compatibility. So it goes into -10 millibar ultimate vacuum. So now if you want to measure temperature inside ultra high vacuum, you can do using this optical fiber. So this was one effort which we made for our vacuum induction brazing. I'll not go into this because Mangesh has already shown this slide. Okay. And this I will rush through this because it's not much, time is not there. So this is a ceramic to metal products. You can see this is a sputtering target, silicon carbide to, this we have used molybdenum here. This is a electrical feed through which is completely made in RRCAT. So our objective is to help designers in converting their ideas into reality as quickly as possible. So these in-house facilities will help them getting the products in a day or two so that they can quickly move ahead and prove their designs. Although I think Indian industry is now capable of doing all these things also, but oh, this is the miniature SMA feed through. This is a very typical job. You can see kinds of materials, since it was made in one single brazing cycle. You can see how many materials are there. So this is now proven. So this is for industry. These are our Linux. So here in machining, what we have now found that for industry, we have done some trials and we can see that we can achieve this accuracy and this surface finish on our Indian CNC lathe. So this information, this knowledge can be transferred to Indian industry when we are building industry. So these things are, of course, brazing we are doing for a long time with 100% success rate. So far, all the linear accelerators made at RRCAT has been made at DMTD only. This is FEL Linux now completely, this we have completely indigenized FEL Linux. This Indus 2 cavity is already installed in the ring. This is completely made at RRCAT. This is RFQ, we made the first segment by brazing. Of course, machining also is done by RRCAT only inside. And with 10 micron volumetric accuracy of the veins, and then brazing it in this furnace with 140 hours long cycle we have operated. We have struggled a lot because the furnace was not designed for this kind of operation, but the technical requirement of making RFQ was that, so we had to improvise and do this job. So now we are confident that we can do this. This is a one job which we did for VECC. So this is angel lens assembly. This is our ECR proton source that we have made at our place. This is also operational, and you can see a lot of intricacies in the design. And this is one technology where I think CAT is the only option, and we want to proliferate to industry so that industry can do this. This is the electroforming. We are building such big components by electrodeposition only. So this is completely additively manufactured component at room temperature. This is already given to the group, and it has qualified all. This is a one quadrupole.
Pointed to
Okay. And this is one bellow which we have made in nickel using electroforming. Now we are trying to do this in alloy, nickel cobalt. This is pure nickel. We can also make copper bellows using this technology. So I think this is the last one. Thanks. Yeah.
Thank you. May I invite one or two quick questions? Yes, please. Krishnaji.
Welding, the material gets somewhat magnetized. But have you seen some directional properties in magnetization? Because
normally, see what we do, we use permeability meters that we have. So we only measure magnetic permeability. We have not gone to that level because the problem is if it distorts the magnetic field, because magnetic field will be concentrated through that material. So in the nearby region, there will be rarefication. So you have a magnetic field distortion.
Generally, in many processes, the magnetization is directional, has directional.
I don't think it is directional here.
Oh, you should. And then your material is also inhomogeneous by very nature of the welding. Somewhere.
Yes, yes. Weld material will be different from.
What sort of sample do you take? So
See,
that
there are various kinds of measurement. See, in situ measurement, you take the probe there at the weld and do it. But we have tested this technology up to 2 Kelvin also. So it is fit for helium vessel construction also, this technology. So there we take a sample right from core of the weld. This is 3 millimeter by 3 millimeter sample, 3 millimeter diameter and 3 millimeter length. So there is a paper which we have wrote in this published in Welding Journal, where these cryogenic qualifications are also given. So there you need a very small sample.
What I wanted.
Can I request you to continue during the free time?
Okay, thank you.
We can so that we can have one more question. Thank you.
Thanks for a very good talk, Abhay.
Thank you, thank you.
This is not a question, it's just a comment that you are addressing some of the problems which accelerator community faces.
Yes.
So special thanks for that.
Yeah.
And for cryo module things where I am working, I would definitely get in touch with you because there are some places where after seeing the presentation, I think we can use them.
Yeah, that is the objective of presentation.
Yes. Thank you.
Indeed. Thank you. Thank you very much. And thank you, Abhay. Let us thank the speaker once again. And on behalf of the organizers, it's my pleasure to present you a memento. With this, I close this session and I hand over to the organizers. Thank you.
Thank you. Let us thank Dr. Mangesh Borge for efficiently managing the time schedule of these sessions. I think we are 10 minutes. We have exceeded only 10 minutes. And that is quite acceptable. And now I would like to invite Dr. K.K. Pant, Head, Free Electron Laser and Utilization Section, RRCAT, to present a memento to our session chair on behalf of organizing committee, InPAC 2025. Thank you, Dr. Pant and Dr. Mangesh Borge. And let us quickly break for a tea. And our next session will start at 11:10 a.m. sharply. You should be back by 11:05. 20 minutes.
I request all the thesis presenters in the next session to please contact at the backstage. All the thesis presenters, please contact at the backstage. And in the next session, we also have the industry participants. Please contact
Hello, welcome you all in the next technical session. In this session, we have a technical talk, then 3 thesis presentation and presentation by industry. To chair this session, I invite Professor P.Y. Nabiraj, outstanding scientist, VCC Kolkata. Although for Indian nuclear fertility does not require an introduction, but for the benefit of younger audience, I give a brief introduction of Professor P.Y. Nabiraj. Professor P.Y. Nabiraj did his Bachelor in Technology from Gulbarga University and his PhD from IIC Bengaluru. He is the product of 36th batch of BRC Training School. He presently the Dean HBNI at Kolkata and member of the Board Studies Interdisciplinary Science and Engineering of HBNI, had ECR Iron Source Facilities Section and Cyclotron Control Section VCC Kolkata. Professor Nabiraj has more than 40 publications, period journals, and recipient of many awards and recognition, including the DAE Scientific and Technical Excellence Award. So, sir, please chair this session. Thank you.
Hello. Can you hear? This session has three parts. One is the technical presentation, the other one is the presentation by industries, and the last one is the thesis presentation. So the first one will be presented by Sri Prashant Khare. And to introduce him, I think everybody knows about him. He is a BE mechanical engineer, and his main research area is cryogenic engineering and its applications, societal applications also, SCRF cavities. And he has a large number of publications. And he has got a good number of awards: Homi Bhabha Science Technology Award 2018, DAE Scientific Technical Excellence Award, Group Achievement Award, and also worth noting is that 6 patents also have been received. So I invite Prashant Khareji to present his talk, and it is for 20 minutes. So let us stick to the timing. We are already running late.
Good morning. Today I'll be talking about the cryomodule technology development at RRCAT and its spin-off. When I saw the whole program, I understood that this is on 4th day. By that time, all of you must have been super saturated with all differential equations, graphs, etc. So I have tried to keep it a very simple, generic kind of presentation where there are mostly photographs. So just be at ease. And now I start. I will first like to say that this is a combined effort of all the colleagues of PAG. So I thank them all. So the outline of the talk is that first I will introduce cryomodule and path chosen for technology assimilation. This is a very complicated technology. So it was thought of that we should have a proper plan. Then I'll go into the chronology of the project, that is work performed for different options of cryomodule, etc. Then I'll go to the first design and development of 650 megahertz cryomodule. It's a 6 cavity cryomodule. Then the second step will be design and development and installation of HTS cryostat. This is akin to a 2 cavity cryomodule. That is why it was taken as the first target. And third is some value engineering. I'll present only one of them, that is the laser welding of SCRF cavity, and then I'll move on to the path ahead. So the first part, first introducing the cryomodule, it's a building block of any accelerator based on SCRF technology. You put all these cryomodules one after the other, of course, as per lattice given by people like Vineet. and then you have the LINAC. The cryo module is an enclosure that supports and houses cavities. Both words are important. It is supported on the cryo module as well as it houses, I mean to say, it provides that cryogenic environment to them so that the cavities can operate at 2 Kelvin or 4 Kelvin as the case may be. A very important part is keeping them in good alignment even after cool down. Just imagine something which is 10-meter long and the axis of the cavities, this like here there are 6 cavities, they have to be within 0.5 millimeter. And add to that complication, that is, this should be there even after cool down, and this is an intangible axis. You have to just make out where the axis is. So then, because cryogenic environment is extremely expensive, we have to feed all these things, RF power, sensors, etc., with minimum heat in leak. So that is another big challenge. And then cool down of limited cool down and warm up of limited length of the string has also to be done. So this is what cryo module is all about. Geographically speaking, this is the cavity, this goes inside the cryo module, and this is where you keep the cryo modules, and then this becomes your LINAC. Now, what are the challenges? A significant design effort and technology assimilation is required. I will like to say here that it is not only us. Way back in 2007, Fermilab, who now is supposed to be an expert, they called people from DAISY and got their first cryo module made. They went to DAISY and learnt it. And like that, it has taken them a pretty long time to assimilate this technology. Then we need a large infrastructure to assemble cryo modules. Human resource development is very necessary. Designing, assembly, cavity string assembly technique, alignment, RF measurement during assembly. All these things are necessary, and then only we will get a cryo module. I would like to mention that making one system, two systems perform on the test bench is easy. But if we have to put them all inside an enclosure and make them run in tandem, that is a challenge. So that is the challenge which will be there in making the cryo module. In the morning, we heard Mr. Singh, because ADSS will need this kind of cryo modules. So coming to this slide, here I'll take some time. First, we participated in it with help of Fermilab. We assessed different cryo module design options which are there. Then we established a small facility. We call it cryo module component test rig. This is not done elsewhere. We were doing it for the first time. So we made this system. Then we prototyped these components. We tested them inside the CCTR. After this, then we went for design of HTS. As I said, HTS is a, what should I say, small scale cryo module, same size cavities, everything is same. But it will have 2 cavities only. So we made this. Then fabrication and installation of HTS cryostat at RRCAT was done. Here, the point which is very important is, we decided that the fabrication will be done in Indian industry. The reason for that is, we wanted to develop vendors for cryo module, because when we will make our own cryo module, we will not go abroad to do it. So this fabrication was done in Indian industry. Messrs. Inox, I don't know whether somebody from this company is here. So this was done. It was successfully installed in RRCAT, and after installation and commissioning, the system was sent. The second system, I'm sorry, I didn't mention, 2 systems were made. One was installed here. The other has been sent to Fermilab. It is on the way, and within another 15 days, it will be reaching Chicago. So this is kind of a complete, for HTS, this is a complete circle that we have completed. Cryo module, of course, we have to start. So now chronology of the project. This is something that we did for the first time. This is a 1.3 gigahertz cavity cryomodule. We designed it with the Fermilab. Basically, it was Fermilab was doing everything. We were just trying to learn. We did some engineering analysis, etc. But subsequently, they changed the frequency from 1.3 gigahertz to 650 megahertz. Then for this 650 megahertz cavity, we decided about we were a part of many iterations which were done for finalizing the inner configuration. And but in the end, Fermilab decided to go for not a top supported cryomodule, but a bottom supported cryomodule. This side has been seen many times, but I put it just because I want to show that here, this is what we are talking about. So now we have two objectives in mind. One, we need a complete technology transfer so that we are able to design and development cryomodules for DAE project. This is our first target. And of course, we have to fabricate one set of components for one cryomodule and send it to Fermilab as in-kind contribution. So coming to this is how the cryomodule looks, because as I said, this space is very expensive where we have cryogenic conditions. So this is a highly dense system with vacuum vessel covering here, strong back, cavity support system, thermal shield, piping, etc. And yes, this shows, this is the strong back. We put the string assembly on this, put all the piping, then there is a thermal shield, it goes inside the vacuum vessel and we get the cryomodule, but it is easier said than done. These are the specifications, I won't go into the detail. It's a 6 cavity cryomodule, that is what I want to mention. This is how it is getting cooled. We get 5 supercritical helium from here. It does many things. Once it cools down the cavities, also gives different thermal straps are there. This gives a kind of thermal support and for these things. This is the facility that I was talking about. In this, we can cool down things up to liquid nitrogen temperature and assess the performance. We call it CCTR. This is one of the examples. This is a compound cylinder with 3 components. The mechanical engineers would remember it from their college days that this is what we used to for analysis. The advantage is it supports cavities with very low heat conduction. Then we created this kind of a scheme where we can assemble cryomodules, and this is like the string assembly comes here. There's a spreader bar which lifts it. Then this is supported on a strong back, and then thermal shield is put, and then it goes inside the vacuum vessel. So the cryomodule assembly, the hall is ready, and you can see the spreader bar mechanism. This is also ready and tested. Now we will be putting rails here. So this is, and anyway, I have showed it. So now coming to the HTS, this particular thing, this is a continuous type of cryostat where 2 cavities are there. It is tested, and you can see how intricate are the piping there. And we designed it with Fermilab, but this time we had a much bigger share of design. And after doing this, we prepared all the fabrication drawings, etc. And then after the review by Fermilab, it was fabricated in Indian industry. These are the specifications. And as I said, it has been fabricated at Inox India Private Limited. And this is how it looks when it was being fabricated. This is the support post, this is the feed can piping, the thermal shield, the vacuum vessel, and then it was tested there under PDI and then commissioned at RRCAT. And I would be very happy to tell you that this gave us an exposure to the culture, that how Fermilab and we can work together. There were travelers which were going back and forth. My colleagues Rupal and Shailesh, they were maintaining the travelers. Each and every step, we would get a nod from Fermilab before going ahead. That taught us so many things. So this was done. And at that time, it looked to us that this is a big catastrophe which has come. But today we realize that it was a blessing in disguise, because what happened 2 years after we had installed and commissioned, something called cold leak appeared. And this is a nightmare for all cryogenic engineers, because this is a leak which does not show itself when it is at room temperature. It appears only when you are at cryogenic temperatures. And this particular leak came, and cold leaks are very difficult to diagnose, but the team, and here I would mention that it was our cryogenics team also which was with us, and we found out the leak, we repaired it. After this commissioning was done, now the question was to sending the second piece of the cryo module, of the HTS cryostat. First is installed at RRCAT to Fermilab. Now, till now, the cryostat had seen a shock load of something like 3 G when while its shipment from Baroda to this place, but in sea voyage, this can go as high as 10 G, more than 3 times. So proper analysis, etc., was done. Then in a huge 40-foot container, and incidentally, it's a huge system. It's not a small system. This was put, and properly shock mitigation, etc., was decided and applied. And this is because we have to take care of all eventualities. There could be heavy rain, etc., when it can come. So this was put in this container, and this is how it has been properly lashed. And now it is, it's a huge system. The all size you can see 5 meter by 1.8 by 2.66, and feed can is 1.37 by 2.67 and sorry 2.4, 1.37 and 2.67, and it weighs roughly slightly more than 6 tons. So this we have sent, and by 15th April, this would be there at Fermilab. Now a bit of value engineering. We decided that because RRCAT is a place, I'm sorry, I didn't mention this. This work has been carried out with support of Dr. B.N. Upadhyay and his team. Normally, as we have seen in the morning, that electron beam welding is followed all over the world. Ever since 1991, there have been efforts to make it with laser welding, but nobody succeeded in the world. So we started this activity, and we took patents, and when we were almost ready, the gentleman seen here, Professor Hasan Padamsi, उनकी किताब को हम बाइबल की तरह यूज करते हैं SCRF टेक्नोलॉजी में. He himself came down here to see this, and he gave very useful suggestions also. And finally, the very first cavity went to 31.6 megavolt per meter with a Q of 10 power of 10, and this was a single cell cavity. Subsequently, we have made a 5-cell cavity also, which has yet to be tested. Now, what are the advantages of this laser welded cavity? Lower capital coins, something like 25 times less. Operating cost is 39, something like 6 times less. But production is 4 to 5 times higher. So this is the economics, performance. Again, the advantages is in number of times. The heat affected zone is 6 to 7 times less. Energy deposited is also 5 to 6 times less. And between samples, shrinkage varies only by 10%. So whatever distortion and shrinkage is there, it is highly predictable. Then we have, oh, I'm sorry, I forgot the welding is not done in vacuum environment, it is done in argon environment. So that is another advantage. And because we have argon jet, so all the muck which is coming out, that is successfully cooled, and what we get on the surface is low contamination. So these are the advantages. Now, the reason why I am showing this slide today, this was the background. The reason is that now we have been asked by our director Malche Saab, I am thankful to him, that this has to be revived. This was kind of in cold storage. So we have started doing it and we have achieved good result. The thickness this time is 2 times higher. So because of that reason, all parameters had to be revised. From 1.7, we have gone to 3.4. So you can see we have reached this place that in a very short distance of 2 millimeters, the RR has dipped below 300 to 260. And I have consulted experts outside India also. They say it is good, but for production, you need to improve it a bit. So this is what we are doing. But just want to say that this technique is being now revived. So now what is the path ahead? We have divided the cryomodule components into 4 groups, and vendor development has been completed. As I said, the HTS development gave us a very good support because we knew who are the people who would be interested and what are their capabilities. We have visited them with the fabrication specifications, what will be the timelines, we got their budgetary estimate, etc. So we are just ready for procurement. We are only waiting for Fermilab to say yes, and we will start indents. Second thing, because we have 2 objectives. First is DAE's, for DAE program we need complete technology assimilation. So we will participate in assembly and testing of cryomodule so that the technology assimilation task is complete. Now coming to a societal application, this is not a spin-off of cryomodule technology, but something interesting which has come out as a result of whatever little cryogenics we know. It is very much relevant for DAE because our vision statement says this is to be achieved by making India energy independent, contributing to provision of sufficient, safe and nutritious food and better health for our people. Under this, we have a vision scheme 5, which is for food safety. And I can share with you that the maximum loss of this fruits and vegetable is 18 to 40%. So imagine what is the condition of farmers who are producing it. That is why we have taken it up. So what we have done, this is a container in which we can maintain temperature, humidity, and also provide inert atmosphere. Because of 3 of these things together, we can keep life of fruits and vegetables very close to their optimum shelf life. And then the farmer gets a chance to get better prices. We get a chance to buy things at much lower rates. Now, what is the advantage of this? This is not cooled by CFCs or powered by diesel. It is 100% eco-friendly. As was mentioned in one of the slides, we have commitments for on carbon footprint. No diesel, no electricity, no carbon footprint. It is cooled with liquid nitrogen, and because there is no compressor, nothing, so minimum maintenance and breakdown, while dynamic system and no dynamic system excepting a fan and a wall. It will have a very long refrigeration system life of 15 years. For regular CFC based and diesel powered systems, it is only 5 to 6 years. Because we are maintaining these 3 things, the freshness remains intact. So the loss of fruits and vegetables, which I said is very high in India, will come down with this. And using liquid nitrogen, now a point comes to mind from where to get all this liquid nitrogen. You will be surprised to know that India has an excess capacity of 35 lakh liters per day. And now why it is happening like this? Because steel plants in India need oxygen. They take out oxygen from air by a cryogenic process, and whatever is left is liquid nitrogen. So that is something which doesn't have much use. In fact, our own IPR, my colleagues may be here from there, they buy it at the rate of 8 rupees per liter. Imagine 8 rupees a liter for liquid nitrogen. It is available in bulk. There are companies which are selling it. So this is a truly make in India technology, 100% eco-friendly, lab-to-land technology, and because of this excess availability of liquid nitrogen, we can say that it is also wealth from waste. So it follows all the directives of government. And because of this great person, Dr. Ratan Tata, who took interest in it, and he told Tata Motors to acquire this technology. This technology was transferred to Messrs. Tata Motors. They have made 2 systems which are, but they don't allow me to put their photographs anywhere. So I'm not displaying it here. And you will be very happy to know that this is one of the 75 landmark technological achievements of India after independence. And this selection was made by Indian National Academy of Engineers. They selected only 75 technologies in 75 years. And this is not from government sector alone. It is from government and private sector combined. And this is something that we could get. One very, I will say, unique feature of this development is this has been designed with the help of farmers. We used to go to villages. I have just put one picture here where the system is in front of a cooperative society, and farmers regularly came to us. And I have no hesitation in saying that they really taught us what is required. And because of this, whatever trials we have done something like 3,000 kilometers of road trials, and Indian Navy did 1,000 kilometers of trial separately. That is for their different type of objects. And it never failed. We took patent in India. We also took a patent in China. And finally, our USP. Our USP is that for 1 kg of fruits and vegetables, if it has to be
5 minutes.
Sure. If it has to be transported for 1,000 kilometers, the cost is less than 1 rupee. I can say it is 70 paise. So this is, imagine something grown in Indore going to still, let's say, New Delhi, and the cost increases by just 70 paise per kg. अभी तो सर 1 रुपए से नीचे का सिक्का भी नहीं मिलता. So it is 100% eco-friendly technology. This is the amount of CO2 emission equivalent which will be saved in 1 year by 1 truck. 1 refrigerated truck, I mean to say. It uses liquid nitrogen, as I said. It can ply on rough roads without breakdown. And refrigeration system has 2-3 times higher operational life. This is when we gave the technology to Tata Motors, and this is what I was mentioning, landmark achievement of engineering and technology in independent India. Here the Shabai system is there. And one last thing that I would like to say, from concept to technology transfer, it has taken simple 30 months. And in those 30 months, there was COVID which was prevailing. Hats off to my colleagues who wore those suits and went to Sabji Mandi, got the material, and tested it. So this is all credit goes to them. I forgot what was the name of that thing that used to wear. Some suits were there during COVID era. Yes, PP kits. So they used to wear that and go. So this has been done in another 1.5 years. The prototypes have been made, and now hopefully it is going to get commercialized. The first system has been sold, and this handing over was done in front of Professor Sood, who was here for our foundation day. So one company has purchased it also, which shows that the technology has got acceptability now. But it was not from Tata Motors, it was from an MSME to whom we had given the technology. So we finally, I acknowledge all members of PAG who and their support, and also that of Fermilab colleagues. Thank you.
It was a very interesting talk. This high-tech technology is not only in the lab, but it has also reached to other countries outside Indian shore. I think all along we have been importing, but right now we are exporting also. This is a very important thing, and I think we should all clap for this. So it's a very fantastic development of, extremely cheap. I think this is the cheapest refrigeration what I could see.
Yes.
Okay. So right now, 1 or 2 questions we can take quickly.
Yes, ma'am.
Yes,
Hello.
Shiva, I have one question. Recently, we heard Chokse about EV welding, and now you are talking about laser welding. And we know that aspect ratio in EV welding is much higher than laser welding. Even power deposition is also high compared to laser welding because of reflection. Then how do we see?
The
Because
amount of energy that we are depositing
it
is
will
less.
get reflected because of metallic surface.
Yes, it reflects, but the area where we are focusing it is quite less. So totally the amount of energy deposited is 5 to 6 times less.
When you go for 4 how do you compare aspect ratio EBW versus this?
Yes, ma'am, still it will be lower by a few times. Because I'll share with you why it is happening like this. This is a pulse energy deposition. Sorry, a pulse laser, and we go for very high amount of overlap. So what happens is, we operate at something like 1 to 2 hertz. So between 2 pulses, there is a very significant amount of cooling. If we look at more than 90% of the time, there is a gas jet and no laser. So what is happening is, unlike EBW, which is a CW operation, our heat affected zone is also less, and also the aspect ratio is also quite less.
It will affect longevity. It's if longevity of the weld quality will get affected if it is not having any trapped gas, whether it is argon or
That is very important. This gentleman, Dr. Ganesh, is sitting here. Madam, for 150 tests, which we have done through metallography, we have not found porosity in a single one of them. So that is not happening.
Commendable. Congratulations.
Thank you.
Thank you.
Anybody else?
Okay, so it was an overview talk, so probably I consider that.
So if no questions, I think we thank Kareji.
Thank you.
So,
Now, I request the session chair to present a memento to the speaker.
now the presentation will be from an industry. I invite D and S Electric Work. It is for 5 minutes.
यहाँ से ये up, ये down, बीच में पेंटर ये लेना है।
Good morning, everyone. Thank you for the committee for giving us a chance to present ourselves in front of you all. I'm Anurag Sharma from D&S Electric Works. We are manufacturing electromagnets, customized magnet coils, transformers, and other electrical products related to your needs. We are serving RRCAT, BARC, VECC, IPR, and now IUAC as well since past 30 years. And we are trusted partners of all of them. We do have in-house design capabilities. We do have fabrication facilities, and we are now expanding our testing facilities as well. What we do? We do fabricate magnets as per your design, or if you need design, we can do that as well. Other than that, we do have expertise in conventional magnets, water-cooled magnets, and fabrication of superconducting magnets as well. Talking about transformers, either you need a control transformer, a rectifier transformer, or any other kind of transformer. Recently, we have supplied a water-cooled transformer to RRCAT as well. And any other needs other than transformer and magnets, we can provide you inductors, whether it is a high frequency or line frequency. Few projects we have supplied to various units of DAE, which are high voltage isolation structures, superconducting magnet coils to both RRCAT and BARC, complicated magnet assemblies, then isolation rectifier and control transformers as well, and few of steering magnet coils we are under development with RRCAT. Presence of D&S Electric Works. We are present beneath the surface of Earth in Sun. We have supplied few parallel resistors through RRCAT on the surface at various DAE units and in the sky as well. We have supplied few magnetotorquer coils which are guiding and steering the satellites. Our capabilities. We do have in-house design capabilities, fabrication, and testing. Also, we are increasing our capabilities continuously as per the client's requirements. Why choose D&S Electric Works? We don't look after the size of project or the cost of project. Either it is a 3 mm coil or a 3 meter coil. We can deliver you both. Whether it is a small scale project or a mass production, we are ready to take the challenge. Current from few milliamperes to kiloamperes. We can supply voltage from few volts to thousands of volts. We can handle it easily. We do have proven track record in RRCAT and BRC, and now we are expanding our reach to global market as well. This is just illustration of size we do work on. On the left, you can see a 3 meter coil in length, and on right, you can see a small steering magnet assembly for supplied to BRC for SEM, that is scanning electron microscope. The scale is representing the size of the assembly. You can contact us on the given details, and for more inquiries or details, you can visit us at booth number 20. Thank you.
Yeah, can you also do permanent magnet based assemblies?
Actually, sir, that is an imported product, and we don't do that permanent magnet things.
Yeah, congratulations
Okay,
for all your contributions. Yeah. So we have a memento from organizers.
Thank you, sir.
We have the next presentation by Synergy Measurement Technologies Private Limited.
So good morning to all. My name is Avinash. I'm from Synergy Measurement Technology Private Limited. We are the authorized channel partner for Keysight Technology. Keysight Technology is a USA-based company that manufactures electronic test and measurement equipment and software. Earlier, it was the spin of the Island Technology and is oriented from the HP, Test and Measurement divisions. So we are the channel partner for the MP, Chhattisgarh, and Gujarat and Telangana region. So we are from the Synergy Measurement Technology. We are the leading electronic test and measurement company in India. We are having the head office at Hyderabad and branch office in Ahmedabad and Indore. And I'm based on Indore. So this is the portfolio of the Keysight. We are dealing with oscilloscope, function generator, multimeter, and LCR meter, AC power supply, DC power supply, vector network analyzer, signal analyzer, data acquisition card. So these are these from some range of the our oscilloscope, which is having the starting range from 50 megahertz to 110 gigahertz, which is available on 2 channel, 4 channel, 8 channel, as well as the different sampling rate frequency. And this is the our newly launched SG3 oscilloscope, which is having the bandwidth from 200 megahertz to 1 gigahertz, and it's having the vertical resolution up to 14 bits. And we have the waveform generator from 20 megahertz to 120 megahertz, and RF analog and vector signal generator from 1 gigahertz to 110 gigahertz. And this is the our recently launched compact signal generator, which is very lightweighted, and it is battery operated, which is having the frequency range from 9 kilohertz to 40 gigahertz. And we are also dealing with power supply, which is available 80 watt to 5100 watt. It is available in single channel, dual channel, as well as multiple channel. We also having the solution for the AC power supply, which is available on 375 watts to 18 kVA. We are having the vector network analyzer, which is available from 4 gigahertz to 67 gigahertz, which is available in handheld as well as benchtop model, as well as USB based model. We are also having signal and spectrum analyzer, which is available from 4 gigahertz to 110 gigahertz, which is also available in handheld as well as the benchtop solution we are having. We are also dealing with digital multimeter, which is available 4.5 to 8.5 digit DMM, also available in handheld as well as the benchtop solutions. We are also dealing with LCR meter, which is available from 20 Hz to 3 gigahertz. We are also having the impedance analyzer, which is also available from 20 Hz to 3 gigahertz with the different test fixture like dielectric test fixture, liquid test fixture, etc. We are also dealing with RF power meter and power sensor, which is also available peak and average power sensor. The range of the frequency is DC to 120 gigahertz, and with the wide dynamic range -60 dBm to 44 dBm. We are also dealing with source measurement unit, which is available in single channel and dual channel, which up to 10 femtoampere the resolution. We are also dealing with electronic design and automation software, which is very essential and useful to integrate the device modeling, circuit designing, EM simulation, and layout capability and system level modeling. We are also having the semiconductor parameter analyzer, which is very useful to find out the IV and CV and pulse characterization of the any electronics component. We also dealing with optical transceiver test solution. We are having the interfaces from optical and electrical interfaces. We are also dealing with quantum control system, which is the combination of dedicated hardware and software capability. All the product is available on the GEM. We also provide the GEM link for the same. This is the list of the major customer. We are present in defense, aerospace, RRCAT, IPR, PRL, SAC, BHEL, all the IIT, NIT, ISCR, etc. And this is my contact number. If you have anything else, please contact me. I'm based at Indore. Thank you. Once again, thanks to all of you.
Yeah, it's interesting to know that you have all the DC 2 gigahertz under one roof. Yeah, please. So now we have a thesis presentations, 3 thesis presentation. Before that, I would like to invite Dr. Arup Bandyopadhyay, Chairman of Thesis Evaluation Committee, just to tell the format of the presentations.
So, sir, as sir conveyed, sir, with your permission, we would like to present mementos to the industry participants,
Yeah, I think so. We should do that.
remaining industry participants. So, industries are essential in advancing the scientific objectives of for the successful realization of the country's Atmanirbhar Bharat mission. To acknowledge the participation of these industries, we would like to present mementos to them. And I now invite Shri Ramesh Kumar, Head RFSD, Shri Bharat Ravlani, Head in Electrical Engineering and Air Conditioning Section, Shri Preetam Singh Bagdwal, RFSD, Shri Shashikant Sohane, Head Superconducting Cavity Processing and Assembly Lab, to come on the stage for presenting mementos to the industry participants. I will now call the name of the industries one by one, and their representatives can come on the stage. The first one is from Forgewell Corporation. The representative from Forgewell Corporation is requested to come on the stage. The next one is Bharat Enterprises. Next is National Power Research Laboratory. Next is Hyoki Technologies. Next is Cryo Gas India. Thank you, all of you. Now the session will be continued as per by the session chair.
I request Dr. Arup Bandyopadhyay just to introduce the format of this presentation.
Hello, and it is good afternoon, I believe. Yeah. So good afternoon to all. So we will be having the thesis presentation now. And there are three thesis presentations will be there. In the field of accelerators, what we are dealing with, writing a thesis itself is a great achievement and getting the PhD degree. So first of all, it should not be looked as a competition. That is very important. So the ISPA has decided a 5-member committee. We are sitting at the front. So all the participants, the 3 participants, will present their thesis work in 15 minutes. So the criteria of evaluation, what we have thought about, first of all, we'll see the quality of the presentation and the timely completion. people should not overshoot time. If they overshoot time too much, that should be taken as a discredit. So it should be completed within 15 minutes. Secondly, we'll see the content of the thesis, and also there will be question answer sessions. And I'll request chairman of the session to give priority to the judges first. But then others also can ask questions. Everybody is free to ask questions so that the evaluations become more fun and more competitive. Okay, so I hand over the.
Just a minor addition. ISPA president is also de facto member of this committee, so 6 members.
Oh, 6 members committee. Sorry, I missed.
It is 12 minutes or 15 minutes actually? 15 minutes? Okay. So I invite the first presenter, Shari Rosili. She will speak on gas jet based profile measurement, ion beam profile measurements.
Hello. Yeah. Good morning. I'm Sherry Rosalie from BRC. I am here to present my thesis, study and analysis of supersonic gas jet based beam profile monitoring system for a high intensity linear proton accelerator, which I did in HBNI. So the outline of my talk will be, first I'll discuss the motivation of this work, then the gap areas, the literature survey, the work done, and the comparison with the international work, the highlights, conclusion, future scope, and some references and publications. So this is a slide which has already been presented by many of my seniors and colleagues. We are working on high intensity proton accelerators. We have world over a lot of high intensity accelerators are coming up. So we are dealing with new challenges relating to the higher current, higher intensity of the beams. So in our program, we have developing this accelerating structures for ADS and other applications in India. So for these high intensity proton accelerators, we are finding a lot of challenges in the new challenges in the instruments, which it has to be capable of withstanding this high intensity, high energy beams. So the motivation of the work is we need beam profile monitors for measuring the profile of the beam to control the beam and see that there is less beam losses, because with intensity the losses also increases. So we have actually tried some traditional methods of profile measurement like wire scanner and scintillating material, but what we have seen is when the intensity is high, it can damage these wires, and it can even saturate the scintillating material or even burn. So we have to go for non-invasive beam profile monitors for this high intensity accelerators. So world over, people are exploring many methods. One of them is using gas, which is minimally invasive. Means you introduce a gas and you can measure the ionization produced by it or the photons generated by the interaction between the beam and the gas. So one of the this is how it will look. We actually introduce some gas in the beam line, and we can see the glow of the produced by the beam passing through it. But here we need at least 10⁻⁻⁶ millibar, and we need 2 viewports. So people are exploring how to limit the deterioration of the vacuum in such large regions. Some people have tried inserting foils and creating gas cells. Some people have explored pulsed gas injection. But the recently supersonic gas jets are being explored, and these can give 2D profile of beam. This is an additional advantage of this scheme. So we decided to explore this. So during my PhD duration, there was a contract of DA which beautifully explained the requirement for this work. So the next generation particle accelerators are pushing the intensity to never before seen levels. So it is more important to measure and control the beams to maximize their efficiency. Traditional tools have no hope of surviving the impact of such beams, so a less invasive method is necessary. It is very useful for a number of projects. So it describes what are the studies that need to be done, the gap areas. So I'll be coming to this. Most of this was covered in the scope of my thesis work, all of it actually. So what is a gas sheet beam profile monitor? In a gas sheet beam profile monitor, we introduce a gas sheet into the beam line. Everybody here must be aware that the beam passes through a high vacuum, ultra high vacuum beam line. So we are introducing a gas sheet, and when the beam passes through it, it deposits some energy and create photons, the fluorescence. It also generates ions. So there are two methods of measuring the profile. One is ion profile monitor, and one is beam induced fluorescence monitors. So very less work is there in the beam induced fluorescence method, because it is useful in very high intensity beams, like in our applications. And its capability improves as the intensity increases. So these are the main components of a gas sheet generator. First, we need a gas source, which will, and then a jet generation, which will actually give a very directional flow of the gas. After that, we use skimmers and orifices to create the shape of the gas sheet, and then it will interact with the beam and create the ions or photons. And then this is the extra additional it has to be removed, the additional gas. Otherwise, the vacuum here will get deteriorated. So one most challenging region in work is creating this gas jet, and second challenge is the collection of the photons and reconstructing the profile of the beam. So the gap areas which I found was generation of gas sheet, pulsed operation. Pulsed operation will be very useful for us. Only introduce the sheet when we require to image the beam profile. Then simulation of the gas sheet. Open simulation tools were rarely covered in the literature. Then characterization of the gas sheet with, itself is very important for the reconstruction of the profile, because the density of the gas, the shape, uniformity are all very important parameters for reconstruction. So for that, the sensors required and the flow visualization techniques need to be developed for this gas sheet. And then the beam induced fluorescence itself was not covered well. The gas scintillation and optics design. So these are the other teams working. When I did the literature survey, there's Japan, then the CERN, and in US, Fermilab, many teams were working on these technologies when I was also working. So I could refer literature mostly from CERN and Japan for this work. So in Japan, initially they tried to make a gas sheet using oxygen jet, and they were trying to focus it using magnets. Later, they developed a new technique which I adopted towards the end of my work. This is called molecular beaming effect. When a gas is introduced through a long nozzle into vacuum, it follows the shape of that nozzle. Here, this technique, you are using a supersonic underexpanded gas jet, and then you are using skimmers to remove the outer gas, and the inner portion is supposed to have very directional flow, and then you are focusing it using magnets. In CERN, what they did was they continued with nitrogen gas, and they continued the shaping, the focusing using a number of skimmers. But this was a method which was prominent when I started my work. But this was very mechanically challenging, and you needed real precision alignment in this work. So these are publications from Fermilab America side. They have also explored both these techniques. So we started doing some simulations on supersonic gas jet, and we also developed an experimental facility for exploring. This is a pitot probe. There is an orifice nozzle in this. There is a high pressure gas, rebar pressure gas, nitrogen gas introduced through this orifice, and we were studying the formation of the supersonic gas jet. So this is an under-expanded gas jet, and this is what happens when we introduce a skimmer. So my next slide was actually a video. Unfortunately, I can't play this video. My PPT is not there. Are you 3 minutes?
Not supported.
It's not supported.
Not
Fine. So we actually used open tools for all these simulations. We used OpenFOAM, and we could get the time evolution of the gas jet, which is very important for our application because it is pulsed. This is a Pitot Pro we designed for this application, and this is a design parameters, and this is a sensor. This is a chip piezoresistive silicon pressure sensor with built-in vacuum reference and auto zero. So this was very useful in all the measurements. And we compared the flow, the plots with our simulation, the actual equations, empirical formula, the CFD simulations, and for very low pressure region, means the high vacuum region, we use DSMC simulation. And we compared with earlier literature, which was not in the pulsed, and we got very matching results. Then for flow visualization, we explored a technique called Schlieren imaging, which is used in aeronautical. So when we got the image, we could not see any flow. Then we applied image processing, like background subtraction and contrast enhancement, and then we could clearly see the shock wave around the Pitot Pro being formed. So we also did a DSMC simulation, and then we compared with the results. So all these are published in our in various conference and journal publications. So this was the original image, and this was after image subtraction, and this was after contrast enhancement. Then we did GN4 simulations for the beam-induced fluorescence studies. So in this, we introduced a proton beam, this yellow color, into a gas sheet, and the blue lines are the photons. And then we could simulate the optics, the aperture and lens, and the detector. And then we introduced a circular-shaped profile beam and a square-shaped beam. And this was the image we got at the detector. So we could see that it tallied well with the profile of the beam. So this kind of a study was first time done, and this is published in our paper, in NIMA paper. Then we try to change the study the effect of focusing, the change in aperture and the ambient gas pressure. So when there is gas in the ambient, we can see a trail like this along with the profile. And without the aperture and with the aperture, we can see how the focusing improves. So then we try to vary the thickness of the gas sheet and see how that is impacting. So we understood that the horizontal profile is actually widening. There is an error introduced in the measurement of the horizontal profile. Then we actually developed a gas sheet generator based on the Japan method. Here we have two gas sheet generators. This is the upper one, and this is the lower sheet generator. So when the gas expands into the vacuum, they will overlap and will create a uniform density region at the center through which the beam can pass. So this is the construction of the one single sheet generator. There's a reservoir, and the gas passes through a very thin slit, and it comes out, and there is one more skimmer slit when it comes out. So there will be two such sheet generators, and in the middle of this, the beam will pass through, and this will be at 45 degrees to the beam axis, so that we can mount a camera on the outside the vacuum vessel and capture the image. So this is the mold flow simulation we used. So these are the two gas sheet generators, and in between them, the sheet is formed here. So this is the transverse profile of the sheet. So we obtained results matching with our experimental measurements of the input pressure and the ambient wall pressure. Then we studied how the sheet uniformity is in the transform as well as in the longitudinal plane.
3 minutes, okay?
Yeah. So this is our experimental setup. Finally, we introduce a high intensity beam into this gas sheet generator, and we varied the gas pressure. So this is a very good indication that this is actually the glow coming from the beam profile monitor, because when the gas pressure varies, we are seeing a change in the intensity. Then we studied the variation with the current of the beam. And then we did number of experiments with different, how the wall pressure and the pressure of the profile is changing. This S by N, we measured in inlet pressure and the variation in the chamber wall pressure. Then we did benchmarking with a solid scintillator. So here on the left side is a image we got from the gas sheet, and the right side is with the solid scintillator, and the bottom is with the simulations in GANT. So we understood that this gas sheet is thinner than 1 mm based on this simulation. Otherwise, we would have seen a widening in the horizontal. So that way we confirmed the sheet is now a thin gas sheet has been formed. So benchmarking and simulations were carried out. And then we got the plot of the profile in the vertical and horizontal for both gas and solid. We compared it. And these are the profile variation with energy, current, and focusing current of the beam. And then we are these are the parameters we varied in this setup and studied. And these are the setup images. This was during the leak test of the internal portion. This was after delivery. We can see the 2 sheet generators. And this is after the system being mounted in the beam line. Now, these are the software tools used in this study for various purposes. And when comparing with international results, I'm grateful to my colleague for a very high intensity beam, because of which we could actually directly view the beam induced fluorescence. This was the first time this was being reported. The other people had not done such a study on such intensity beams earlier. So we got that advantage. And so the highlights of the work is we simulated the gas jet generation in rarefied flow domain using open and free software tools, studied time response of pitot in probes in supersonic flow. We could also have flow visualization using Schlieren imaging, and took large set of measurements to thoroughly study the system dynamics in low energy, high intensity range. We could complete the model of the beam induced fluorescence of gas for the first time using mole flow and GN4. So as a conclusion, this study and analysis was simulated, design, technology was developed, tested successfully, and benchmarked with a high intensity proton beam. The beam profile was clearly visible and accurately captured using a camera for various beam parameters. System performance was adequate for non-invasive 2D measurement in low and medium energy section. This was found. And developed simulation models can be beneficial for expanding the design to accommodate other beams and operational ranges. So in future, we plan to design for 20 MeV and 40 MeV phase and gather operation and performance assessment. So these are some of the references which I used in the work latest. And then these are the publications that were coming in the journal. Number of conference publications, including InPAC, 3 publications in InPACs have been given. Thank you.
Nice. You have almost completed in accurate time. The floor is open for the reviewers.
So, Sherry, thank you for completing in time.
Yeah.
And very interesting work. Can you go to the slide where you have shown the number of international publications you have done? How many of that? Just want to see.
Publications. Okay.
Yeah.
This is a journal.
Yeah, just hold it there. So you have one RSI, one NIM, and the third one is
Journal of Instrumentation.
Okay, fine. Now, at one point of time, you said UHV, but then I found the vacuum during your experiment was of the order of -5, -6, isn't it?
-5, -6 in the gas sheet, where we are introducing a bump in the pressure there.
Okay.
So that we can create enough fluorescence. But the surrounding vacuum in the beam line can be in the ultra high vacuum, normally in our proton beam program.
Okay, but then how do you take care when you are introducing the gas from outside?
Yeah.
It is always a dynamic gas load.
Yeah.
So how do you take care of the dynamic gas load?
Yeah, we need high capacity pumps, and we are introducing it in a directional way. So the design of the gas flow is such that it passes through and gets removed very quickly, and without degrading a large vacuum. Of course, there will be some ambient rise, but that is lesser compared to the beam induced fluorescence normal method, like residual gas method. In the residual gas method, we have to actually raise the gas pressure in the whole region.
Okay. And then I missed the last part. So you have, through your simulation, a profile, and you have measured that profile using gas system. And then how you have characterized it with some other method?
Solid scintillator was introduced into it. We used a pulsed beam, and we captured the image using a solid scintillator.
But the left image and the right image aren't matching.
The red one is a solid scintillator profile image.
Yes.
The
but if the
blue
scale is same, the
Yeah.
left side image is much larger, isn't it?
The red one is larger.
No, left side.
Yeah, because the ambient gas and there will be a glow because of the beam passing through the ambient also. Some ambient gas pressure increase is also there. But the central part is due to the gas sheet.
Yeah, so my question is that suppose on the right side is the actual picture of the solid scintillator.
Solid state scintillator, yeah.
Yeah, and the left side is what you have observed in your technique. So
Yes.
how do you propose from this left side technique to reach to that place? What has to be done? Because this is not
Actually,
1:1 correspondence.
yeah.
So how that should be done?
We can use higher capacity pumps so that the ambient gas is removed more efficiently. And then we can use image processing techniques. Actually, we get a Gaussian and we can measure the beam width even with this image. We are getting that.
Okay.
So what we need is to know the beam width and the beam profile. That information can be taken from this image by subtracting that background ambient. Like if you take a section here, you know what is the ambient gas profile, and we know the density profile of the gas through measurements and simulations.
Fine.
And then we
No,
can use
so I've understood.
Yeah.
So it is analytical you are doing. So do you have a comparison that the right side, what is the beam size, and the left side, whether by this technique, what you have achieved?
Yeah, we have done the comparison in the paper. We have published it actually.
You don't have it here.
Huh.
Okay.
The error we actually computed using this as a reference.
It's a very nice presentation. You mentioned that it is the supersonic gas jet which you are
Yes.
using. Why that needs to be supersonic?
The supersonic speed, the gas is very directional. It is easy to shape it into a sheet instead of, it will not, there is a shockwave structure that is formed which protects the surrounding gases from hitting these gases and
Okay, you
losing the
mentioned
directivity.
that this is actually meant for very intense beams.
Yes.
Right? So
Yeah.
if the beam is intense, normally the profile monitors will saturate. I mean, every profile monitor
Yes.
will have some saturation.
Yes.
So does that supersonic characteristic has to do something with its
With gas we can actually control the pressure, and we are actually measuring the image of the photons coming. So the material is here, the gas pressure can be controlled, and we can make sure the camera doesn't get saturated by adjusting its
I would
aperture.
guess that it is actually going out at a very high speed, so that is why it is not saturating.
Yeah, it's not standing there, that is there, but
Okay, the other thing is that it is not completely non-invasive because some
yeah, minimally
transmission loss,
Yeah.
there must be some effect on the beam, the emittance growth.
Yeah,
Is that something?
the loss has been studied by the Japanese team, and they found it less than 0.1%, 0.2%. That
Was
range.
it in your case? Did you measure the
No,
loss?
in my case, I didn't measure. There's already a work done by Japan, so we didn't repeat that.
And the emittance growth, has that been studied because of this?
Not yet, not yet.
Okay,
We
thank
have
you.
not.
Hello, Sherry. Nice presentation.
Thank you, ma'am.
Regarding the same slide which you are showing, you have done a benchmarking between the simulation and solid scintillator.
Yeah.
So anything related to beam parameters, can you quantify something on this?
Yeah, the beam parameters we have varied. This is a highly focused beam we have taken here.
Okay.
So we can actually change the focus of the beam, the energy of the beam, the current of the beam, and we have taken how it affects the measurement of the beam profile. That studies we have done, and see, this is the variation with the current. Then this is a variation with gas pressure, and we have done with beam energy also. With beam energy, beam current, focusing current, when we changed, what is the measurement? We have done those studies.
No, this is a simulated or measured?
This is a measured.
Measured.
It's a measured.
Okay. Have you done any error analysis or between the measured one and the simulated?
For error analysis, we had only this profile. This is like with scintillator and with our gas sheet. So we measured the vertical and horizontal, and we found there is a slight increase in error in the horizontal actually compared to the vertical.
And that is accounted for?
That is because of the ambient gas. If you reduce ambient gas, that error will reduce.
Okay.
Thank you for a very nice presentation. I have one question. Like you have used only nitrogen, and other people, like Japanese people, are using oxygen.
Yeah.
So, nitrogen was the only choice, or you had
They used initially oxygen, but later they also came to nitrogen. Oxygen had the advantage that it can be focused using the magnets, but nitrogen has the advantage that it has a higher scintillation yield.
So about the induced fluorescence, so I was
Yeah.
wondering if a higher atomic number gas might have given you better results, whether you have studied that?
Actually, in Liverpool, they have studied comparison with number of gases for various parameters, like the wavelength should be very sharp and the lifetime should be less, and the scintillation yield, that is the main thing, should be high. So they have compared many gases, and they have even done with metal vapors and all.
So you never thought that you should go.
From their results, it was very clear that nitrogen is a very good option.
And one more thing, is there any hardware you developed for this?
Hardware was developed. This was developed for this gas sheet generator was developed for this system only.
Okay.
This is the entire system. This was connected in the beam line.
Okay.
So this was developed in
So
Bangalore.
you did simulation and then developed the hardware.
Yes, yes.
Okay. Thank you.
Thank you.
Good, a very nice presentation. I just want to ask, you told about the alignment accuracies.
Yeah.
What kind of accuracies you are looking for this system?
In this system, we have no stringent alignment requirements. But in the earlier skimmer-based system, that was a very challenging part.
So
This new system using molecular beam flow technique has reduced that stringent requirement. Now we have a very like 1 centimeter radius area with uniform density. So it is not that stringent now.
Okay.
So that is one main advantage of this technique.
Okay, very nice presentation. Just I want to know one thing, that's the gas sheet.
Yes.
You are generating from the slit, na?
Yes, sir.
So what is the chance of it is exactly flat sheet will be there, or there may be some curvature?
Yeah, we have to ensure during fabrication and the joining.
The gas sheet generated by this slit will be flat, or it will be exactly flat, or some curvature will be there in the sheet, gas sheet itself.
It will start widening, not curve, but it can start widening.
Widening, that's fine.
Yeah, not curvature.
It will you are generating parallel sheets, na?
Yes.
But those sheets are slightly bent, or it's exactly flat. That's one thing. How can be then they are moving also. So there may be some delay between the interaction of this beam, generation of the fluorescence, and
Yes.
so those delay with the moving sheets.
Yes.
How they are going to affect the accuracy of your profile?
Yeah, so the delay in the proton beam hitting the gas and the photon coming out, that is in the nanosecond range. That for this night, that is one of the selection criteria also for the gas selection.
Now that speed you are deciding, the supersonic speed, it is moving with the supersonic speed.
Yeah.
Sheet is also moving with the supersonic speed.
Yeah.
So in that with that supersonic speed, how much the deviation will be there? That you analyzed or not?
Yeah, that is that speed is there plus the time for the photon. So that time has to be reduced. Means lifetime of that gas, the time required for it to get excited and
that you calculated or not?
yeah, it has been calculated. That delay will only create an offset maximum.
Yeah, offset,
So no error in the beam profile measurement actually. That is what is observed.
Error in profile. So what will be that error only? It is
No,
it will be some considerable.
in the profile, maximum the profile will have a slight shift, but the profile width and profile parameters there won't be any error visible because of this. It is negligible compared to at least the pixel error and things. That is.
Yeah, if any one question can be taken up. Yes. Yes, please.
Yes.
Showed that screen where as Dr. Bandyopadhyay also inquired, there is a difference between the profile monitor or the scintillating screen and this thing.
Yes.
But your simulation agrees well with it.
Yes.
So does the simulation take
The measurement means there
the
is
measurement? So is it because of some scattering or something which this simulation takes care of? And if that is true, then is there an energy? Because you have done it at very low energies. Whereas the literature you showed was at 300 MeV.
Yeah, we get the scintillation at this energy actually.
So can this be no, had it been done at some other energy, would you have expected a better beam profile?
the gas sheet, because this simulation is for the gas sheet and not for the solid state scintillator.
No. Your simulation of the gas sheet agrees well with what you saw.
Yeah.
Does the simulation takes care of scattering because your beam energy is very low?
No, it doesn't. There's no scattering effect here. This trail is because of the ambient gas also getting scintillated.
Ambient gas, you are in -10, you said.
Yeah, even that gets scintillated by such high intense beam.
Did you do it without beam also?
Yes. Without beam, we don't get this glow.
Then if you don't get it without glow, then
Without beam, the gas doesn't glow. With beam, the ambient glows slightly.
So
And
with
where
beam-
the sheet is there,
with beam but without gas sheet, do you get that glow?
no, we don't get. That is what we change the pressure of the gas. We change this ambient is rising because of the introduction of the gas sheet. When we introduce gas into the gas sheet, some of the there is a slight raise in the ambient pressure also in that in the nearby region. So when the pressure changes, we see the glow increasing. This is a when there is no gas pressure, no very less introduced gas, the ambient also doesn't increase. It is a linear relation. That's what we observed
Maybe I'll have a detailed discussion
in the
during
chamber.
lunchtime.
Okay.
Yeah. So I have one last question.
Yes.
Did you characterize the gas jet itself?
No, not directly. It was not possible.
Uniformity in the gas density across
Yeah.
the cross section.
Yeah.
So that
So
was
we
could answer
explored the pitot probe and all, but at this kind of vacuum levels, we don't have the sensors. We need a capacitive manometer, or we need Schlieren with higher sensitivity. We are working on that.
So that could be one of the answers for.
So for that only we depended on simulation. From simulation, we understood that if this is the profile, then we'll get this kind of a beam. So when that matched, we indirectly deduced the profile of the sheet.
Okay.
That is what we did actually.
Thank you so much for your nice presentation. I think we are running out of time. So let me call upon Hitesh Kevlani. He will.
We should thank the.
Thank you so much. I'll call upon Hitesh Kevlani. He will talk on characterization of ECR plasma and ion source.
Yes.
इसे नेक्स्ट इसमें बोल लीजिए हाँ
नहीं सकते वो वाला माइक नहीं
Hello. Good afternoon, everyone. My name is Hitesh Kevlani. Is it audible? Hello. I am Hitesh Kevlani. I have carried out my PhD work on the characterization of ECR plasma and ion beam in continuous and pulse mode under HBNI. So these are the outline of the talk. Coursework and publication detail, introduction, scope of the research, plasma characterization, ion beam pulsing technology, emittance characterization, and proton fraction characterization. So these are the 5 APS coursework at IIT Bombay and pre-synopsis details of the work. These are the list of publication. There are 3 journal publication in Journal of Instrumentation and more than 3 conference paper. I have listed 3 over here. One is in IPAC, International Particle Acceleration Conference. Introduction. So we are working on a ECR ion source. So we are matching the applied magnetron frequency with the electron gyration frequency, and we are operating at 2.45 gigahertz. So the requirement of ion source are low beam emittance, high beam current, better proton fraction. It should operate in continuous pulse mode, and it should give stable, repeatable, and reliable beam operation. So we have 3 ion source. This one is a LEHIPA ion source. This is a 3 electrode ion source. This is a 5 electrode ion source. Basically, it has a 1 add-on puller and 1 ground electrode add-on. And this is a upgraded 3 electrode ion source. So all the 3 ion source were designed by Dr. Pradeep Roy Chaudhary. So I have done the work on characterization of 5 electrode and upgraded 3 electrode ion source for pulse and CW operation. So this is the 3 electrode of LEHIPA ion source and upgraded 3 electrode. The difference is that electrode on a movable rail, electrode gap can be varied with the help of a screw assembly. Magnets are on movable rail, and it has a inbuilt excess shielding and compact footprint. So this is the this is the difference between 3 electrode and 5 electrode ion source. These are the 3 aperture, plasma, suppressor and ground. These are the plasma, puller, ground, first suppressor and ground electrode, second ground electrode. So we have used ion source in LEHIPA. We have successfully achieved 3 MeV in 2019, 6.8 MeV, 11 MeV, 20 MeV in 4 stages. So we have operated ion source in pulse mode. So while pulsing the ion source, we have pulsed the plasma. And we have, these are the ion source pulse beam, this is the beam entering to the RFQ, and this is the accelerated beam from the RFQ. So doing this, we have operated the ion source for a CW operation. But while doing the pulse, we are pulsing the plasma. So the behavior of plasma temperature and density is varying with the pulse operation. So to investigate that, this thesis has been, this work has been carried out. The scope of the research work, first stage is a plasma characterization, which will include a plasma density and temperature with respect to time and power other parameter. The second is beam pulsing technology, pulsing the extractor high voltage, and second is the pulsing the plasma. Third is the beam characterization with comparison of 3 electrode and 5 electrode ion source with operating system parameter, and the fourth is the proton fraction characterization. So starting with the plasma characterization, this is the basic Langmuir Pro IV characteristic in which we are measuring with the help of IV scan. This is the Langmuir probe we have used with the tip of tungsten, and it has a parameter listed here. So this is the data acquisition card made for the Langmuir probe and automation system for this one. So it can apply voltage shift and measure the current and get the IV data. From the measured IV data, we are measuring the protein potential, plasma potential, electron temperature and ion density. So these are the plot of the measurement of temperature and density from the Langmuir probe, and it has an error in the range of 7% for the temperature and 4% in the range of density. So this is the experimental setup for the plasma density. So this is a micro waveguide line. This is the plasma chamber extraction geometry, and we put a probe over here. So you can see the probe over here, and these are the some other 2 probes shown here. This is a setup for the 3 electrode ion source. So when we apply the CW plasma, so you can see the when we increase the power, we can see the electron current increasing and ion current also increasing, and temperature of the IV probe plasma also observable from here. So when we pulse the system, so you can see how the pulse to pulse plasma parameters are varying. It can shown from this IV plot. So if we plot the in terms of density and temperature, so as power is increasing, my density is increasing, and also because as power is increasing, electron energy gained by the electron increasing, which is useful for the increase in the density. And for CW, if you show the density is stable, higher, and temperature is very lower, and for a pulse, temperature is very high. So this shows that for the pulse operation of plasma is in transient mode. So electron and ion temperature is in transient mode, which will give higher beam parameters. Second, so this is the conclusion which I also discussed, increasing the power, increase the density, and decrease the temperature. Same way for the plasma on time. Second thing, the ion beam pulsing topology. So pulse operation is required for controlling the beam power. So beam power is controlled by controlling the beam current or the duty cycle. So there are 2 options: pulsing the ion source or chopper in the beam line. So I have investigated pulsing the plasma and pulsing the HV extractor geometry. So first case is the pulsing the plasma with DC operation of extraction high voltage, pulsing the extractor with the CW operation of plasma. So this is the first case where I am applying the 10 kV HV pulse on the plasma electrode and 2 kV DC on the suppressor and ground. Plasma in CW mode, so plasma is stabilized. So this can show you this is 400 watt power, forward power, and reflected power is 30 watt. This is a stable portion of the plasma. Electron and ion density are very stable. Plasma parameter are stable. So when we increase the beam pulse, this is the HV pulse, this is beam current. So as this is a 200 microsecond pulse. So HV pulse and beam pulse. As we increase the beam pulse pulse width, the stable beam pulse is extended. It has a ripple of 0.1, flat top of 100 microsecond, rise and fall time of 55 microsecond. And rise time depend on HV rise time, capacitance of HV cable, and extraction geometry capacitance. Second case is the pulsing the microwave. Pulsing the microwave, I am pulsing the putting the DC HV and pulsing the micro magnetron. So this is the forward power, this is the reflected power. We have to tune the tuner to optimize the power, and every time plasma formation processes take place. So it has a stabilization time which depend on the on time of the system. So as we see, for a 1 millisecond of 500 microsecond to 2 millisecond, if I increase the beam pulse, so it has a little ripple which is higher than the earlier case, it is 0.5. It has a higher rise time, 130 to 200, 290 microsecond. This rise time depend on the microwave power, gas pressure, impedance matching, and the magnetic field. So this is summary plot of the both pulsing the HV and pulsing the plasma. These are the rise time of fall time of this one case, and this is the rise time of fall time of pulsing the magnetron. So this is published in the Journal of Instrumentation. So this one is a better suited for the proton accelerators. Second is the beam emittance characterization. This is the emittance plot, basic definition of emittance. This is the Ellison scanner which I have developed to measure the emittance. So this is the deflector plate. This is the first slit, second slit, and applying a voltage sweep and measure the beam profile at that place. This is the relation between millirad and applied V plate. So this is the photograph of in-house developed Ellison scanner, first slit, deflector plate, and movable bellow to measure. And these are the parameters of the Ellison scanner. For 50 kV, 88 millirad is the design parameter of this one. So publication is there is a publication of for this one in INPAC. So this is the instrumentation control developed for Ellison scanner, and this is the layout of this one. So this is the measured emittance just after the ion source. It is a combination of all the species. So if you measure, so this is the low noise current. Low noise is also coming with. To overcome this, we take 90% of the peak and filter out it, and after you can measure the beam emittance. So this is the 0.32 for a 50 kV beam in 5 electrode ion. So these are beam size, beam divergence, and beam orientation. So the error analysis in the emittance, error is there in the position. Error is there in the measurement. So all the parameters listed: accuracy of measurement 5 micron, accuracy in voltage 0.076 volt, corresponding millirad is there, and error analysis because of finite slit, which is derivative from this one, and which come in the range of 6%. So 0.32 plus or minus 0.025 millirad. This is the experimental setup for measure the beam emittance just after the ion source. So ion source followed by DCCT to measure the current during the experiment, and followed by Ellison scanner. So system has been operated round the clock to give repetitive performance, beam current stable and repetitive beam. So emittance depend on the plasma density, temperature of ion and electron, extraction geometry gap, and plasma potential of the electrode. So experiment has been carried by varying microwave power, extractor geometry potentials, and plasma on time. So first case is the beam with respect to microwave power. So these are the emittance plot with respect to microwave: 600 watt, 800 watt, 1000 watt for beam current of 3.5 milliampere, 5.1 and 6.1. So as current is increasing, all the y-axis level are similar to observe the behavior of the ellipse. So as you can see, as increase the power, the red portion in the beam Ellison become dominant, and the beam emittance also improves. So this is because our density is increasing and temperature is decreasing. So ion temperature is also decreasing. So emittance is improving. So this is the emittance plot with respect to microwave power in 3 electrode, and this is the 5 electrode. So we can get a 0.32 in here and 0.43 in 3 electrode ion source. Similar with beam current plot, it is given for 4 to 20 milliampere and 2 to 12 milliampere in 5 electrode ion source. This is a summary of microwave power analysis. Second stage is the beam with extractor electrode potential. So as we increase the extractor potential from 20 kV to 50 kV, so we can see that emittance for 20 kV is in 32. 0.27 and 0.43, because system was designed for 50 kV, so all the parameters were that, but we are getting emittance of 0.43. This is because this is the emittance of a combined beam, H plus, H3 plus, H3 plus, which I also presented in a multi-species beam characterization in second day of INPAC. So this is a plot of beam emittance with respect to energy. So we get a dip at 30 kV and we are getting the 0.4 at 50 kV, and in 5 electrode we are getting lesser emittance because of polar electrode, and of 0.16 to 0.26 pi in the range. Current plot with respect to extractor is this is emission limited current, so we are not getting that current of higher in the depth. So this is the current plot, and this is a summary of the beam emission related to extractor. Third is the suppressor potential. So by varying the suppressor in 3 electrode ion source, we are getting the emittance improvement in 3 electrode ion source, because in 3 electrode we have plasma electrode and suppressor electrode. Combination of this is increasing the affect the beam emittance. So this has been observed in 3 electrode ion source, whereas in 5 electrode ion source suppressor is a 4th electrode and it has no effect on the beam emittance. So it has been observed in both the cases, and beam current there is no effect in the 5 electrode and slight effect in the 3 electrode ion source. The last one is the beam incident with a polar electrode. Polar is in 2nd electrode in 5 electrode ion source. It was designed for 40 kV, and it is matching with the experimental data. We are getting deep at 40 to 40 kV in 5 electrode ion source. So after doing all this experiment, this is one plasma on time. So as we increase the plasma on time, so plasma becomes stabilized at some time. So in this plot we can see that 2 humps are shown for a 5 millisecond, and we increase to 200 millisecond, it becomes single. So for a lower plasma on time, there is other processes are happening, because we are getting plasma getting stabilized after 10 millisecond, which we have observed, and impedance also improves. So this is a plot of beam emittance which improves with time, and beam current with increasing with the time. These are the this is the summary of the plot. Gas pressure for operating 1 to 1.2 minus 5 millibar, operating power greater than 1 kilowatt, beam times 50 millisecond, or to 20 or 50 is okay. Beam current in 50 kV 20 milliampere, 30 kV 19 milliampere. Beam emittance is 0.4, combined emittance for 50 kV, 0.27 combined emittance for 30 kV. Same way for 5 electrode, emittance is better 0.3 and 30 kV is 0.18. Proton fraction characterization. Proton fraction has been characterized with the help of bending magnet, and ion source contain 3 species, but also there is another species H2O plus there is a, which we have carried out with wind filter, which is done after this completion of this theory. So which has been measured with wind filter. So proton fraction depends on density and temperature and of electron, operating gas pressure, micro power, and plasma wall material. So these are the experimental setup of proton fraction measurement with the bending magnet. We have used a focusing solenoid of 1000 to focus the beam, and experiment has been carried out for 1000 Gauss. So this is the instrumentation control for the pulse beam operation of a bending magnet to measure the beam emittance or beam proton fraction. This is a beam waveform, forward power, reflected power, beam current, and trigger pulse. This is a SS chamber. So with SS we are getting 60% of proton fraction, 33% of H2. With to improve it, we had to add extra electron, which we have done by putting alumina and boron nitride in the plasma chamber and increase the proton fraction. So we have done this, and we got 80% of proton fraction, and at 800 watt, and for a higher power of 1.4, we got around 93% with a focusing solenoid. So this is the summary of a proton fraction measurement, and publication is there on this topic. And finally, I conclude that system has been characterization with plasma characterization with a Langmuir probe, and density and temperature has been investigated with micro power and other T on time. Beam pulsing topology, pulsing the extractor and pulsing the high plasma. And third is the beam emittance characterization. 5 electrode gives better emittance. And the last one is the proton fraction characterization, which study has been carried with alumina, boron nitride, and aluminum. And last one thing I want to future work is that use of permanent magnet, if study of single step ridge waveguide, use of solid state micro generator, and pulsing the high extractor HV with a higher voltage 30 kV and 50 kV, and one is space charge compensation, which I also presented in the second day. And I would like to thank my guide Dr. B. Dikshit, our committee member Dr. Archana Sharma, Gopi Kavanat Patankarsi, our external examiner, my mentor Roy Chaudhary sir, DS Patil sir, our colleague Garat. And these are my IRD colleagues, Rajesh Kumarji, our head, Krishna Gopalji, Rao sir, Singh sir, and mechanical team, and my family members. And one thing I want to show, last one, is the beam emittance. After focusing the beam, we get all the species separated, H plus, H2 plus, H3 plus, which was carried out after completing this one. So this is the difference between combined beam emittance and a single beam emittance.
You should conclude.
Okay, thank you.
Writing, sir.
Yeah, Dr. Hitesh.
Yes, sir.
So it was a ECR storm we faced.
Yes, sir.
79 slides. And you have too much to show, too many data. Very good. Now you tell me, you are using 2.45 gigahertz.
Yes, sir.
And for most of the proton sources, we find that.
Yes.
Why it is so?
Because so magnetrons are readily available and magnetic field requirement for the same will be lesser because of that.
No, but suppose I have in my lab a 6.4 gigahertz source.
Yes, sir.
So would you like to use that? And if you use that, what will change?
So it will increase the magnetic field and density will be affected because of the higher.
No, you tell me in terms of beam. See, I have given you the higher frequency source. I have given you higher magnetic field also. So in terms of extracted beam parameters, will something change?
About the 3 electrode geometry and 5 electrode geometry
Yes, sir.
presented the comparison.
Yes, sir.
So can you just briefly tell me, based on your exhaustive experience,
Hmm.
what is the comparison and what is the physics behind it? I mean,
So in 3 electrode, we have plasma electrode and suppressor electrode, suppress the backstreaming electrode. While in case of 5 electrode, we have added electrode like grid in the electron gun, which is used to control the divergence of the beam emitters. So that is give the better kind of fine tuning for the system, but it will give one disadvantage that vacuum in the plasma chamber is suctioned through these 5 apertures. So the vacuum load of the system is increasing. So and while applying the puller voltage, we are phase it gone to CC mode, power supply mode. So to control that, and we have to done very hard experiment trial, either by improving the vacuum, putting 2 turbo, finalizing system. So effect of puller is that we are controlling the beam impedance, but we are also observed that some leakage current is there, which is drawing to the puller electrode. So because of that, we get lesser current in 5 electrode compared to 3 electrode.
So
we are trying to improve that.
HIPAA, you'll be going for which one?
We have actually using as per today, we are going with the upgraded 3 electrode answers.
Okay, thank you.
Yeah, Hitesh, it was a very nice presentation, a very detailed presentation. So my question is, when you're doing the you have done 2 experiments, microwave pulsing
Yes, sir.
and the DC pulsing.
Yes, ma'am.
What you have observed regarding proton fraction in the
So
extraction?
in
What
proton
was the
fraction,
difference between the 2 and which one you will prefer?
so that is a good question. During the HV pulsing, my plasma parameter is stabilized. So in stabilized condition, if you extract the beam, the proton fraction will be better. While in pulsing the magnetron, my plasma and parameter are transient. So it has a lesser proton fraction.
Exactly. I was about to ask that when you pulse from microwave power, definitely your plasma parameters, because plasma quenches and again it starts,
So it will
then
take
it stabilizes. So whether when you're extracting the beam, it should be in the when the plasma is
stable
stabilized.
plasma. So that stabilization time, actually plasma formation time is around say few microsecond, 50 to 100 microsecond, but actual electron temperature and ion temperature stabilization time is less than 5 milliseconds.
Exactly. So yeah, my second question you already answered that plasma stabilizes in which condition? It is basically then it is a DC
Yes.
pulsing.
So that is a better option. DC plasma with a pulse HV.
But if this for the same question in 5 electrode assembly, which one you will prefer?
So you pulse the first 2 electrode, 50 kV and 40 kV, and we use DC register divider for 40 kV. That is the option for that one.
But when you do in the long term, keep on pulsing the electrodes, what is your estimation about the impurities introduced by the electrodes?
That experiment.
If you get it gets sputtered during the plasma.
Yes. So plasma and DC. So
over a period of time.
So that experiment we have not conducted yet, madam, because we have done one little bit on. We are presently working on a DC, so we don't have faced any problem sputtering as in the DC mode.
Okay, thank you.
Thank you for a very nice presentation. I just want to know, like you have used boron nitride and alumina to increase the proton fraction.
Yes, madam.
So how it has helped you to increase the proton fraction?
So earlier with we have studied with the alumina and aluminum and alumina. So alumina has a secondary electron coefficient 6 and boron nitride is in the range of 3. So we have put this and we have conditioned for the plasma. After conditioning, because of the secondary electron, which are energizing 3 equations in the chemistry, generating H2 plus 2H plus, first thing H2 plus 2H, which has a in the range of energy electron. So that dominate with this insulators. So that improves the proton fraction, but we have to change during the period of 6 months. That is the condition.
Okay, so very regular removal of
Yes.
okay. And one more question, like you have shown results for all species emittance measurement.
Yes, yes.
So for single species, how much it was and how you
For 50 kV it is 0.2 and for 30 kV is 0.13.
For
5
single
mm RMS normalized single species emitter.
for singles, how you have removed other species?
So there are 2 methods. One is I have to fit Gaussian in the Gaussian in this portion, and I have to subtract this Gaussian with mean and sigma. I have estimation this because this is not moving, and subtract this one. After filtering this, we will get the emitters. But if you remove this one and matching these 2 emitters, this will come nearly same. So that 2 method we have done.
So it is by simulation only.
No, I have experimental. These are the experimental data.
Experimental data. Okay. Thank you.
How accurate these data, like when you compare with the actual, how you have said this data is really your whatever you are looking for H plus. It is for H plus, not mixed with other these things.
So it is as per the theories design of a solenoid magnet. If you apply 1000 Gauss, your H plus will coming in the focusing zone. Okay. So it will move to second and fourth quadrant of the ellipse. So which we have theoretical data and we have practical data which are matching. That is theory is the base proof of this one.
Okay, so you are comparing with your theory.
Yes.
Okay.
Nice presentation. Just
thank you, sir.
You are suppose this for the pulse, you are pulsating the either plasma
Sir,
or the
your
voltage.
sound is not also.
Yeah. So either you are pulsating this voltage or the plasma, right now? So suppose I have to operate at 50 hertz,
Yes, sir.
like that,
Yes, sir.
or even higher. So in that case, which one you will be going?
If I have available 50 kV supply, I will go with that.
Not 50 kV, I'm asking 50 hertz.
50 hertz.
50 hertz with a very small pulse rate. So in that case, which one? you will
Pulsing
be
the
opting?
extractor is best suited always.
So it's always extractor is best suited
Yes.
compared to
Magnet.
Okay. In which case your pulse will be more clean.
Pulsing the extractor zone.
So pulsing the extractor, it will be more clean means energy is spared and then extraction and energy will be always better.
Yes.
Well, that's one thing. If it is so like that. For this separation of this H plus, H2 plus and H3 plus, you used SS403 304 chamber and then aluminum chamber. Right?
Alumina.
Alumina chamber also. So you have gone for two types of chamber?
Yes.
Why?
Because alumina has a alumina has a secondary electron coefficient of 6 and boron has a secondary electron coefficient 3. So when plasma has a electron which has a higher tail electron which are not confining because of the solenoid field, when it strike to the alumina, it will generate secondary electron. For one electron, it will generate 6 electron. So this 6 electron have energy range which are useful to convert H2 plus to H plus. And six procedures are there, 18 procedures are there. So out of 10, this which are converting H plus, like H2 molecule to H and H to H plus, H3 plus to H plus. There are 18 to 20 procedures which are dominating because of this. And these processes increase the proton fraction. So secondary electron coefficient is the main source.
Okay. Okay.
Yeah. Any more questions? Please, 1, 2.
While you are extracting the proton beam or H minus, S plus plus, your RF is flatly constant. So there is a droop in the current because your RF impedance matching condition changing that time.
In pulse, so in pulsing the microwave, you have seen the growth in the beam current. While
A very large number of slides, so it's difficult to search. You can maybe answer it, yes, without going to
I'll
the
show
slide.
just it is there. So this one is the pulsing the my plasma. So as plasma density is increasing, it is not stabilized. Because of that, you saw this ramp in the nature. While pulsing the extractor, you don't have this kind of ramp. So this shows that your plasma is stabilized.
Okay.
If there are no questions, I have one question. Yeah, you want to ask something? Yeah.
Secondary electron emissions. Use boron nitride. Can you use titanium nitride?
Yes.
Titanium nitride is having lower secondary electron yield in comparison to boron nitride.
Yes.
So why don't you have gone for titanium nitride?
I don't have available at that time. Thank you.
Okay.
This Langmuir probe measurements you have done, actually this is a very highly magnetized plasma, right?
Yes, sir.
So you have introduced it laterally.
Yes, sir.
Right? So actually, these all the parameters get split into parallel as well as perpendicular.
Yes, sir.
So how do you take that error into account here? Because it gives a very big difference in the TE and
So
PI.
basically, we use perpendicular to the magnet that care we have taken basically.
The parallel, if you put it, will give a totally different one.
No, so for parallel injection, we have to right angle the probe and from the extractor side and measure the
you have done that?
other. No, I have not done that.
Can most of the cases when the power is increased, the electron temperature actually should increase. In your graph, it shows electron temperature.
So
is
because
coming
my
down.
density is increasing and electron energy which was gained, it is
Actually, the
util.
power should give more energy. I think
Yes.
there is some problem in the measurement. Maybe.
Okay, thank you.
Okay,
Thank you.
it's a very nice talk. Thank you so
Thank
much. Next one is a presentation by Sumit Chaudhary on control methodologies of piezo actuator-based X-ray mirrors.
Okay, good afternoon, everyone. My name is Sumit. I completed my PhD from Homi Bhabha National Institute and work at RRCAT Indore. My PhD thesis title is Investigation on Safe Control Methodology of Piezo Actuator Based X-ray Deformable Mirror, its fabrication and characterization for adaptive optics. During this presentation, first I introduce the background and significance of the work, and next I come to gap area in the literature and objective of the work. Next, I discuss the safe control methodology, what is the limitation of existing method, how we remove or address that limitation. Next, I come to discuss fabrication and characterization of piezo-actuated X-ray deformable mirror. And next, we show the publication arises from the work. And last, I summarize my work. As we know, accelerated charged particle emit electromagnetic radiation if the charged particle moving at a relativistic speed and accelerate radially, then emitted electromagnetic radiation is known as synchrotron radiation. In synchrotron radiation, they have energy from infrared to hard X-ray. Among all these energy, X-ray are mostly used to characterize the material for various field of application. X-rays are focused. Some optics is not coming in this slide. Actually, previously I checked that is coming. Reflection based and diffraction based optics can be used to focus the X-rays, but the focusing property of refraction and diffraction based optics are wavelength dependent. Due to this reason, mirrors are mostly used in beam line to focus the X-ray beam. At beam line, aberration-free, adjustable size focal spot of high energy X-ray is required to accommodate different experimental geometry. Deformable mirror will satisfy this requirement. Deformable mirror can correct the wavefront distortion and provide the variable size beam at experimental station. Sorry for the glitch. Can you open the PDF because the PPT is not working properly? Actually, earlier I checked that is working, but some figures is not coming.
PDF open for me. Mine.
ठीक है ये चलेगा ओके Deformable mirror can correct the wavefront distortion for providing the aberration-free focus and provide the variable size beam at experimental station. And piezo actuator make a monolithic structure with the mirror substrate and provide the accuracy in sub-nanometer region. So piezo actuated deformable mirror be selected and explore the literature regarding the piezo actuated X-ray deformable mirror, and we found out some gap area like a systematic model and methodology for shape control optimization to achieve the target profile of deformable mirror are not available. Furthermore, necessary information on design, fabrication process, and associated challenges for the development of deformable mirror are not present in the literature. In addition, nonlinear behavior of piezoelectric actuator at high electric field and its implementation on real-world problem is not well explored in the literature. So our objective is develop a model and methodology for analyzing the performance and correction capability of piezo-actuated X-ray deformable mirror at design stage and achieve the target aspheric or arbitrary shape in real world condition. And our second objective is design and develop a piezo-actuated X-ray deformable mirror for focusing the synchrotron radiation at experimental station of Indus 2 synchrotron radiation source. I come to my first objective. People are using singular value decomposition method to optimize the electrode potential. But this method has several limitations. If I talking about the limitation, it cannot apply the constraint. So most of the time, the computed electrode potential is practically not feasible for the real system. So we proposed alternative approach that is called piezo response function based optimization. In this, we used response of piezo actuator and optimize the either between target shape and achieve shape by using optimization technique in a deformable mirror. To achieve the aspheric shape and arbitrary shape, you need number of piezo actuators. So number of piezo actuators shift your problem for unimodel to multimodel. So you need a global optimization technique. So we tested commonly used global optimization technique to optimize the 28 electrode, and we found that simulated annealing gives better convergence for shape control problem. In addition, the deformable mirror has thickness like a 5 to 8 mm. So you need a high electric field to bend that substrate. So second, we have analyzed the response of piezoceramic actuator under high electric field. Our experimental, analytical, and numerical study shows that at high electric field, you must consider the nonlinearity of the piezoelectric actuator. If you are not considered, then you cannot achieve the shape control in some nanometer laser. So in addition, the supplier or piezoelectric manufacturer will not give you the nonlinear coefficient. So the problem is also a problem. In literature, you have not any standard technique to calculate the nonlinear coefficient. So to address this problem, we proposed the iterative piezo response function based optimization. In this optimization, we compensate the error due to nonlinear behavior of piezo actuator in iterative manner. Second thing, if you are talking about the sub-nanometer accuracy in shape control, so all the things you need to consider in your analysis, for example, deviation in epoxy strength, diversity of electrode or actuator size, exact mounting condition. If you do the numerical analysis like FEM and calculate the voltage, then you cannot reach up to sub-nanometer level. So we introduced data-driven optimization, in which we experimentally measure the piezo response function and used in optimization to achieve the sub-nanometer accuracy. This is the idea. So first we did the theoretical analysis to verify our idea. We take a cantilever piezoelectric UNIMAP having different number of actuators, and we perform a theoretical study. And in theoretical study, this shows that IPRF based optimization it compensates the nonlinear behavior iteratively. This is the theoretical analysis. So next we verified it experimentally. By experimental verification, we used piezoelectric unimap-based silicon mirror and test it using confocal displacement sensor. And this is also shows with the number of iteration we achieve the target shape. After developing the understanding of shape control methodology, we go for the fabrication of piezo-actuated X-ray deformable mirror. We polish the zero dust substrate using chemical mechanical polishing and do the gold coating on mirror substrate to increase the incident angle. We do the photolithography to pattern the 9 electrode on the piezo actuator and bond it with the mirror substrate, and we design the mounting condition for ex situ and in situ characterization of PXDM. For ex situ characterization, we use long trace profiler, and for in situ characterization, we used BL12 ADXRD beamline. This is the optical layout of BL12 ADXRD beamline. And we plan to test our mirror using this configuration. We mount our mirror on experimental station and set the detector at 1 meter away from the experimental station. And we focus the beam far from away from the detector and refocus the beam using our developed fabricated PXDM at the detector. This is the for focusing, you need the parabolic shape mirror. This is the equation for the parabolic shape mirror. In this equation, you require incident angle and image distance. If we keep the image distance 1 meter and incident angle alpha is 3 millirad, then this is the parabolic profile which we need to generate for the focusing of X-rays. So first we measure the piezo response function of all 9 electrode and make a optimization problem. So to achieve this parabolic profile, we do the IPR based optimization. If we can see, with the number of iteration, the root mean square error is decreasing, and we can achieve the target shape with the root mean square error of 42 nanometer. After fourth iteration, it will start increasing. So we take the optimization for voltage for the experiment. Next, we after finding out the optimum voltage, we go on beam line. We mount our mirror on experimental station, and first we are not align the mirror in the beam path and measure the beam size. And the red dot shows the measured data, and the green line shows the fitting curve. So after fitting, we find out the beam size, that is FWHM is 235 micrometer. And also we model the using the beamline parameter. We do the ray tracing and we calculate the beam size of the at the detector. That is shown by the red line, and it can be seen both are matching very well. Next, we align the mirror in the beam path and set the incident angle and apply the optimum voltage. After applying the voltage, it focus the X-ray beam into of size FWHM at 83 nanometer. Same things we perform on the ray tracing, and the ray tracing result is matching well with well with our experimental result. Here we focus the X-ray beam in vertical direction, but we can use it for horizontal direction also. So in future, we can propose a KB mirror to focus the beam in both the direction in sub-micron level. We publish our finding in 6 peer-reviewed journal, in which 3 in smart material and structure, 1 in mechanics of advanced material and structure, 1 in simulation, and 1 is nuclear instrument and method in physics research. We published our finding in 2 international conferences, and in this work, we developed a new methodology. This research introduced novel shape control methodology for adaptive optics in synchrotron radiation beamline. We proposed iterative piezo response function-based optimization method developed to achieve the target profile using nonlinear piezoelectric actuator without prior knowledge of higher order coefficient of piezo actuator. And also we develop a product and prototype piezo actuator based X-ray deformable mirror successfully developed for synchrotron beamline application. We fabricated PXDM, focused the high valence SR at vertical direction from FWHM 235 micrometer to 83 micrometer. And thank you. This is the acknowledgement. I acknowledge. I will thank to my guide Dr. Rahul Shukla and also doctoral committee and many persons who helped to make the successful of this work. And thank you for your attention.
Thank you, Sumit. Thank you, Sumit. I think the viewers can ask questions.
Dr. Sumit, nice presentation and very important work, no doubt about it. So this test, whatever results you showed, it is in the actual Indus beamline or?
Actual Indus beamline, sir. We tested at BL12 ADXRD beamline. This is experimentally tested, and we also compare our result with the ray tracing. We perform the ray tracing using the AUI software, and we compare the experimental result with our experiment with the ray tracing result. Red line is our ray tracing result calculated from the ray tracing, and this is the actual measurement. Dot is the measurement, and we fitted with the green line to compare the result. This is the fitting. Green line is fitting the experimental data, and red one is the calculated data from the ray tracing.
Okay.
Very interesting and useful work. Can you go to your slide where you saw about the piezo response functions? I think 17, 18, something like that. Yeah, this one. So this one, these curves, these are measured or these are simulated?
No, sir. This is measured. We used a long trace profiler to measure this curve.
So you give some input to each of the piezo.
Yes,
like
sir.
Pair of 1 to pair of 9.
Yes, sir. Yes, sir. We apply 400 volt and measure the profile. After that, we calculate for unit volt. We divide by the 400.
So this is for a unit volt.
Yes, sir. This is not unit volt. This is at 400 volt.
400 volt.
Yes, sir.
But then you also talked about that the novel thing in your work was that the non-linearity was not studied earlier. So
Yes,
this
sir.
is linear, no?
No.
I mean, where is the information about the non-linearity here in terms of the electric field or the voltage?
Actually, if you apply in actual system, if you apply the voltage, like if you apply the 10 volt, what is the profile, and you calculate the PRF, and you apply the 300 volt, and you calculate the PRF, both are not same.
So you generate this curve for different voltages?
No, sir. We measured at 400 volt and do the iterative thing to compensate the nonlinearity to achieve the target shape. Like if you apply, you calculate from 400 volt to generate the PRF.
Okay, fine.
Okay.
So, I mean, that nonlinearity is taken care of by iterative
approach.
Okay. You could have even studied it and found out the nonlinearity, taken this data for different voltages.
Yes,
and
sir.
then you have a lookup table kind of thing for the related to the nonlinearity, and you could have
Actually, for mirror, we are not compare with the theoretical and experimental result, but we make a different piezoelectric unimap and studied. This is the piezoelectric unimap. We make different size and different with the different substrate, and we found that this is the nonlinear things, and we tested if this is the linear. And we see the deviation. Deviation is this. With the increase of voltage, the deviation is higher. If you go more higher voltage, then it is more deviation from the linear one.
Okay, thank you.
Nice presentation.
Thank
I
you.
don't have any question.
Nice presentation, Sumit. I just want to ask whether the position of your piezo actuator is important in the beamline, where you are going to locate it, and what is the size of your piezo, this mirror?
You actually, I am not get exactly question. For you want to know the size of piezo, or you want to know the size of mirror?
Mirror.
Mirror. Actually, here this mirror size is 100 mm. Total length is 150 mm, but we use piezo of 100 mm. So we take the active area 100 mm and we perform the experiment with the 100 mm. We restrict the beam size to fall it on 100 mm using the slits. So in further, if you want to use KB mirror, so the benefit of the KB mirror, they focus very short image distance. So you cannot use very long mirror. So we are targeting 100 mm and 150 mm size of mirror.
Okay.
So that will used for in KB mirror to focus both horizontal and vertical direction.
And one more thing, that parabolic profile that you got, and you expected that it has to be a parabola, right?
Yes, sir. Yes, ma'am. You can same methodology you can use for elliptical mirror to generate the elliptical shape or any arbitrary shape. And now because we are not disturbing all the optics, so the requirement here for the parabolic shape, so we generate the parabolic shape. Same way we can generate elliptical shape or whatever shape is required for the, if we go for the aberration correction, whatever the shape are required, we can generate. Okay.
Excellent work. I just want to know, you have discretized your piezo, right? You have done many 28 numbers of the piezo you have used. Earlier slide, yeah. Yes, somewhere.
Yes, sir, this one.
Okay. Now, how did you optimize these numbers?
Actually, this is the theoretical study to get which optimization method is best suited for our shape control problem. So we use a 28 actuator. In practical case, we are not going to 28 actuator. If our optimization method is capable to handle a large number of actuator, so it will also handle the lesser number of actuator. So our plan to make a electrode a maximum up to 15 or 18. Generally, people are also using not more than 18 or 20 electrodes. So you need 20 independent power supply. So practically it is used in like 18 electrode. But for the method checking or for the development, we go for the 28 electrode. If our method is capable to handle large things, so it also capable to.
So it is possible.
Yes, possible for lower electrode also.
Sumit, very good presentation. Just I want to know, well, you are using this piezo deformable mirror.
Yes, sir.
Suppose I made this, I am getting the exactly parabolic shape initially and characterize and got the response of all piezoelectric. With the time, suppose 3 year, 4 year working in the synchrotron beamline, whether the calculation or whatever you have characterized will change or it will remain same?
In piezoelectric, little decay, but like but it can go up to 3 and 4 years. After 3 and 4 years, you need to recalibrate and you can use.
Okay, so recalibration will be.
Recalibration is required after like 3 or 4 years, but it will work continuously in up to 3 and 4 years.
Okay, thank you.
Any more questions? Yes, Mike.
Have you studied the effect of power supply stability? Because you are feeding this piezo with some power source, isn't it?
Yes, sir.
So their stability will also have effect on your profile, finally. So have you studied that part?
No, sir, that part I have not studied, but whatever supply we are using, that have instability is we are not studying.
Because it will be for a long time, no? That so
Yes,
long-term stability of the power supply will also matter.
So now we are for our experiment, we are not using long time. So we used not consider that point. But if we are using in the beamline for that thing, then we need to study. This is the first study we have performed. So in that study we are not include all the things.
Okay.
So for simplicity, we optimize these things. Okay.
You have used 28 segments for controlling. So I think that calculation time of the optimization program will take some time. You have not talked about how much it takes time to calculate per 28 segments.
Okay, if we use simulated handling, and for a 28 actuator, we use 28 actuator, then it will take approximately half an hour.
Half an hour.
In MATLAB, we are using MATLAB to optimize. That takes half an hour. If the number of actuator is less, then so we can reduce the number of iteration, so we can reduce the number of time also.
Okay, thank you.
Thank you.
Hello, sir.
There's one question. Have you checked the effect of initial beam parameters, that is from the dipole source you are taking the beam, photon beam? Is there an impact of the initial horizontal and vertical beam sizes on your focusing what you are achieving 83 micrometer? Is there a chance to really further improve the beam quality from the storage ring, or you can go further down in the beam size at the experimental station instead of 83, let us 40 micron?
Okay. Beam size parameter for the experiment, if that is not be included in this experiment, what is the uncertainty in the beam parameter, that is not included. If we can do, if we measure the real time beam size or beam wavefront distortion, that we can correct to reduce the focus size. Because that instability give you in the focus. If because you set the profile, if beam instability or anything that include in aberration, that will increase your focus size. If you want to measure, you change the profile of the of deformable mirror, then you can get the best focal size.
Okay, I just have one last question. Everybody is hungry. These piezo elements are known to have hysteresis, but have you studied
Hysteresis,
that?
yes, sir.
We did not see any hysteresis measure.
Actually, if you see, we using iterative iterative tuning. So we give sufficient time to rectify the hysteresis, because in one measurement between successive measurement, we give sufficient time to nullify the hysteresis, because we generate one profile and we are not changing constitutively to different profile. So once you compensate the hysteresis and generate that profile, then it will be stable.
Do you also give a negative volt?
Huh?
Do you also give negative volt, or only you end up at 0 volts when you want to bring it back? Because you have to compensate for hysteresis, right?
No, if you left for some time, then it compensate the hysteresis. If you need to wait sufficient time to compensate the hysteresis, because in one measurement to two measurement, we give approximately like a 40 minute or 1 hour time to compensate the hysteresis. And we are also tested that things in LTP. We give first we measure the profile and we apply the voltage. And after 40 and 50 minutes, we also measure the profile at without voltage. If these are same, then we go for the next.
Okay, okay. Thank you so much. It's a nice talk with a lot of publications. Thank you so much.
Okay.
And I thank all the speakers of today's the current session. Thank you so much.
Now we are at the end of the session. I would like to thank on behalf of the organizing committee, thank the session chair, Professor Nabiraj. Now I request Dr. Akhilesh Jain, head solid state RF amplifier section, to present a memento to the section chair as our level of action. Thank you, sir. Now there is an announcement. We will gather here again on 12:15 for the parallel session. Sorry, 14:15 for next parallel sessions in 3 halls. Thank you.
Hello, hello.
Hello.
Good afternoon, all the participants and guests. I welcome you to the last technical session of INPAC 2025. We have with us Shri Prashant Khare sir, OS and Head CDCA Division RRCAT. I am honored to invite him to chair this session. Shri Prashant Khare sir has contributed significantly in the design and development of cryomodule for SCRF cavity and bringing refrigerated technology in the form of Shivai for transport of perishable items. He holds 6 patents for his work and has received several prestigious awards, including Homi Bhabha Science and Technology Award 2018. I request Shri Prashant Khare sir for further proceeding of this session. Thank you.
Good afternoon. Now we come to the last session of last technical session for INPAC 2025, and we have 4 lectures on very interesting topics. First is for plasma processing technique by Shri Vikas Jain, then status of superconducting cyclotron at VECC by Mr. Atanu Datta, then development of indigenous 4K class cryocooler by Shri Rajveer Singh Duhan, and fabrication of superconducting niobium resonators at IUAC by Shri Kishore Mistry. But this last talk, I will like to prepone as the second one, just after Shri Vikas Jain. So I welcome Dr. Vikas Jain to come. Vikas ji, your time is 15 minutes, but I will request you to finish it off earlier because we are already running late. I'll inform you after 12 minutes. Thank you.
Thank you, Khare sir. The presentation of my is on development of plasma processing technique for SCR, superconducting cavities at RRCAT. So what we have done, we have independently developed this technique of processing the cavity through plasma. The main hello. So I thank Suresh and Kuldeep to prepare these slides. So how I have planned this is I just give the principle, then what are the plasma generation techniques, experimental setup, and rush through different results and these things. So as you know that superconducting cavities are nowadays essential part of modern particle accelerators for efficient charge acceleration. So this is a for any new accelerator, people think on these, especially if you want to go for high duty cycle, you cannot avoid superconducting cavities. However, now mostly people are using it on these cavities. How the cavity is made up of niobium generally. Right now, niobium is the only material where its TC is 9.2 Kelvin, and because of that, we are using it for all our accelerator program. In future, if some other material like NB3SN and this evolve, but still for high duty, this niobium cannot be replaced at present. The main issue comes from the surface chemistry. If the surface chemistry of any surface
a superconducting surface, if it is not good, it is going to give some trouble. For example, if it is a superconducting niobium cavity, it is you cannot weld it at room temperature, means by TIG welding or some other method at room temperature. I mean, not room temperature, at room temperature, the normal conditions, because oxidation is big issue. So you have to do either with some inert gas environment, unlike we see today morning by laser welding or electron beam welding. Now, doing that, whatever cleanliness you do, if there are certain residue of carbon or some other hydrocarbons left over the surface during the processing fabrication, then it is going to create the trouble. So you have to remove that. So to remove that, if you there are certain methods which we have already developed at RRCAT, like processing. You have to do the bulk processing of the cavity by removing the damage layer by using some chemical like HF and HNO, this EP process that is called electropolis process, and we already had few papers on these deliberations. So I'm not going into detail, but why if those can do the work, then why this is required? This is specifically required for giving the field emission, because field emission comes even if the vacuum breaks, and during the, even you do in clean room, and some particle gets contaminated and it is sitting over the surface, it is going to create trouble, and it is going to do the field emission and other problems. So what we have done, we have used the RF-based RF-based system, where we use noble gases like neon and argon to remove this impurity. How it works, I'll just give a quick glimpse on that. So see, at room temperature, and especially this technique, why I'm saying, especially this technique is very useful if you have already installed your system into the accelerator. And if it is there in accelerator, you cannot remove it and use it. So this technique originally generated by ORNL, when they face a problem of their LINAC that is getting contaminated, and a lot of field emission coming out of that. So what they decided, that can we do in situ processing? So to do that in situ processing, they evolved this process, plasma processing. However, they have done with some other method. We are doing with some other methods, and like that, they removed it, and they find that they have improved its performance. The basic thing here is, if your cavity is contaminated like this, the whole of the surface is contaminated, and then you start cleaning with the plasma, and once the plasma react with the whatever residue over the surface, it emits the gases, and those gases one has to pump out. That is the basic methodology for doing the plasma processing. So I'm not going into detail how plasma processing works, how it does the chemical reaction and other things, because that will take a lot of time. So I'll directly jump on to what we have done here. So you, for example, if there are some hydrocarbon impurity, CXH, and the cleaning is done through oxygen. It doesn't mean that we have oxygen. Oxygen is very in fraction of percentage oxygen is there, and that reacts, but you create either neon or argon plasma, or you can create some other plasma also. But there are certain disadvantage using both neon or argon, because argon being heavy, it has certain advantage, but also neon is close to oxygen. So we have seen various results that sometimes this neon is working better, sometimes argon is working better. Still people are searching the exact answer. So this is the open area for research for at least. So this is the chemical reaction which will happen And then how you know, you use RGA and other things to check whether it, what are the components coming out. And we have checked also that once we start the plasma, earlier there is nothing is coming except the argon, which was argon peak. But then we saw the H2O and CO and CO2, every component comes. So we have to intentionally, what we did some samples and we contaminated those samples, generated the plasma, and we find out the result. I'll just show some of them. So you can use either of these techniques. The radio frequency plasmas are very much useful for the cavity. So you have to generate a TM010 frequency plasma, means you have to give that frequency, resonating frequency. So what it will do, basically it will establish an electric field across the cavity. And then we can do the plasma cleaning there. So what we have done both the things together. So earlier we started with the very high 10% of oxygen. We thought, okay, this should work. It was working well, but then we find that this technique doesn't work on cavity. It was good for sample. Then we have changed our methodology. However, you can see that with the neon plasma, the color, and with the argon plasma, the color comes because of its frequency, frequency of atoms at that temperature. So, and now what we did, we have made some 10 by 10 by 1 mm thick samples, which were placed at equator, iris, and for iris, means on the beam tube. Various samples were kept, and you can see that these were just, we have put this hydrocarbon, the ink, and then that ink is put, and these were placed at various places. So you can see after 10 hours, the result after 10 hours, few samples at iris, those got very much clean, but there were the samples which are very far away. So the plasma is not propagating everywhere, but we are interested on high field region only. So at high field region, yes, this result was very useful. Then we extended this single cell cavity approach to multi-cell cavity approach.
Vikasji, 3 minutes left.
Yes, sure. So for multi-cell cavity, it is, we have to use the different setup. This is the schematic of the setup. You can see the setup there. Now only important thing, thanks to our RF group, they have really worked hard and find out which frequency combination they have to use to get rid, glow the plasma in particular cell, and they moved on all over the cells. So they have, so you can see they have used some different type of frequencies, like TM010, it has 5 modes, like 1 by 5, pi 2 by 5, pi, and up to pi mode. So these 5 modes, there were some combinations were made, and then they find at this the primarily the plasma glown into that cell number 1, 2, 3. So there were different frequency sets. So a lot of work was done, and in last InPAC, Praveen has presented how to manipulate the frequency for different cells. And then we find out that you can see this 18 number is H2O, and then 28, it was not known actually earlier that we were when we were using this 28 was coming very high, but then we discovered that the gas we are using, it has a lot of contaminated oxygen, nitrogen. So we removed that and we used the 6N argon, and that point of time we could get this much this figure from RGA. And then one of the cavity we have tested, and you can see that it was improved like this. The gradient earlier coming was 8.5 because of some reason, and then it went up to 14, and then power which was taken by cavity is 180, watt, and then it is only 13. And the Q also improved. And the radiation, this is what we are looking for. The radiation significantly reduced, which is the mainly effect of plasma processing. So this 5-cell cavity has really worked, and we are further working on how to optimize this. So I'm in the concluding slide, sir. This is the critical importance of surface quality. The performance of superconducting cavity, vital for particle accelerator, is highly dependent on the quality of inner surface, impurities, imperfection, which lead to energy losses and reduces the accelerating gradient. Basically, work function improved. This is what we have done. We have also checked the work function of samples on INDORE's BL3 beamline, and we saw there was a significant improvement in the work function of those samples. The plasma processing technique development is very good. We can use either of the gas, neon or argon. Then systematic optimization and testing. So this is going on, improving the cavity performance. So we are now planning to go for some other cavities also. Because as many cavities as we do, we can do a lot of experiment, and then we say, because every performance will be known at 2K only. So that is why it's taking time. And this can become a potentially chemical-free process. There are some work going on at Jefferson Lab. They are trying to get rid of this the chemical cleaning and just doing with the plasma cleaning, but they are still very at early stage. But that if that works out, then this technique will become really chemical-free technique for the superconducting cavities. Thank you, sir.
Thank you, Dr. Vikas, completing well in time. And I think we have time for it. 1 or 2 questions maximum. Let's.
Vikas, great work done. If the geometry of the cavity is changed, then what are the optimization you have to do in the setup for other geometries?
Geometry of different cavities.
Yeah.
Yeah. It is possible, and people have tried with the SSR cavities also. And the only thing, they have to change the RF frequency there, because here we are using the combination of frequency to generate that plasma. So there also that optimization need to be done. And like here also, I have not told about that we have also worked on the antenna length, antenna diameter, and other things. So we have to optimize that.
It has to be all different setup.
Yeah, it has to be all different setup.
Can you give it to Pansa?
When you show a combination of modes, that means you launch multiple frequencies.
Yeah.
But when you said initially that this is good for dressed cavities, so will the coupler take different frequencies?
Yeah, it will. Because what you have to do, you have to basically sweep between with certain time.
Will the coupler launch with equal efficiency?
Yeah.
Coupler will be optimized
I think
for certain beta.
they have done, like Praveen has a combination of like pi by 5 mode and then some other mode.
यहाँ तो आपकी open cavity थी.
हाँ, यहाँ open, okay.
But you said it is good for dressed cavities.
Dressed cavities also they have.
Where you cannot open. So वहाँ can you use such combinations?
It should be possible using the other port also, because they have another port for that is field probe port. So there you can use, they can use another coupler for making this.
Okay, I think please we'll leave it for a tea session. Thank you, Dr. Vikas. Thanks, Dr. Vikas. And now I'll request Mr. Mistry. He'll be speaking about the work being done at IUAC for fabrication of superconducting niobium resonators. Of course, these are QWR and not high beta elliptical things. Mr. Sab will be giving you 12 minutes initially. Then I'll tell you that you have only 3 minutes left. Thank you.
Good afternoon to all of you. I am presenting on behalf of my group members, and the topic is fabrication of superconducting niobium resonators at IUAC. My plan of presentation: SRF infrastructure at IUAC, outcome from the IUAC SRF facilities, recent completion of the construction of 6 spare QWRs and 14 niobium tuners, then development of low beta 650 MHz 5-cell niobium cavities, and then I will conclude. The SRF infrastructure at IUAC was commissioned more than 2 decades ago. It consists of an electron beam welding facility, a surface preparation laboratory, a high vacuum furnace, and in addition, a test crash for offline testing of the quarter wave resonators at 4K. As I have mentioned that this facility was commissioned more than 2 decades ago. Since its inception, it produced a variety of cavities over a wide range of velocities, both for our in-house project as well as for the national and international collaborations. It includes 1.5 dozens of quarter wave resonators along with their niobium slow tuners. They have successfully completed, and after successful completion, all of them have been installed in the IUAC beamline to complete the second and third cryo module. And since then, all these resonators are successfully delivering beam to the users for the nuclear physics experiments. Then design and development of prototype niobium low beta QWR, and it has been tested successfully, and it has achieved the design, it has exceeded the design gradient. Then construction of 2 bare niobium SSR1 single spoke resonators for Fermilab USA, and in cold test at 2K, both the resonators exceeded the PIP2 design goal, and after dressing up, one of them installed in the PIP2 injector facility. Then 4 1.3 GHz Tesla type niobium single cell cavities and a 5-cell cavity have been developed, and a 650 MHz single cell cavity also developed in collaboration with RRCAT INDORE. Another 2 650 MHz niobium single cell cavity. This is low beta cavity in collaboration with VECC Kolkata. So all these cavities I have qualified the cold test after standard surface processing exceeding their nominal design goals. Thus, it validates the fabrication procedure, especially the electron beam welding technique followed by the IUAC group members. Now, I will talk about some recent developments. Recently, 6 QWRs along with 14 niobium slow tuners as spares for IUAC superconducting LINAC have been successfully completed. Though the earlier built cavities, they are performing well. Still, for these spare cavities, we strive for further improvement in the fabrication process and electron beam welding to achieve even further better performance on it. So these are the 6 cavities, and these are the slow tuners for them. Now I will discuss some critical welding, critical joints for these cavities, QWR. This photograph shows the assembly of a coupling port to the niobium cylindrical outer housing. So this is a saddle shaped joint. So due to that, at the time of electron beam welding, always there is a change in the gun to work distance between the heel and the valley of the joint. Again, there is a thickness difference also in the hill and the valley, and the weld length is changing here when the beam travels from the hill towards the valley, because this cylinder, a hole has been drilled to the cylinder to fit this coupling port into it. So when you see the joint from the top at the time of electron beam welding, it looks like a circle, but this is not a circle. This is actually an ellipse. If we unfold the cylinder after drilling a hole, the joint will be an ellipse. So therefore, the beam when travels from this hill towards the valley, it is actually traveling a larger distance in a set duration of time. So therefore, during electron beam welding, all these things had to be keep in mind. And another critical joint is the closure welding joint. This is critical because this joint is in the high magnetic field region, and a solid 16 millimeter thick niobium flange is attached here to the 3.2 millimeter thick niobium outer housing. So there is a huge thickness difference, and also there is a difference in the thermal mass also. So at the time of fabricating our earlier cavities, some of the cavities we got blow-throughs during this welding. So therefore, during this fabrication of these spare cube rollers, we have taken care during this welding, and we have developed our weld process and parameter to overcome all these problems. So finally, we have completed all this welding successfully without a single blow through. So as you know that the fixing the blow through in the niobium cavity is really a very painful task. Now the fabrication of LV650 5-cell cavities. After successful development of two single cell niobium cavities in collaboration with VCC Kolkata, the fabrication of 5-cell cavity was initiated. Our aim is to develop two 5-cell low beta cavities. In this project, VCC is fabricating all the toolings and fixtures required for the machining and the forming work, and they are also doing the machining and forming of this of all the niobium components. IUSC is sharing its expertise in all this above work. In addition, extending its superconducting resonator fabrication facility infrastructure for this fabrication. These are the joints we have successfully completed for LV650 cavities. Now I will explain a few of them. This is the iris welding. This welding have been completed from both sides, inside as well as outside. And for this welding, the fixturing plays a very important role, because at the time of welding, we have to optimize the clamping pressure of the fixture. If the pressure is too high, it will give excess weld shrinkage. And also, the diameter of the fixture also has to be optimized. Actually, the diameter of the fixture should be slightly larger than the iris diameter. If the diameter is more, then during welding, it will simply bend both the half cells, and this gap will be reduced. So later stage, inserting a stiffener ring through this gap will be difficult. So after successful development, these are the actual components. The stiffener ring have been, sorry, I'm sorry. This is another critical development, parameter development for the stiffener ring welding to the niobium half cells. Actually, due to the shortage of material, the actual simulation could not be done on the dummy samples. Therefore, we have done the parameter development on small samples only, but you can see the profile of this sample is similar to the half cells. Okay, and a small piece of stiffener ring was attached to it, and after welding, this sample was cut and mechanically polished and chemically etched to see the actual depth of penetration, and the radiography test also carried out to see the quality of the weld, and finally this joint was machined to actually visually inspect the depth of penetration. After successful development, this is the stiffener ring have been attached to both the hub cells, and as I said that the gap is very less here, it is around 20 to 22 millimeter. Therefore, the desired tilt could not be possible to access the fillet joint corner. This is further critical joint because one side of this stiffener ring, niobium stiffener ring, is attached to the niobium hub cell, and the other side is niobium titanium spool. So it's a dissimilar metal weld, therefore it is further difficult. Another critical joint, field probe. Actually, the part is very small. The diameter of the joint is only 30 millimeter. So if you calculate the total weld length, means pi d will be around 95 millimeter. So it is very difficult to decide where to ramp up the current and the for linear weld also, and the ramp and the overlap region also, and then again ramp down. So it's like the weld finished before it starts. So here you can see the beautiful underbead has been produced here on the RF side. This is another difficult part because they are dissimilar material. This is niobium titanium flange attached to the niobium beam pipe. This is difficult because both the material are different. Their properties also different. They are having different melting point, thermal conductivity, specific heat. So, and sometimes if the gap between these joints are slightly more, then the electron beam will simply round off both the edges instead of joining them. So this welding also we have successfully completed. Now this is the most critical joint, the equator joint. Again, this is in the high magnetic field region, and this is also a blind joint. And after successful parameter development on dummy hub cells, dummy equator, sorry, the actual 2 equator joint we have completed successfully so far. Though the weld result is good, still we are trying to trying for the further improvement of the weld joint.
Kishorji, 3 minutes.
Okay, sir. Now I will talk some problem, that is the non-availability of niobium material, or you can say the limited availability of niobium material. Actually, this is a part in the beam port, in the beam pipe. This is very small part. Actually, this is simply a 4 millimeter, a beam pipe of 4 millimeter wall thickness. On top of that, another 4 millimeter step is there. So to fabricate this part, we need a beam pipe of 8 millimeter wall thickness. So that material we did not have. So therefore, with the available material, that is 4 millimeter wall thickness beam pipe, we took, and a niobium ring of another 4 millimeter was machined, and that was attached to the beam pipe by electron beam welding from both sides, and then the niobium titanium spool was attached over this. Another example of limited availability of material, niobium material. This is a field probe. To fabricate this field probe, a niobium solid bar stock of 30 millimeter diameter is required. That material also we did not have. Therefore, the available size, that is 17 millimeter outer diameter bar stock, we have machined, and it was machined to a pipe, and at one end of that pipe, a circular niobium plate of 4 millimeter thickness was electron beam welded from both sides, and then this plate was formed to a saddle shape, and then the OD was machined to desired size. So that way we have successfully completed the field probe. Only difference was there was an additional electron beam welding here, which was not there in the actual drawing. In the meantime, we have received 2 actual beam port, machined beam port from RRCAT. So we have finally used those 2 beam ports to the actual cavity. And you can see in this picture, these 2 are received from RRCAT, and this is our field probe. This is the present status of the low beta 650 megahertz 5-cell cavity. These assembly are complete. These 2 equator joints have been successfully completed. Both the end walls, both the end groups are ready. Now the question is, what work remains to complete the first LB 655 cell cavity? These 3 equator welding we have to complete. In addition, this niobium titanium flange have to be attached to the coupling port. So these weldings are remaining. So hopefully in another 1 month, we will be able to complete the first 650 megahertz low beta 5-cell cavities. Now I will conclude. The SRF infrastructure at IUSC was set up more than 2 decades ago. It is the first such cavity to be established in the country. The facility has been used to develop and build different types of superconducting niobium cavities over a wide range of velocities. The facility has produced niobium cavities for both in-house project as well as for the national and international collaborations. Recently, construction of 6 spare QWRs for the IUSC superconducting LINAC has been completed, and construction of 2 5-cell 650 megahertz low beta cavities in advanced stage. One of them is nearing completion. These are the group members, and I would like to mention that Dr. P.N. Prakash, though he is retired now, but always always he is there to help us. Whenever any problem is there, he is always ready to help us. And finally, I would like to thank IUC director for continuously giving support and encourage us. Thank you.
Thank you, Mr. San. Now that we don't have time, I would request that the questions are taken outside the hall if he has time. So thank you very much. Manish, we will come later. Okay.
Okay, thank you very much.
Please. Thank you for a very nice talk.
Thank you, sir. Thank you very much.
Now I request Dr. Rajveer Singh Duhan to come for this cryo-cooler talk.
एंटर का है ठीक है इसके लिए ये लगाएंगे ठीक
सभी को मेरा नमस्कार. I'm R.S. Duhan, Dr. R.S. Duhan. This is about 4K class cryocooler. So as the title suggests, is indigenous, is 4K, and is cryogen free. Maybe you have also seen that in the recent time, the demand for the cryogen free application is growing. this cryogen-free operation offer reduced costs and the greater accessibility. It's like your domestic refrigerator. You don't need to be expert in the cryogenics to operate the cryo cooler. It simplify ease of use, and as you see in in this presentation, we call it single stage and double stage. So what it mean when we say single stage and double stage? In case of double stage, this is double stage cryocooler. I have deliberately made this visible. This is first stage, this one, and this is the second stage, and this is called the cold finger. When we say the class, the temperature, the minimum temperature what you are getting here is the that one. So in case of 4K cryocooler, you will get the 4K temperature on this cold tip. Okay. First, before going to this conversation, I will give you the brief introduction. So there are basically 4 type of these cryocoolers. So first one is the Stirling type of cryocooler. They are mainly used for in the 80K range because they are very efficient. Cost effective also, but the limitation is they cannot go beyond 20K. Then is there also a growing interest in the pulse tube cryocoolers. They have this low vibrations and very high reliability, but the difficulty is they cannot be scaled down to the small sizes. They are very efficient for the large sizes. Then is the GM or the Gafford McMahon cryocooler. They are simple and they are robust, and they mostly they are used for all these demanding applications. And there are these JT or the Joule Thomson cryocoolers. They are very compact, but the only is that they give you the high cooling at a fixed temperature. So each technology have their advantages and disadvantages. We will talking about this cryocooler only. Gafford McMahon. We have developed the cryocooler which is based on this technology. Nowadays, the cryocoolers are coming with this GM technology plus with the plus tube the hybrid mode. So I will explain you how this cryocooler works. So I have drawn this very simple sketch where you can understand how the working principle of the cryocooler. So you have a compressor, then just I put the valves. This is SP valve, LP valve, and then you have the displacer inside of the liner, and this is your. I think this presentation is old one. Okay. Anyway, I will. This is your the cold tip. So in the first case, the compressor is the only the powerhouse for this CCR. So it supply very pure helium gas, say at 250 psi, and LP pressure in our case is 50 psi. So you can see the SP valve is open and LP valve is closed. So this displacer is at the bottom side. In the next step, just displacer this goes up, still SP valve is open and LP valve is closed. So this is the second step. And in case of the third step, you can see this SP valve closed and LP valve open. So the expansion of gas take place, and this because the helium gas expand, so cooling take place, and in the next step, SP valve still closed, SP valve still closed, LP valve is open, and this displacer goes down. This way, actually, this is nothing but it's a regenerative type of heat exchanger. So in this cycle, is stored the cooling from this expansion, and when this next step will start, the process will start at some Kelvin or some Kelvin lower than the previous step. And that's how it keep on working. If I do it fast, so it goes up, expand, and then store this. Now, why there is this growing interest? So, one is this very new field, this quantum computing, as a very this curricular has made very this popular because of that. Then there are the superconducting electronics. Then there are sensors which are used in the defense. So if you look at this, the mainly you can categorize this application into the magnets. Then you have the life sciences and the research, like superconducting magnet, waveless shifters, and so forth. Now look at this very simplified diagram of this quantum computing. So you have the curricular. This is the curricular. This is, as I said, this is the first stage at 50K. Then the second stage is 4K. And after that, the dilution refrigeration take over. Dilution refrigeration is nothing but instead of the helium-4, the mixture of helium-4 and helium-3 is used. And this dilution refrigeration can go to up to this 2 millikelvin easily. And for this quantum computing, the requirement is something in the range of 10 to 15 millikelvin. And then you have this qubit chip, which is here. And you maybe have seen that a lot of this wiring goes from this to that. And this qubit is, as you know, is very, very fast. What are our strengths? We have designed, as you look at this in this picture, if you see from the outside, it look like only pipes. Actually, this is a vacuum shroud, and inside it is the cold finger. So, and this is the motor. Motor is also this helium sealed. Actually, we have made a curricular that simple that it's a single button operated. In case of any fault, this red light will glow, and this is the expander part, and this is the compressor part. So compressor and expander part are connected through flexible hoses. The gas comes to through this pipe, then goes perform the cycle and goes through this motor and back to the compressor. We have designed multiple single and double stage curricular, and not only we have designed, we have also given then for the field trials at the diverse user laboratory inside the CAT and outside the CAT. Also, we have this recently we have transferred the technology for the 30K curricular to the industry along with the helium compressor and through the Atmanirbhar Bharat initiative. So, when we say about the class of the curricular, so actually class depend upon the ultimate temperature or the temperature of interest. If I say 30 Kelvin, it means that the ultimate temperature will be 30 Kelvin. The design of this single stage curricular is it can go to the minimum temperature of 30K. Then there are some curricular, say 40K class. It doesn't mean that the ultimate temperature is 40K. It means that this curricular has the maximum capacity, cooling capacity at the 40K. It can go down to the certain temperature, but the area of interest may be something at the higher temperature. So we have built this 30K curricular and 10K curriculars, and we have also built one system which can go to the even 4 Kelvin. So when I say this 30K class curricular or 10K class curricular and 4K curricular, we were only interested in the ultimate temperature, not what you can say some refrigeration at the higher stage. So these temperatures are capable of reaching 30K, 10K, and 4K. If I talk about the this 4K cryocooler, the 1 watt cooling with 1 watt cooling power at the 4K are the most commonly used cryocooler for the MRI applications. So these are the cryocooler which are very commonly used in the industry. Okay. For the superconducting application in the accelerator, or you can say for other application, we don't want to deploy multiple cryocooler, but there is another scheme. World over is also some very few people are also working where we can produce large refrigeration at 4K using single cryocooler. So scheme is like that. You will have a cryocooler, one cryocooler which is capable of producing say 4 Kelvin at 2 watt with 2 watt cooling power, and then you have a secondary circuit. We have where you have the series of heat exchangers. The gas and this secondary circuit is also connected to a helium compressor. So you have a one cryocooler and 2 helium compressors. And this is corrected by this way. Sir, give me 2 additional minutes because it's very important.
Dohanji, 3 minutes only.
Okay, I will try to finish it. So this first stage is coupled at 45, and second stage is coupled at say 12 watt, and then through the JT, and the load is at the 4K. So here the thermal management and the material selection is very important. So by doing this scheme, you can achieve more than say 7-8 watt at 4K. And this type of cryocooler is very good for the superconducting application in case of accelerator. And we have a strength. We know how to design cryocooler. We know how to design this heat exchanger which can operate at the 4K. We know how to design JT valve. We know how to design this cryostat. So most of the components that are used, we know how to design and working helium compressor. So most of the component used in the circuit we can design in-house and build through the industry. So this is the cooling characteristic of our 4K cryocooler. So it can achieve this. We have started. I have taken one instance where we have started at somewhere at 1130, and by this 1326 we have achieved a 4 Kelvin. Then because of the excitement or all that, we have taken the few reading. So here you can see. So this is the first stage temperature, and this is the second stage temperature. So the rise in the temperature is because these cryocooler are self-cleaning. Our cryocooler use 5N purity helium gas, so it clean itself. If there is a impurity, temperature goes up, and this impurity is freeze somewhere, and then it comes down again. The scheme which I have mentioned can provide a very good cooling at 4K. This has a very reduced vibration level, and it can supply the cooling long time. And this is very cost effective for the commercialization. These are the cryocooler we have supplied in the different labs. So these are the photographs of the cryocooler. And before finishing my presentation, I just want to I have a price quote of the cryocooler. Just I want to read out so that you have some questions specific to the. So if I want to buy a 4K cryocooler which has a cooling capacity of 1 watt, this is from Sumitomo. This will be costing around 48 lakh. The same cryocooler, the different type of cryocooler which have only 0.4 watt of the cooling power at 4K will be 35 lakh. So you can see 15 lakh difference. Both are producing 4K, but the difference in the cooling power is in the range of only 1.4 watt. And 10K cryocooler, which is very used this in the cryo pumping, is around 26 lakh. Whereas 30K cryocoolers with the wattage of something like 35 watt at 80K will be of the 35 lakh. This doesn't mean that the cryocooler which is going to the lower temperature is the cheaper one. It's depend upon the what is your requirement.
Dohan sir,
Okay.
I think the time is
Sir,
over. Thank you.
okay. Thank you. Thank you very much.
Yeah, we can take a question or two, Chairman sir.
No, sir, there's no time. That's why I did not ask also.
You can ask me later on. I'm
Yeah, he's
open
here
to,
only.
I'm open to the every question you can ask me.
Okay,
ठीक है sir. Sir,
okay.
sir, online there is a.
Yeah,
Sir, you can ask, sir.
this is a good work, Gohan. I just wanted to know
Thank you,
if the heat load at 4K is we are able to heat load at the first stage 40K if we are able to reduce, will we be able to support slightly more load at second stage?
No, sir. Actually, it depends upon the design. So how you design it, so it's on that. Whether you want to go to the lower temperature or you want to support some load at certain temperature. So even if you reduce a few Kelvin at the first stage, the temperature will be more or less the same. You can gain maybe a few milliwatts on that.
Was this 1 watt measured at 4K? How did you measure it?
No. I am saying at the ultimate temperature is the 4K at 0 watt.
No, at 0 watt. Okay. Did you
Ultimate.
measure the heat load? Did you measure the heat load at second stage?
So I'm saying, sir, it's 0 watt at 4K. So if you want some wattage at 4K, the compressor size will be 2.5 times, and the design of this will be changed. We at this time we are only interested to work out how to achieve 4K.
Okay. So it supports almost no power at that. Okay, that's fine.
Yes, sir.
That's
Yes, sir.
understandable. Okay.
Yes, sir.
Thank you, Dr. Malhotra.
Yes, sir.
Please.
Thank you, sir. Thank you.
So now we come to the last talk of the session.
Yeah,
And this is by
Yes, sir.
Okay, the GPM of ISPA is now delayed by 15 minutes. So next talk is by Mr. Atanu Datta. It is on status of K500 superconducting cyclotron at VCC. Please.
Thank you, sir.
You have 12 minutes and then 3 minutes.
Okay. So good afternoon, everybody. So we are right now at the last lecture of all this INPAC session. So I'll be talking a little bit of different things. I will present about the status of superconducting cyclotron in VCC Kolkata. So you know that this superconducting cyclotron in VCC was developed mainly for basic science research in the field of nuclear physics and material science. And this cyclotron can accelerate positive charge particles whose charge to mass number ratio comes in the range of 0.01 to 0.5. In this range we can accelerate. And maximum energy, you know, we can get up to 80 MeV per nuclei for the lighter atoms. And we can get up to 20 MeV per nucleon for the heavier ions whose mass number is more than 100. So in 2021, from 2021 actually, we have started to deliver different kinds of ion beams in superconducting cyclotron, and at present we are delivering this nitrogen, oxygen and neon beams. So after this brief introduction, I will mainly cover, I will give a brief description of the system, then I will show you the operation region, present ion beam we are under operation, experimental facilities, fast beam experiment, future plan, conclusion, reference and acknowledgement. what happens. Okay, so you know that these parameters are very familiar to you, that we can get maximum 5 Tesla of field in the superconducting cyclotron, and we can produce this field using a 2 pair of niobium titanium coil, and 3 RF resonating cavity, okay, are used to provide necessary accelerating field to the charged particle, and we can vary the RF frequency in the range 9 to 27 megahertz. So this is basically the ion source area. This is the ECR ion source, 14.45 gigahertz ion source, where we produce the positive charge particles, and then we transport through these horizontal beam lines all through this. And then there is a vertical bending magnet. With this vertical bending magnet, actually we bend the charge particles in vertically downward direction. And after that, the charge particle passes through the central hole of the magnet, where the field is very high. And after that, it enters in this very small, this whole region. It is basically, this is the casing of the spiral inflector. So spiral inflector basically a electrostatic device which can bend the vertically injected beam into the horizontal plane of the cyclotron. Unfortunately, I forgot to put the figure of the spiral inflector. And then beam comes out, that is a hole sidewise. From that beam comes out and then enters the first D. So then after that it enters the second D and then the third D. So in the gaps between these two D and this ground part, ions gains energy. So as the ion gains energy, its radius also increases. So as the radius increases, it moves towards the outer, means towards the extraction region. So I will be skipping this figure because in first day lecture our director have already shown similar type of figures, and these are actually the components of magnets and the RF system, and these are the some components of the RF system. Similar types of figures are shown in the first day. Okay, sorry. Okay, so I already mentioned that as the ions gets energy, its radius increases, and as its radius increases, it comes towards this extraction region. So in superconducting cyclotron, that extraction region is very means the ion has to cross a very long path. Means it enters the first electrostatic deflector here, then all through this path it has to cover, then it has to come out through the cyclotron through this region. Now, whenever we say that ion beam is reaching at the extraction radius, that doesn't mean that all the ion beam will pass through the electrostatic deflector. That ion beam needs to satisfy some type of conditions, and then only the ions will pass through this fast electrostatic deflector. So, and to do that, we need to offset little bit the ion beam so that they can enter easily in this fast electrostatic deflector. And here the ion beam, suppose in 667 millimeter, we inject the ion here, then it will come out from 680 millimeter. That means almost 13 millimeter of radial gain occurs. So in this way, actually, we moves the ion towards the outer radius. So then it enters into the second electrostatic deflector. But in this process, actually, the ion moves towards the higher radius. And as the ion reaches the higher radius, there the magnetic field starts to fall very sharply. And that creates a very large radial instability in the beam. And to control that large instability in the radial focusing, we use some separate kind of channels called magnetic channels. These M1, M2, M3, M4, these M8, M1 to M8, these are passive magnetic channels. We use these kind of channels to guide the beams. And then finally through this channel, we take out the ion beams from the cyclotron. So this is the photograph of the fast electrostatic deflector. You can see this is the high voltage electrode and this is the septum. So it is kept at a negative high voltage and passes through this region. And gap is almost 6 millimeter in this range. Okay, this is the photograph of the magnetic channel. So this is the copper block, and inside the copper block you can see these parts, these are iron part, these are embedded within this copper block, and that is the hole. So we call it channel. So through this channel actually ion beams passes. The main purpose of using these iron pieces are that it locally modify the magnetic field in this region and provides a better field to get desired radial focusing. Okay, let's come for the operational region. I already mentioned that in superconducting cyclotron we can use RF in the range of 9 to 27 megahertz, and our magnetic field limit is from 30 kilogauss to 50 kilogauss. So you can say that this rectangle, if you draw this large rectangle, this will be our actual operational region. But at present we are operating in this region, means the RF frequency is from 14 megahertz to approximately 18 megahertz, and the magnetic field we are presently limiting at 30 kilogauss to 34 kilogauss. Now we have seen that if we operate in this region, the beams remain very stable, and for nuclear physics experiment they want very stable beam. So we didn't at this moment we are not trying to go at the higher power or higher frequency, but gradually we will do that. So at present this is our operational beam. So these are the list of the some ions that currently we are means delivering. So nitrogen, oxygen, and neon. Just I will mention few ions. So this is a nitrogen 5 plus 17.89 megahertz. So this is 29.4 MeV per nuclei, approximately 30 MeV. So this is the highest energy so far we are getting. And you see that this nitrogen 4 plus, there are several frequency, 14 megahertz, 14.46. And as the frequency increases from 14 to 15.10, you can see that the central field, this B0 is the central field, that is also increases. So that means that if the magnetic field increase, then the requirement of D voltage also increases. So here I have put the D voltage requirement in terms of power. So you can see that initially it was requiring approximately 23.7, then it is increasing 25, and this 30.8. So as we go towards the higher frequency, the required RF power also increases. And these are the some more ions that we have already delivered. And at present we are giving this 15 megahertz nitrogen 4 plus beam to the user. Okay, I'm skipping this bit. Okay, experimental facilities. So in VCC we have actually provision. We have provision for 4 beam lines, and at present we are giving means using this fast beam line. And here there is a scattering chamber inside which our nuclear physicists they do all kinds of experiments. And that neutron array is already installed, but that beam line we have not yet installed. So these beam lines are at present they are absent now. Okay, so this is the scattering chamber that I already mentioned. It is called SARC, high vacuum scattering chamber, or segmented horizontal axis reaction chamber. This is very large scattering chamber. You can see its diameter, its length is 2.2 meter, means, and its diameter is 1 meter. So this is the one experimental facilities. And there are some other experimental facilities are also there. They called Chakra, the 4-pi charge particle detector array for kinematic reconstruction and analysis. Actually, these slides our nuclear physicist they have provided me. So I'm just showing you that whatever facilities will be used in future. Okay, then there is this new for neutron-based experiment. There is liquid scintillator-based neutron time of flight array. That is already installed. It is in the second beam line, but the beam line we have not yet installed. And they have also developed this multi-wire proportional counter to explore the fission dynamics in heavy ion collision. At present, they are using these detectors. So this is the one photograph inside the scattering chamber. There is one MWPC detector. This is another detector, and this is the sample holder where we can target can be placed. And okay, so this is the the experiments with the fast beam. So that characterization of fast beam with the K500 superconducting cyclotron was published already in this paper. Topon Rana and their team, they have did this experiment, and they from our calculation we mentioned that that we provided them that 252.1 MeV beam we have given them. But from experiment, they found that that's the peak was coming around 250.3 MeV, and this deviation is due to that uncertainty in the turns, means which turns are passing through the deflector and the other electronics and detector uncertainties. And the energy spread they calculated, it was around 585 kiloelectron volt. And these are the some results. Means it is these results with 14 nitrogen on gold target, So with 18 eV nuclear beam, and these are actually the means particle identification spectrum. You can see that Z is equal to 2, 3. So different for different particles, they got different types of distribution. And okay, these are the some experiments they have carried out. I actually do not know in detail what are these things. This experiment, the isoscaling property of fragments emitted in reaction via nitrogen neon on tin target. Various types of tin samples they have used. Okay, and then the experiment study of isospin equilibrium at higher excitation, then study of entrance channel effects. So they have also communicated these results in physical review letter, physical review C. So now the future plan is that we will try to expand our operational region. I already mentioned that we are now limited very shorter operational region. So next we will try to develop argon beam, and that argon beam will argon 12 plus generally gives in our settings 25 MeV per nucleon. That means almost 1 GeV of total energy we can achieve with the if we succeed in accelerating the argon beam. And this installation and commissioning of second and third beam line, it is not yet decided, but for that it will be required a long shutdown. So at present, all the quadruple triplets and switching magnets are already designed for this beam line, and they are already manufactured, and it is there in VCC. And some beam dynamical studies are also have been taken out to finalize the position of the magnets. Already it was designed sometime before, but now with the help of the experimental data, we want to finalize the position. So there was one paper in the poster session in the first day. So this is the
okay. Thank you.
Okay. So this is the final summary. So ion beam presently available for nuclear physics experiments is up to 30 eV nucleon. Though the available operational region is small, but it provides stable beam, which makes nuclear physics experiments successful. Operational region will be increased gradually, and then installation and commissioning of second and third beam line will start at suitable time. So these are the some publications. Okay, these are the some publications from our experimental physics groups. That is the characterization paper, and these are the some DAE BRN symposium paper. And these are the some papers related with superconducting cyclotron from my colleagues. And there are several other papers also there, but I could not put all the papers here. So I like to acknowledge all my colleagues for their continuous support to get the superconducting cyclotron right now in this present condition. So these are my many colleagues, but many are missing here. So it is the final slide. Thank you.
Thank you, Atanuji. I'm sorry we can't take any questions because we are late by 14 minutes. Please.
Yes. Okay.
So that brings us to the end of the last technical session. Thanks to the audience and the speakers both.
On behalf of the organizer of InPAC 2025, may I request Shri Viraj Bhangi sir, Associate Director, Electron Accelerator Group, to present a memento to session chair for successfully conducting this session. Sir.
आपने मेरा ट्रांसफर सर मैं ये डेस्कटॉप पे बना दूं क्या? तो इसको एक मिनट बंद कर सकते हैं इसका खोल के इसी को मतलब एक प्रोजेक्ट कर लेंगे एक अच्छे से एक बार बोल दीजिए उनको बंद कर सकते कॉपी करना है हाँ
नहीं तो अभी एक काम करते हैं कि we are going to start the proceedings and due to quorum we will be delaying it for another 10 minutes.
फाइल आपकी है
ठीक है और मेरे पास 2 और हैं एक इनका हो जाएगा ठीक है तो नहीं
कैमरा बंद करना है
हाँ ठीक है
नहीं नहीं नहीं
नहीं स्टॉप शेयर मत करो
नहीं हटा रहे हैं ना उसको
शेयर
हटा रहे हैं। तुमने हटा दिया ठीक है इसीलिए मैं
Since one more parallel session is going on, we have to wait couple of more minutes. It's the last, this thing is going on, last session. Meanwhile, when we assemble, we'll have to see whether the quorum is complete or not. Otherwise, we have to adjourn for another 5 minutes. So we are starting ISPA GBM now. Because of quorum, we have to delay it, adjourn it for 5 minutes, and then we start. The last session also ended there, and people are coming. So we will start the ISPA GBM after 5 minutes. Thank you for your patience. So good afternoon once again. Now we have got the people also and quorum is also done. We can start our session and with the permission of President ISPA, shall we start the proceedings for the GBM? Okay. So now I request President ISPA, Gurnaam Singh sir, and Additional Director Tushar Puntambekar ji to come on the stage for the ISPA GBM function. I request Treasurer Sri Anil Holikatti to accompany them.
इसको अनफ्रीज कर दो, अनफ्रीज कर दो। नहीं आप क्या पानी वाले तो गिलास भरे ना, पी लो ना। कहाँ? ये भरे।
So, our this evening is especially for our valuable guests, and those are none other than our 4 people who have immensely contributed to the accelerator program. And we would like to felicitate all 4 of them. Dr. Archana Sharma, please give a big hand of applause to Dr. Archana Sharma. Dr. Gopal Joshi sir. Sri Govind Parchani sir. Last but not the least, Sri Mahen Lad sir. सर सभी लोग डिमांड कर रहे हैं कि सर एक बार खड़े हो जाएं। Okay. So what we are not doing any other formalities, but just directly starting the felicitation function. So with the permission of President. Correct, sir? Yeah. Thank you. So first of all, I would like to invite Sri Sanjay Chokse sir to give the brief introduction of Dr. Archana Sharma, because he is from his college and he was associated most right from, I think, his college days. So big round of applause for Sir Chokse sir.
बायोडेटा नहीं, इसमें 2 पेज इससे बड़ा है ना, इसी से आगे वाला। Thanks, Vikas Jain, dignitaries on dais, and other colleagues. I think Archana Sharma madam itself is very popular, but madam I know since I think 1982 or 3, when she just joined college, and my house happened to be just next to the block of girls hostel. So I used to see Madam Archana Sharma used to have one old bicycle which she used to, although college was very near from hostel, but she was religiously using that bicycle. सही है ना? मैंने शायद गलत नहीं बोला। और मैं जब BRC ट्रेनिंग स्कूल ज्वाइन किया तो मतलब because our motivator for joining DA is same actually, that is Dr. MS Balde.
जिनकी किताब शायद बहुत सारे इलेक्ट्रिकल वाले पढ़ते थे, थायरिस्टर इंजीनियरिंग बाई बर्डे साहब, और उनकी बेटी शायद हमारी कॉलोनी में फर्स्ट थी वो ज्वाइन ट्रेनिंग स्कूल 30th बैच इलेक्ट्रिकल, रोहिणी दत्तार। वो उनके फादर हम मैडम को भी मोटिवेट किया, और फिर मैं आगे पीछे हो रहा था वेदर आई शुड ज्वाइन ट्रेनिंग स्कूल और नॉट। तो उन्होंने बोला नहीं, मेरी बेटी ने ज्वाइन किया, अर्चना तिवारी ने भी ज्वाइन किया, भाई तिवारी थी, और आपको भी ज्वाइन करना है, ये बता दूं मैं। इस तरीके से हम ट्रेनिंग स्कूल का, मैडम से मेरी बहुत जल्दी मुलाकात हो गई थी बीआरसी ट्रेनिंग स्कूल में मैं था जब, शी वॉज इन आई थिंक APPD। उन्होंने कुछ एक्सीलेटर वर्ड बताया था, मुझे बस में बैठा था, मुझे याद तो नहीं, समझ में नहीं आया कि एक्सीलेटर में क्या है, क्योंकि ट्रेनिंग स्कूल में उस समय एक्सीलेटर पढ़ाया भी नहीं गया था। बट मुझे इतना मालूम था कि शी स्टार्टेड वर्किंग इन एक्सीलेटर। तो मुझे 88 में ही पता चल गया था कि मैडम इज वर्किंग इन सम डिवीजन ऑफ BRC विच इज़ रिलेटेड टू पार्टिकल एक्सीलेटर। सो अर्चना मैडम की जर्नी उस हिसाब से देखा जाए तो मतलब ऑलमोस्ट नाउ इट इज़ 37 ईयर्स इन पार्टिकल एक्सीलेटर, और काफ़ी उन्होंने लंबा समय बिताया है। And she retired as distinguished scientist and group director BTG from BRC in August I think था, है ना, if I'm correct। मतलब मैं ज़्यादा कहीं देख नहीं रहा हूँ बेटा, मुझे काफ़ी चीज़ें वैसे ही याद रहती हैं। So 31st August she retired from BRC, और उस समय कुछ कॉन्फ्रेंस थी, मैं गया भी था इनके रिटायरमेंट पे वहाँ पे, और बहुत जल्दी उन्होंने मुझे एक दिन फ़ोन करके बताया कि मेरे को तो मतलब मैंने एक जॉब ज्वाइन कर लिया है रायपुर में एस IIIT, और AIML वगैरह कुछ पूछने लगी मेरे से। मैंने कहा मुझे तो AIML के बारे में नहीं, मैंने कहीं यूज़ नहीं किया है, बट वो बोले कि शॉर्टली शी विल कनेक्ट। तो उनका एक मतलब प्रोफाइल जो है एक्सलेटर और इन चीज़ों के लिए बहुत बढ़िया, और मतलब शी मोटिवेटेड मैनी कलीग्स। उन्होंने एक्चुअली हमको और एसएन सिंह को भी बहुत हवा भरी थी PhD के लिए, और द्विवेदी जी को भी, लेकिन हम लोग वो पता नहीं PhD नहीं सोच पाए। हमने कहा मैडम आपको ही हम डॉक्टर बोल देते हैं, हम लोग नहीं कर पाए डॉक्टर, तो कोई बात नहीं है। एसएन सिंह ठीक है ना, काफ़ी मोटिवेट किया था मैडम ने हमको, और मतलब एक्सीलेटर में उनका काम मतलब बहुत वेल नोन है, और बहुत सारे उनमें, और मैं थोड़ी थोड़ी देर में देखता था कि वो एक किसी नए फील्ड में भी दिखाई देती थी। एकदम से पता चला कि खारघर प्रोजेक्ट में भी है। पहले मैं वो जानता था कि शी वाज मेकिंग पावर सप्लाई फॉर वेल्डिंग, पल्स्ड वेल्डिंग, और उसके बाद मल्टीपल, मतलब आप उनका पूरा स्पेक्ट्रम देखेंगे तो बहुत फील्ड में उन्होंने काम किया है। एंड शी रिटायर्ड आफ्टर मेकिंग लॉट ऑफ कंट्रीब्यूशन इन पार्टिकल एक्सीलेटर। थैंक यू।
ठीक है सर, एक स्लाइड और थी, फिर भी मैं so I will just complete, no problem. So as Choksey sir has told most of the things, I will say that she has done PhD from IISc Bangalore, and she has guide for many PhD students at HBNI and elsewhere also. One thing which I think we must applaud, she has been selected in top 75 Indian women in the Principal Scientific Advisor newsletter. That is something which is a remarkable thing, and we have such person with us. So thank you very much for accepting our invitation for this. So with this, I would like to invite her to the stage.
इन पिक की स्लाइड लगा देना।
अच्छा नहीं, ठीक है, ये लगने ये इनका यही रहने दो। So ma'am, आइए। First of all, I request President ISPA to give her a to honor her with a sapling. चौकसे जी आप भी आ जाइए। यस यस। Now I request Additional Director Puntambekar sir to facilitate her with और बैचमेट भी हैं पुंतांबेकर सर तो बैचमेट भी हैं सॉल एंड श्रीफल Gurnam Singh sir, please give him. Thank you, sir.
Thank you, sir.
I request President ISPA and Gurnam Singh sir give her the certificate and souvenir. Now I request Archana ma'am to say a few words for this ISPA and INPAC or whatever you want to say, ma'am. Thank you.
मैं ज़्यादा बोलूँगी तो इमोशनल हो जाऊँगी और इतना अच्छा माहौल किया है चौकसे जी ने तो मैं उसको ख़राब नहीं करना चाहती हूँ। रियली में मेरा रोम रोम आप सभी लोगों का कर्जदार है और जो भी मैंने अचीव किया वो मेरे सीनियर्स की ब्लेसिंग्स थी, जूनियर का प्यार था और डिपार्टमेंट ने जो अपॉर्चुनिटी दी उसको मैंने मतलब कर पाई और इतना रिकग्निशन इतना वो मिला कि मतलब ब्लड में आ गया है अभी सब कुछ। तो मैं आप लोगों को जितना आभार प्रकट करूं कम है और इस प्रोग्राम में बुलाने के लिए मैं विकास जी का, चौकसे जी का, पूरी कमेटी का, इधर इस्पा का मैं तहे दिल से धन्यवाद देती हूँ। इंदौर मतलब हमारा दूसरा घर जैसा ही रहा है, बीआरसी के बाद निकल के हर प्रोग्राम में हमको सपोर्ट मिला है। पल्स पावर एक्सीलेटर होता था तो मैं जाती थी, आरएफ एक्सीलेटर में कविता जी जाती थी, आरएफ साइड से मंजरी जी, तो हर जगह हम लोग ऑलमोस्ट ग्रो किए हैं यहाँ पे, मतलब बचपन से आते रहे हैं। 4 लोग एक ही बाथरूम भी यूज़ किए हैं, अभी 4 कमरे में एक बाथरूम, मतलब एक इतना बड़ा सूट दिया है। थैंक यू पुतंबेकर जी इतना सम्मान देने के लिए। और बस आखिरी में यही बोलूँगी कि एहसान मेरे दिल पे तुम्हारा है दोस्तों, ये दिल आपके प्यार का मारा है दोस्तों। थैंक यू।
Thank you, ma'am. We are blessed to have you here. Now I request Gopal Joshi sir. Just before you come to the stage, I think I was targeting, I was asking some of the colleagues, but unfortunately they have left for either Mahakal or some other work. So I will.
विकास
Yes.
विकास मैं ऑनलाइन हूँ, संजय मल्होत्रा।
अरे हाँ, बहुत बढ़िया। मल्होत्रा sir, if you can read his biodata, it will be great pleasure. Are you able to see our screen?
Yeah, I am able to see your screen, Vikas.
Yes, yes.
बायोडाटा
So,
आप
sir,
ही पढ़िए।
सर आप पढ़ दीजिए सर का बायोडाटा।
अरे नहीं, ये तो आपका प्रेरोगेटिव है, आप पढ़ लीजिए। मैं थोड़ा सा बाद में
आप as a ISPA member, I request you to read his important contributions, sir.
Okay.
Malhotra sir.
ओके, थैंक यू सो मच, थैंक यू सो मच। एंड सभी लोगों का पहले अभिवादन करता हूं मैं। डॉक्टर गोपाल जोशी कंट्रीब्यूशन तो मैं इस स्लाइड के बिना भी बहुत अच्छे से बता सकता हूं। वो एज ए सीनियर इलेक्ट्रिकल इंजीनियर एंड एन एल्डर ब्रदर, we know his contribution towards, he's sort of, you can say, the first generation accelerator technologist at BRC. He belongs to that first generation of accelerator technology engineers at BARC. And मैं पहले ऑफिशियल वाला आपने जो बनाया वो पढ़ देता हूँ। He has about 38 years से ज़्यादा है हमके। He joined as a young a very young engineer, graduated from Madan Mohan Malviya National Institute of Technology, Tawarisi कहते थे, जयपुर का. He academically, of course, he is a brilliant engineer. He did his PhD from IIT Bombay under the redoubtable Professor Girish Kumar. Professor Girish Kumar is a very famous in all RF engineering community, RF technology community, and physics community. He was on the tower radiation. आज जो ये words mobile phone से आ रहे हैं, SAR वगैरह, स्पेसिफिक एब्जॉर्प्शन रेशियो, उसके वो चुनिंदा साइंटिस्ट में से थे, मेजर करते थे हर जगह. तो गोपाल जोशी साहब ने उनके अंडर में पीएचडी किया है, और एकेडमिकली आल्सो एट आईआईटी बॉम्बे हिज नेम वाज वेरी गुड. गोपाल जोशी साहब के बनाए हुए कंट्रोलर्स, एज आपने भी पॉइंट आउट किया है, ऑस्ट्रेलियन नेशनल यूनिवर्सिटी में हैं, IUSC दिल्ली में इनका नाम है, डॉक्टर भुवन साहू मस्ट बी अराउंड, ही इज ऑलरेडी ऑनलाइन, आई एम सीइंग भुवन साहू, उनके साथ इन्होंने काम किया है. इनके कंट्रोलर गैनिल में इनके सेंसर्स, बीपीएम्स कंट्रोल सब काम कर रहा है. एंड आई एम सो वेरी हैप्पी टू अनाउंस दैट फर्मिलैब कोलैबोरेशन में गोपाल जोशी का शुरू से साथ रहा है. इन द एंड रेजोनेंस कंट्रोल सिस्टम इनका फर्मिलैब में भी पिछले दिनों में ही चला है, जस्ट एट द कस्प ऑफ हिज रिटायरमेंट. हिज कलीग्स हैव कम बैक एंड दे आर हैप्पी टू अनाउंस दैट. बिसाइड्स दैट RFQ वगैरह कंट्रोल और लेहिपा में इनका बहुत बड़ा योगदान रहा है. And I am very happy to be associated with him. And finally, also I'm part of his division and now heading that division only, which Joshi Sahab has left a rich legacy for that. Thank you so much.
One more slide is there, sir.
हाँ जी, बोलिए. One more point, novel techniques, हाँ, self-excited group. अच्छा, one more slide is there. अच्छा, sorry, मैंने तो अपनी तरफ से काफी सारे ऐड कर दिए थे. He richly, yes, definitely 325 megahertz solid state RF power amplifier. He was head of division warm magnets. In fact, some of the first deliverables to Fermilab happened in the form of MEBT magnets, and all this good work that our team also did. Actually, the team performed best when Gopal Joshi Sahab was the head of division. I sincerely admit that under his leadership, actually, people felt very motivated. In a way, people were able to perform, and largely his giving a long rope and a wider scope to youngsters. For that also, on behalf of all the young team, my team, I would like to thank him for that. His team, of course, must be a fan of him. He is like a godfather to them, control team. And indigenous development of RF components, bandpass filter, high power RF loads, all these things he has done. He also, at the fag end of his career, he actually graduated from classical mechanics into the quantum domain. He just loved. He read the quantum mechanics for many years. Now his team is developing a superconducting based qubits. Actually, he has guided that team well. So I think he was one to graduate. Although many people may not feel like going into a new field at an advanced age, but he has gone into that. Thanks to him. Thank you so much.
Thank you, Malhotra sir, for coming all the way from Mumbai to here through voice. So we could listen you very clearly, and we could get your feeling about Dr. Joshi. I request now Dr. Joshi to come onto the stage. Yes. I request Puntambekar sir to give him a sapling. I request Gurnam Singh sir to offer him Sol and Srifal.
Now I request President ISPA to give the certificate. Sir, we are really grateful to you, and you have taken time to come Indore for the making the InPAC a great success. I request you to say a few words for this August gathering.
Thank you, sir. मैं बहुत डीपली ऑनर्ड फील कर रहा हूँ इस सम्मान दिए जाने पर। ये मेरे लिए बहुत बड़ी बात है। लेकिन जैसा अर्चना मैडम ने कहा, ये मैं भी वैसे ही महसूस कर रहा हूँ कि ये सब मेरे सीनियर्स का आशीर्वाद है, और मेरे साथ में जो काम कर रहे हैं जो लोग, उन लोगों का जो मेरे प्रति जो हम लोगों ने मिलके काम किया, उनका जो सहयोग रहा, ये उसी से ही संभव हो पाया है। तो ये अवार्ड ये सब उन्हीं के लिए है। तो और मैं संजय जी आपको बहुत धन्यवाद देता हूँ। आपने मेरी क्षमताओं से बहुत अधिक मेरे को क्या सम्मान दिया अपने बातचीत में, तो उसके लिए मैं बहुत बहुत आभारी हूँ। आपका बहुत बहुत धन्यवाद। मैंने भी आपसे बहुत कुछ सीखा है। इतना आपके जैसा मेहनत करने वाला व्यक्ति अगर साथ में रहे तो थोड़ा तो आदमी में आ ही जाता है साथ। तो थैंक यू वेरी मच।
आई एम ओवरवेल्म्ड सर।
हाँ, धन्यवाद संजय। और सर, मैं फिर से और अधिक, मेरे पास ज़्यादा मैं बोल नहीं सकता है, लेकिन मुझे बहुत खुशी है और मैं बहुत बहुत क्या कहते हैं अनुग्रहित फील करता हूँ कि मेरे को इतना उस अवार्ड के योग्य समझा गया। थैंक यू वेरी मच।
Thank you, sir, for your kind words. Now I request Govind Parchani ji, but before requesting him to come on the stage, I request his colleague Bharat ji Ravlani ji. Are you here? Yeah. Because जहाँ पे हम खड़े हैं शायद आपके बिना संभव नहीं हो पाता, और सर ने बहुत ऐसे काम किए हैं एक्सेलेरेटर से रिलेटेड, तो वो भी थोड़े से हम आपको बताना चाहेंगे। तो भरत लावलानी जी।
धन्यवाद विकास जी, ये मौका किस्मत वालों को ही मिलता है। श्री गोविंद परचानी जी, जैसा सब जानते हैं, इज आउटस्टैंडिंग साइंटिस्ट एंड प्रेजेंटली वर्किंग एज चीफ इंजीनियर RRCAT and head construction services division. He has completed his BE Civil in 1987 from Shri SG ITS Indore, and he has worked initially in the Gilcon Project Services Private Limited in 1989. Then he was selected to training school orientation training program by BRC Training School. In 1990, he has joined ANCED BRC, and then subsequently he was transferred to Rajaramana Center for Advanced Technology. That time it was called Center for Advanced Technology. In 91, he has completed his master's in structural engineering in 1997 from SG ITS only. And he has expertise in design and construction management of research and development laboratories. He has been a key person in successful completion of planning, design, and construction of number of R&D labs for laser and accelerator program, including Indus Complex, and the successful construction of Indus 2 facility, having challenges for vibration isolation, precision requirements of alignment, environmental condition, radiation shielding, and multidisciplinary services to his credit. He has also contributed for creation of facilities for accelerator technology for components development and testing, industrial accelerator development and testing facility at RRCAT, and there was a unique scheme for radiation shielding, what utilizing a hybrid system of concrete and soil. Probably it was first time in the country. And then his contribution for setting up of many infrastructure facilities for semiconductor cavity development program, which includes VTS, HTS, chemical lab, and ISO 4 clean room facility for assembly have paved way for research program. His dedicated efforts for comprehensive planning, design of building facility for IRFEL lab has also enabled not only in undertaking the project in phased manner, but also making it a user facility afterwards. The use of innovative techniques for ground improvement and radiation shielding vault has facilitated the construction of ARPF at that typical site near Sabji. Everybody knows it's a very typical site near the river. And in addition to that, he has been instrumental in conceptualization of industry. HBSRS, he has contributed. In fact, the many layouts and many design inputs are already ready before we get the project. So it is very, there are a number of challenges in terms of ground vibration isolation for sensitive booster and storage ring. He had been steering the construction program for about 60 buildings, particularly. It is a very big number which has got integrated services for civil, electrical, air conditioning, and horticulture. He is a member of 34 committees at RRCAT. In addition to, he is a member for building works at IIT Indore. He is a member for building and works committee for IUC, DI Consortium. And in fact, he is member for building and construction committee at IIM Indore also. He has been member of Indian Geotechnical Society, and he is a co-chairman of IGS Indore chapter. And he has published almost 40 research papers, various conferences. He is a recipient of many DA Group Achievement Awards, that is 2008, 16, 17, 18, 19. Under his leadership, RRK Township has received award of cleanest township under Swachh Abhiyan consecutively for 5 years. I think I can go on for a very long time. So I'm extremely happy to read his biodata in front of you. Thank you so much. Thank you.
Thank you, Ravlane ji. I think you have read almost all things, but the cleanest township which you mentioned at the last is really a remarkable work, because we are in the cleanest city and this is the cleanest township. So lot of credit goes to him also. Now, last but not the least, we are waiting for, sorry, I forgot. I thought I will call both of them together, but so I request Govind Parchani ji to come on the stage. Sorry for that delay. Gurnam Singh. I request Gurnam Singh sir to give the sapling. No. I request President ISPA to give the Saul and Srifal, to honor with him Saul and Srifal. No, President. I request Gurnam Singh sir. I request Anil Holigatti also to help Singh sahab. Now I request President ISPA to give the certificate.
क्या आप सभी को मालूम है कि परचानी जी एक कवि भी हैं, लेकिन शायद आज वो एक्सक्यूज मांग रहे हैं। लेकिन एक्सक्यूज किया नहीं जाएगा सर आपको। हम आपसे रिक्वेस्ट है कि अगर आपको कुछ याद आए तो ठीक है, अदरवाइज हमारे लिए कुछ, और स्पेशली सिंह साहब और कुंतम्बेकर साहब के लिए
है। नहीं नहीं, थैंक यू विकास। जो जैसे कविता का बोला, वो एक्चुअली मैं खाली फेयरवेल के दिन पढ़ता हूँ, तो ये अच्छा नहीं होगा कि मैं कुछ कविता आज बोलूं, क्योंकि आज कोई रिटायरमेंट नहीं है। फर्स्ट ऑफ ऑल आई वुड लाइक टू थैंक ISPA फॉर गिविंग मी दिस ऑनर. In fact, this honor is not for me, but for all civil engineers associated with the particle accelerator technology works. ये और भी इम्पॉर्टेंट हो जाता है क्योंकि एक्सेलरेटर टेक्नोलॉजी में बेसिकली जो सब सिस्टम्स होते हैं, कोर सब सिस्टम्स होते हैं, उनमें उनका ज़्यादा मतलब उसमें महत्व है, महत्व बिल्डिंग का भी है। पर ISPA ने इसको रिकॉग्नाइज किया, उसके लिए उनका बहुत बहुत धन्यवाद, आभार। मेरे हिसाब से, मेरे ख्याल से ये पहली फोरम है जिसमें सिविल इंजीनियर्स को ये रिकॉग्निशन मिल रहा है, और ये सिविल इंजीनियरिंग फ्रेटर्निटी के लिए बहुत ही गर्व का विषय है, सौभाग्य है, और एक नई चैनल खुली है, मैं बोल सकता हूँ। और आगे भी ऐसा कई लॉरेल्स आएंगे और हम आगे बहुत अच्छा काम करेंगे। यदि मैं यहाँ पे मेरे साथियों का नाम नहीं लूँगा तो ये अनफेयर होगा, क्योंकि ये अवार्ड मेरा ये सम्मान जो है वो मेरे अकेले के बलबूते पे कभी भी पॉसिबल नहीं हो सकता था। मेरे साथियों ने मेरे साथ जो काम किया, उसी की वजह से ये सम्मान हमें मिला है, और हमें बहुत कुछ सीखने को मिला है। तो सबसे पहले धन्यवाद चोकसे जी को भी, जिन्होंने हमें ISPA का लाइफ मेंबर बनाया तो हम इस स्टेज पे आ सके। बहुत बहुत धन्यवाद। बहुत खुशी का क्षण है, और ये एक बहुत अच्छा संदेश है सिविल इंजीनियर्स के लिए भी कि हमें कंधे से कंधा मिला के चलना है, और एक्सेलरेटर टेक्नोलॉजी के लिए जितनी भी उनकी फैसिलिटीज़ के लिए जो भी सब हैं चीज़ें, उनको पूरा करना है। धन्यवाद, बहुत बहुत धन्यवाद।
या
सर,
विकास, गोविंद जी के लिए एक दो सेंटेंस
हाँ हाँ,
बोल सकते।
एक मिनट सर, एक मिनट। संजय जी आपको कुछ बोलना चाह रहे हैं। हाँ सर, बोलिए।
First of all, congratulations, Govind ji, on this award. See, it is for 33rd batch is almost on the verge of retirement. Several of our colleagues have retired. For all the audience, Govind Parchani belongs to my batchmate, and retiring a bit early since the civil engineering trainees joined necessarily after MTech only at that time, that point of time. They were all postgraduates. So they had the specialization in the field. And of course, the accelerator rests on you. I have written in the chat box too. सबसे इम्पोर्टेंट है ग्राउंड वाइब्रेशंस के अगेंस्ट अगर एक्सीलरेटर को प्रोटेक्ट नहीं करेंगे तो अलाइनमेंट वाले आपको नहीं छोड़ेंगे. सो all things start from the base and foundation of the accelerator that you lay, and several times the credit doesn't come new, but from my side, from the BRC accelerator community, sir, many congratulations to you on finishing this task very successfully. धन्यवाद.
Thank you Sanjay, thanks a lot.
थैंक यू सर. सर, एज यू करेक्टली सेड, बिना प्रॉपर फाउंडेशन के कोई भी एक्सेलरेटर नहीं चल सकता. इसके लिए मैं परचानी जी को बहुत बहुत धन्यवाद देता हूं. थैंक यू वेरी मच सर. लाड जी के एक बहुत परम मित्र हैं श्री सक्सेना साहब. आई रिक्वेस्ट सक्सेना जी, यू सक्सेना साहब, टू कम ऑन द स्टेज और लाड जी के लिए उनका बायोडाटा पढ़ें.
Good afternoon. It's my pleasure to read the brief details about the work of my friend Mahendra ji. महेंद्र जी को वैसे कोई यहाँ गेट में किसी इंट्रोडक्शन की जरूरत नहीं है. ही इज़ अ मल्टी डिसिप्लिनरी पर्सन. मीन्स वो आपको प्लेग्राउंड पे भी मिल जाएंगे. कुछ चीज़ें हो सकता है यहाँ ना लिखी हों, वो भी मैं अपने मन से बताना चाहता हूँ कि बैडमिंटन और क्रिकेट के जो खिलाड़ी हैं वो हमारे सभी लोग लाड़ साहब को एक मार्गदर्शक और एक खिलाड़ी के रूप में बहुत अच्छे से जानते हैं. Born in April 1965, of course 14th April, he is B from DAVV Indore, joined RRCAT in 1987 as scientific officer from the Bar Training School, 35th batch. 30th batch. Extensive involvement in the development of the RF systems for various accelerators at RRCAT and 31.6, 13, 325, 476, 505.8 and 650 megahertz RF systems. All these things have applications in Indus Synchrotron, IRFEL, and the proposed ISNS. He pioneered in the R&D of low-level RF, control and signal processing, high-power vacuum tubes-based power amplifiers, solid-state RF amplifiers. Currently, he is Director PAG at RRCAT, Technical Coordinator under IIFC, previously Sub-Project Coordinator for 650 MHz RF power amplifier developments, earlier Head of the RF System Division at RRCAT. He is driving the indigenous development of very high power solid state RF amplifiers, digitally low level RF systems, 505.8 megahertz normal conducting RF cavities, high power circulators. Approximately 240 papers and 15 journal papers. Steering technology development for high proton accelerator. He was Vice President and General Secretary of ISPA, member of several DAE committees and international collaborations with Hiletra, contributing to the design of 505.8 megahertz RF systems. He was the guest scientist, Karlsruhe, Germany, involved in commissioning of ENCA SRS RF systems. One more thing which I wanted to just give about highlighting characteristic. We all are electronics engineers and have a very good idea about the systems. And when it comes to a stabilized system, there comes a feedback. So, and that particular feedback, also the negative feedback. The negative feedback which stabilizes the system. So in RRCAT, I find him the only person who gives the negative feedback and stabilize the RRCAT systems at the management level also. Of course, negative feedback is a थोड़ा बुरा भी लगता है कभी कभी किसी को एकदम सामने से बोलने से, पर वो बोल देते हैं और वो सिस्टम के लिए बहुत अच्छा होता है. फाइनली सिस्टम comes to a stabilized state because of that. I admire his characteristic. Thanks, sir.
Now I request former Vice President and General Secretary Sri Mahen Ladji, General Secretary SPA, Sri Mahen Ladji, to the stage. I request Tushar Puntambekar sir to honor him with sapling. I request Gurnam Singh sir to offer him Sol and Srifal. Now I request President ISPA to honor him with certificate. Now I request Lard sir to say a few words for this gathering.
सबसे पहले तो मैं इस्पा को धन्यवाद देता हूँ to honor me for such a delightful function and in front of august gathering of my all the colleagues from the different fields, and especially we have guests from BRC and all other institutes. So thank you ISPA and all the authorities, and I'm honored to have been facilitated by Gurnam Singh ji sir. ऐसे मौके में बोलना थोड़ा सा, गोपाल जोशी जी ने बोला कि वे भावुक हो जाते हैं, पर सभी लोगों ने जो बोला है वो मेरे लिए भी ट्रू है कि बी तक तो मेरा ही सफ़र था, खुद का काम की मेहनत थी, पर उसके बाद जो भी यहाँ दिखाया गया है वो मेरे सभी साथियों के मेहनत और कंट्रीब्यूशन और मेरे टीम वर्क के कारण हुआ है। तो मैं आप सभी को धन्यवाद देता हूँ और भगवान की कृपा रही है और आप सब लोगों का सहयोग रहा है कि मैं आज इस मुकाम पे पहुंचा हूँ। सो बहुत बहुत धन्यवाद एंड धन्यवाद।
Thank you, Lard sir. So on that note, now we start our ISPA proceedings. I request. ओके सो अवार्ड वालों को थोड़ा वेट करना पड़ेगा क्योंकि हमारा सीक्वेंस ये है कि इसके बाद हम सर आप बैठिए नहीं अभी ISPA की प्रोसीडिंग्स चालू करेंगे। उसके लिए पहले मैं प्रेसिडेंट ISPA से रिक्वेस्ट करूंगा कि सैपलिंग से अभी हम मतलब फॉर्मल चालू कर रहे हैं ना सर, इसीलिए तो गुरनाम सिंह सर को सैपलिंग भेंट करें। I request President ISPA to honor Umtambekar sir with another sapling. Now I request President ISPA to start the GBM function, and I request him to start the presidential address.
Good afternoon.
श्री पुंतांबेकर जी, श्री गुरनाम सिंह जी, हमारे सीनियर श्री विकास, डॉक्टर विकास जैन, श्री अनिल कोहली कट्टी जी, dignitaries in the audience, Madam Archana, श्री लाट जी, कहाँ पर, अच्छा लाट जी, परचानी जी, पुराने लोगों में मुंद्रा जी, सनेचा जी, और सभी जोशी जी, and colleagues and friends. So on behalf of Indian Society for Particle Accelerator, ISPA, as a president, I welcome you all to this ISPA GBM. Indian Society for Particle Accelerator has been playing a pivotal role in promoting the advancement of accelerator science technology and its application in the country, which is one of its important aims and objectives. Particle accelerators are one of the highly versatile instruments made by the physicist, and it means designed by physicists, and then it's a given shape by engineers. Because these particle accelerators can be used in every field of the life, including agriculture, medicine, material research, defense, everywhere. So its versatility is very high. A particle accelerator, we think of any instrument or equipment which is having such a wide application, it's difficult to find except this particle accelerators. So looking at its importance, PSA, this Principal Scientific Advisor, and then in the Mega Science Vision 2035, this particle accelerator has been given an important, that's an identified area for the research in the country. So ISPA continues to nurture a thriving ecosystem for accelerator science technology and its application by organizing thematic meetings, conferences, and workshops. Over the past year, it has conducted several important events, including a 2-day meeting on science with free electron lasers and high-power IR terahertz sources, 1-day meeting on manufacturing of industrial Linux by Indian industry, and a workshop on electron beam welding for accelerator and associated technology. These gatherings have provided a valuable platform for knowledge sharing, collaboration, and exchange of innovative ideas. And then presently, this InPAC, it is also being organized under the aegis of ISPA, which is one of the biggest forum for the accelerator community in the country. So in India, particle accelerator technology is now well established with the constant enlightened efforts marked by our predecessors, the present generation, and professionals in our field have proved themselves as able scientists, engineers, researchers, nationally and internationally. We have successfully developed a lot of technologies, but we still need to develop many more. ISPA has been trying its best in bringing a common platform in terms of accelerator-related science, technology, and research work for the past several years. And we are definitely on a positive path. The present conference and InPAC organized under the aegis of ISPA with the support of BRNS is one step towards this. This conference comes presently at the time when we are thinking of industry, ADSS, which are having a lot of challenging technologies that what we have developed so far. So this type of forum organized by ISPA will surely be able to meet all those challenges. And then other thing is, in addition to these large mega science projects, still we need a lot of smaller accelerators for societal applications. That is again an area in which we have to expand our activities. Many of these projects present significant scientific and technological challenges requiring concerted efforts and multi-institutional collaborations. ISPA will actively collaborate among institutes and provide forum for discussion, fostering interaction among scientists and technologists to address these challenges effectively. To promote and encourage young researchers and also to recognize them, awards are also provided by the ISPA. During this InPAC, we will be providing best student poster presentation, best regular poster presentation, best thesis presentation awards. These awards aim to motivate participants to deliver high quality presentations, facilitate the effective
dissemination of research findings. In addition, the contribution of young researchers also recognized through ISPA Young Scientist and Young Engineers Award. In closing, I would like to congratulate all the winners who will be announced soon. And I also congratulate all the scientists, engineers, delegates who have enthusiastically participated in INPAC 2025. Thank you all.
Thank you, Vijayan sir. So as President ISPA told about many things, what I will do, I will just give a glimpse of all the activities which happened after we took over the ISPA activities. So this is our ISPA Executive Board, which consists of people from BARC, VCC, and IUSC. So as the President told that we have done so many things, and I am not counting this INPAC 2025 because it is still going on. So one-day theme meeting we have done in January 2025, which was supported by ISPA. Then 2 days workshop which was held in November 2024, that was on electron beam welding for particle accelerators and associated technologies. And then 40th DI safety meet, there also ISPA supported. Then there was a theme meeting on free electron laser and high power IR terahertz sources. So RRCAT, this happened in August. Then there was a meeting at BARC, which was supported by ISPA. And the radiation safety meet, which happened in May 2024. So this is some important glimpse of the INPAC 2025, which is recently happened. And you can see our former chairman, Vyas sir, inaugurating the industrial session, and then the abstract book. He has opened the abstract book, and now abstract book you can download from the website. It is available, and I'm happy to announce another thing, that we have received more than 310 manuscripts of INPAC 2025 manuscript, all full manuscript, which is going to get released soon. And this is a record in the sense that during the INPAC, in all INPAC, whatever happened so far, we have around 90% of the manuscript has been received. Even our INPAC is going on. So we hope to go close to 99% because 1% is already withdrawn. So at least 99%, if this comes, this book is going to be very technically rich, a lot of discussions. You could have seen that yesterday, 7:20 p.m., people were discussing the posters. So that is what the technical details people want to know, and they want to contribute. So a big applaud for all the participants. And then it is covered by media a lot. You can see the growing need for accelerator in industry and medical applications. And then medical क्षेत्र में accelerator की ज़रूरत फिर अमेरिका प्रयोगशाला के वैज्ञानिकों ने पार्टिकल एक्सेलेरेटर की बताई तकनीक. तो ये काफ़ी वाइडली कवर हुआ है. और इसके अलावा सोशल मीडिया पे भी काफ़ी अच्छे रिव्यूज़ आए हैं इसके बारे में. इसके अलावा जो राटिक हुआ था, एक्चुअली देयर वर many clippings. Unfortunately, I could not get those headlines, but it happened, and a lot of discussions held during this meeting also. After before that, this electron beam welding machine and electron beam welding particle accelerator and associated technology workshop. This was a grand success, and 153 delegates has attended that. And we could know first time that India has so many electron beam welding machines, because we were just thinking that we are having 4 or 5 only, but when we dig, we find that India has more than 50 electron beam welding machines. That is what we find, that ISRO and DRDO and then HAL and DI itself and some other private companies, they're already working. So this technology are already matured, and this time the demand has come from DRDL that they may host this workshop this year. So that is something good news for us. And then this was also covered widely in the our local newspapers. So I'll not go into detail, but this was a grand success. And then this is what happened in August. The Archana ma'am is here, and she basically hosted this electron beam technology and application, the SEPTA, and this was also a great success. And you can see the ISPA symbol somewhere here, yes. So this also, I think, supported by Power Beam Society of India. And so now you can see that we are also extending our support to the some symposium, conference, theme meetings or workshops. Then this happened in August, and this is the gathering, and we felicitated many of our seniors that time also. And it was also a grand success. I think Pantji has given this slide, and Pantji was very keen on giving this work because this was first time held in India. And congratulations, Pantji, for holding a great theme meeting on the laser. And this was also covered. This is basically CAT and IUSC's related work. So this also covered widely with our local newspaper. Then this safety meet. Safety meet, I think we can we support it, but we are not really directly partner to it, but we support it because it is like that we have to just support all those activities which are helping accelerator in one way or others. So that is the main motto for this. And awards were given during the safety meet, and it was also covered by various papers. Thank you for the, this is just, now I would like to ask some of the members if you have any suggestion for holding something, but I have already received one suggestion from BARC and SVLS Rao. Are you online, Rao?
Hello.
Okay.
Hello. Can you hear us?
So
Yeah.
if you are online. Yes. Yes. So he has given a proposal for InPAS. So this is InPAC, and he has given some proposal for InPAS, and he has already discussed with Malseji and other group directors at BARC. So Sunny Rao, over to you, if you can explain this.
So, first of all, thank you, sir, for giving me this thing to present. This is not the first Indian particle accelerator school, because previously most of the people know that there is a beam physics school used to happen, and there all the newcomers and institutes like IIT students from there. So we would like to give this type of basically start this type of Indian particle accelerator school. And also mainly objective of this is to equip the newly joined POs and SOs with essential skills for our accelerator program, because definitely when training school is always there, but during the training school, there is no hands-on experience, and also some things like what are the softwares, how to use the software, such other things are not there. So we are proposing first to mainly basic audience are the POs and SOs, and obviously the speakers are from well-known renowned BAE institutes, SEBI, and also IUSC speakers also will be there. And we are proposing the first one is the theme of this accelerator school is the linear accelerators, mainly ion and electrons, both science and technology, not only the physics only, science and technology. And main emphasis will be on the practical sessions and simulation tools, which we will do, and hands-on activities also. Like, I mean, I will not tell that we will make all the things like high power conditioning and other things, but it's basically whatever the low power activities generally we do before the cavity switch to the high powers and other things. And program details, frequencies like the BRC. Right, first thing we are planning to be in BRC, and duration will be 6 days, like right now. And most probably we are thinking that September to November, because most of the STEVOs and SOs will join in August. So immediately after 1 or 2 months, whenever they join, they will get the area where they were going to work, and that this will be useful for them. And we are proposing it to be every year based on different themes like synchrotrons, cyclotrons, and it will be in synchrotrons as a RRCAT, because RRCAT is the masters in synchrotrons, and cyclotrons as a VECC, as the name itself is suggests the VECC is the variable energy cyclotron. So those things I want to say. Can you just go to the other slide, sir? And definitely we need the support, financial as well as advisory support also we need. Definitely it's financial support. That's the reason why we want to go for the ISPA. And because it is a society for particle accelerators. So this type of thing, most probably it will be important for our future accelerator physicists as well as engineers. So we need the support from the financial support and also advisory things also. Once the financial is there, then there are so many people, experts, seniors sitting here as well as the in BCC and everywhere. And definitely the impact of this will be the strengthen the Indian accelerator program, definitely. And enhances also the collaboration between the different labs and institutions. Right now, we are targeting only to the newly joined POs and SOs, and we are asking support. So right now, I have not given the estimation of the budget and other things, but once the proposal is accepted, then we can go for the proposals and
okay. Thank you
very much, sir.
Yeah.
Thank you very much.
So now I request GBM, if you have any other queries related to this, or we raise your hand if you are seconding this. Then we can discuss and the modalities, different modalities in our committee, and then we'll. So, yeah, they are working on it. Yeah, Rajesh ji has some suggestion. Please come.
Yeah, I think that's a good suggestion. But we are making a mix of the interest between the two things. Number one, what we are assuming here is ISPA as a body will get support from all the technical institutes, RRCAT. We are assuming, we are assuming, and that should not be assumed, because the parent institutes, the RRCAT, BRC, VCC, IGCAR, we are expecting that the support from those institutes will be available for us, and the senior employees will be permitted to go for taking the lectures and everything. So this model has to be first discussed out, and then only this can be decided. I think but the suggestion is good.
Okay, thank you. So what we will do, as most of the people have raised the hand and seconded this proposal, we will discuss in executive committee in details. And then I also request SVLS Rao to discuss with seniors over there and make the final proposal and send to ISPA. And then we will, after finalizing, we can float this idea.
Okay,
Yes.
sir. Thank you. Thank you very much.
Joxeji has some idea.
Yeah.
So far, all the our accelerator related activities, it is all this thing in 4-5 institute only, since our either ISPA has form or accelerator. So we have not come. See, earlier also when the school was there, it was at CAT only. And at the time has come that accelerator should go to university and college. So at least school, this type of school should be at some university where, so that it will, universities and colleges should get a chance, so that accelerator should spread to, should have a wider spectrum. That is my suggestion. Because since 2003, except this 4-5 institute, in fact, INPAC also we have not taken to any university and college. It has focused to all 4-5 institute only. So at least the school level thing should go to some university. That is my suggestion.
Sir, thank you, sir. This is definitely very welcome suggestion. Since it is going to be annual event, we have to go, because it is we are going to conduct every year. We have to have it with university, IITs and some other institution where accelerator can be promoted, because what happens, this 5-6 institute, this is restricted right now, not restricted, but it is limited to these 4-5 institute only. And if we expand our reach to various universities, and if we can get the various PhDs or postdocs from the various institute, which will be very helpful. So this also we will keep in mind. So, but we can start with BARC and then we can go, because it is going to be every year. So we can have in any institute which are supporting this idea. So thank you, sir. So any other agenda, any other point if you have, not related to this, but some different point that also can be. Yes, Pritam, you have some. Yeah, please come here.
So already we have spoken about the school, but this will take like some effort. You'll have to have system in place. I had some idea, like we were talking of, Vijen Prasad ji said, ki you won't find any other field where you have almost every, like any other system where you will have every field working in, like in accelerator, we have magnet, we have vacuum, we have RF, we have feedback control, we have data acquisition, we have everything. And you go to the colleges and ask them whether they know, students ask them even in the MTech colleges, whether they know what the particle accelerator is. So I don't think many of them knows what the particle accelerator exactly is. So one way of educating them to have a school like what Raoji has proposed, another way could be probably we can, which is probably the easier way to do, identify one speaker, some senior speaker, which is good enough to go to some universities or on a common function and educate them only about the technologies and the areas on which we guys are working on. So that will not put a lot of efforts and the financial tax on the ISPA also. And it's a kind of easier model also. In that way, we reaches to the colleges and we can probably have a more number of ISPA membership. And once the students in their B are aware about this particle accelerator thing and the kind of activity we are into, then probably in MTech, they can also think of getting in connect with probably RRCAT, VCC, BRC, and find out some of, though we have a model, but still I think a model where we can probably just send 1 or 2 senior colleagues. Oftenly, maybe every
so
2-3
I think this is a very welcome idea. Maybe Pritam ji, if you can send this idea to ISPA Executive Committee, we will discuss in more detail. And then another point, which is Rajni, are you online?
I'm there.
Okay. So Rajni has proposed the idea of starting a newsletter. So she is also Vice President ISPA. So welcome Rajni. First of all, let us welcome her with a round of applause.
Thank you, sir.
Can you tell your idea of having this newsletter?
Yeah, sure. I have a slide. Is it okay to share,
You
or
can
otherwise
share.
I can speak?
No, you can share. Can you make the arrangement for?
Okay, you will have to give me the sharing
Yeah,
rights.
we are unsharing and.
ठीक है
ऑलरेडी कर दिए
लाइट बंद
Yeah, please go ahead, ma'am.
अभी आप शेयर कर लीजिए
Okay, I have shared my screen. Is it visible? Is my screen visible, sir?
Yeah. Wait for 20 seconds.
Oh.
It is visible.
Okay. Okay, so as already said by the President and the General Secretary, since being formed in 2003, ISPA, through its consistent efforts by funding various symposiums, workshops and conferences like INPAC, it has built a strong collaborative network of researchers and engineers. So events like INPAC, which is currently now going on in RRCAT, these show the immense value of bringing the community together. So these gatherings like INPAC, they spark new ideas, they highlight significant contributions, and they offer a platform for meaningful exchange of ideas. However, such interactions should not be limited to just once in 2 years. So, but we cannot increase the frequency of impact. So, to ensure ongoing engagement, so there is a need for more frequent touch points. And an ISPA newsletter would serve as a very good medium to do that. So, it will be a good medium to share insights, research updates, and community news on a regular basis, recognize the outstanding contributions by various individuals, institutions in the field, encourage interaction among similar interest groups, and foster collaboration both among academic research and also involve industry. So I propose that we start online newsletter. So to start with, we can have the frequency as once in 6 months, and then depending on the response, it can be taken forward, maybe even quarterly. And it could be hosted on the ISPA website, and it will be a very good step towards advancing accelerator science and technology across the country and building more connected accelerator community. So for this, we look forward for support and active involvement of all the members, all institutions, and also the emerging researchers from even universities to help shape this initiative. And I also welcome any insightful ideas, contributions, or any suggestions that can enrich this initiative.
Okay, thank you, Rajni. I think this idea is right. If it is okay, just clap, and so we say that this idea is really good. So we will. We have already discussed this in our executive committee meeting, and we will do some needful thing, maybe in couple of weeks, to start this newsletter. Bakshi ji, you have some point?
Yes, it was related to a school on
School, okay.
accelerators. So it's just that we should cautiously look forward to the frequency, because on the one hand, it is nice to spread the things, but it is my personal opinion that if they spread too fast and too frequently, then there is a chance of degradation.
then if it becomes a routine thing for everybody, then it loses importance.
Yeah. No, your point is well taken. However, this is for limited audience, like newer TSOs and newer entries to DAE.
Right.
So it won't be any this thing. It won't be any problem of degrading things. Only thing, this is not like INPAC. INPAC is happening every 2 years.
2 years.
So that is why you can see lot of people, lot of paper coming. People are waiting for INPAC to happen. So those kind of things happen. So yes, your concern was discussed earlier regarding this, and that will be taken care. Okay, thank you.
Thank you.
So after this, I request Anil Holigatti ji to present the status of the financial status from the last where we have took over. Now you present them.
Yeah. एक मिनट Excuse me. चेंज इसको लगाना है इसको लगा किसको मेरा पीपीटी प्लेस के चेक कर लो इसको लगाओ इसके बाद पीपीटी कौन सी देगा ठीक एक इसको इधर नीचे दबा दो फिर सही आ रही
Good afternoon, everybody. Today I am going to present the Hello. Yeah. Good afternoon, everybody. Today I am going to present the ISPA audit report for financial year 2022-2023. So here the status of financial year 2022-23. So as on 1st April 2022, the life number was 691. So during this year, from 31st March 23, it increased to 35 new members, life member added there. So that count was increased up to 726. Corporate membership registered 7, still 7 is there. So cash in hand as on 1st April 2020 was 3,425 rupees. So at year end, this cash was with us 17,197. So current account balance in ISPA 1st April 2022 was 21,15,994. So at year end, it reaches 20,57,100 rupees. So already there are 4 FDs are running. So this fixed FDs 15 lakh still it is continuing. So this is unaudited expenditure and income report for financial year 2022-23. First I will read expenditure part, this side, left side part. So May 22 expenditure incurred during the INPAC2025 includes catering charges, flex banners, webcast and award ceremony. So we have spent 57,220 rupees. 27 May 2022, web hosting charges and domain name renewal we have paid 840 rupees. 15 January 2022, winners of best posters, best thesis, young engineers and young scientist award for the INPAC 2022, which was held in Calcutta. We are given 66,000 rupees award. Then 20th June 2022, expenditure incurred in organizing the theme meeting, that is soil dynamics and foundation design held in RRCAT. So I spent 1,30,821 rupees. 1st of July 22, audit fee and income tax return filing CFE were paid 11,210. On 29 April 2023, expenditure for event organization for INPAC 2023 in VRC. So here we have spent 5,57,346 rupees. So for this event, we transfer money from ISPA account to INPAC. It's called seed money for organizing the INPAC 2023 at VRC. So seed money was transferred to INPAC account 6,70,000. So account keeping charges and other charges for this financial year was 1,178 rupees. So during this year, total expenditure was 14,95,352. Now income part we'll see. So during this year, 35 new members were added. So 1,000 rupees membership fee for life members. So deposited 35,000 rupees. Income tax refund were received last financial was, that is deposited in account 11,060 rupees. This theme meeting, that is TMS FD on 22, held at RRCAT on 24th and 25th. There is 2 days theme meeting.
DCC and RRCAT also.
Yeah. So this donation were received from participant vendors for scientific exhibition, 1,05,000 rupees. March 23, INPAC 2023 on March 13 to 16 held in DRC Mumbai. So I received donation from participating vendors and scientific exhibition, 13,99,170 rupees. So total income we received 15,50,230 rupees. So difference over the expenditure, it is profit 54,878 rupees during this year. So this is a final, that is audit income and expenditure report for financial year 2022-23. This was prepared by our CA. Whatever already I have discussed, that is, I have mentioned that. And this is a audit balance sheet reported on 31st/3/22. This is the income tax return acknowledgement for FY 2022-23. Finally, whatever was given, we are refunded again back. So it's 0. So for next financial year 2023-24, so audit reports here I'm presenting. So status of financial year 2023-24. As on 1st April 2023, member was 726. It increased up to financial year end is 13 members added. So this count was increased 739. Corporate life members 7. Cash in hand 17,197 starting of this year. At the year end, cash in hand was 5,088 rupees. So current account balance starting of this 21,57,100. So at year end, it reaches 23,52,911 rupees. So deposits are there, 4 deposits are there, 15 lakh rupees. This is a unaudited expenditure and income tax report, income report for 2023-24. I will read first expenditure. So on 5th of April, so we are refunded. We have given back to some suppliers, so that 50,000 rupees we are returned to that supplier. Then expenditure include for food and beverage arranged during the INPAC 2023, RRC 22,000. Domain registration charges, website hosting charges, Google Workspace charges, and Cisco Wex subscription charges were paid 34,970 rupees. We received again a refund of vendor contribution for scientific exhibition for the INPAC 2023, that is 65,000 rupees. Seed money paid to INPAC account 1,20,000. Okay, we'll first read income this year. Membership fee from 13 when we added, that is 13,000 rupees. Income tax refund for this assessment year 22-23, 13,130 rupees we have received. April 23, INPAC 2023 held at VRC Mumbai on March 13 to 16, 2023. Received donation from the participating vendors for scientific exhibition 1,56,215. So there is a theme meeting for control scientific and instrumentation for future accelerator held at RRCAT on 26 May 2023 at RRCAT Convention Center. So we have received donation from participating vendors for scientific exhibition 15,000 rupees. We are the INPAC account, we have returned back the seed money, that is 3,50,000. In our ISPA account, we received again back. We'll read first expenditure again and for continuation this. On 9th, time fast. So winners and poster best for thesis and engineer awards were given 80,000 rupees. Expenditure included in organizing theme meeting 61,695 rupees. Website hosting charges, domain charges, renewal 1,414 rupees. Refund TDS amount to vendor, that is 1,300 rupees. ISPA account income tax challenge payment 88,740 rupees. Audit fees and income tax challenge, audit fees and income tax returning 15,340 rupees. Account keeping charges 973 rupees. So total expenditure during this financial year was 5,62,297. So this seed money was again returned back to INPAC, that is 2 lakh. So total income was 7,47,347. So difference over expenditure, that is income over expenditure were received, that is profit this year was 1,85,116. This is audit report, a report prepared by our CA and deposited in income tax. So this is our acknowledgement for this year 2023-24. Thank you.
Okay, with this, we are at the end of the GBM discussions. And now I request Puntambekar sir to announce the awards for, we will start with the awards for the best scientist first and then best engineer. Sir, आप इधर आ जाइए, मैं बताऊंगा आप.
Yes, sir.
सर ये थोड़ा मैं जूम कर देता हूँ आपको.
पुलिस के कर देते हैं.
So, sir, please announce this Young Scientist Award.
ये
पूरा पढ़ना है?
हाँ, just पढ़ दीजिए.
Complete this.
Yes.
Okay. So the committee has looked into the contributions of candidates in the national projects and importance of their contribution to the programs. It was neck-to-neck competition between all the candidates, and committee has tough time to decide on. I think Mike is not. Committee had tough time to decide on one candidate. The winner of Young Scientist Award is Shri Ram Prakash. Shri Ram Prakash is associated with Accelerator B Physics section at RRCAT Indore. He has developed 2D Python code and benchmarked it for understanding trajectories diagrams. He has developed 3D PIC model to study multipacting with space charge effects. He used Pluka-based radiation transport code to estimate dark current energy distribution. He also analyzed heat load from HOM in SRF cavities. He also contributed to optimizing SRF cavity design. Apart from this, he has also contributed to the Fermilab project. Results of his work are published in reputed international journals. So many congratulations to Sri Ram Prakash for this achievement. Yeah.
So now,
Yeah.
Young Engineer Awards.
This is the announcement of Young Engineer Award. The technical documents along with 2 referees assessment for young engineers of 5 candidates were shared by ISPA executive. The committee members went through all the documents shared, and then the committee in online meetings reviewed all cases precisely. In addition to comments of referees, the weightages were given to contribution of the candidates in national international projects and their importance. All the candidates had very good quality technical contribution, and all the candidates deserve the award, and was close competition between all the candidates. It was difficult for the committee to decide on one candidate. As the committee decided winner of Young Engineer Award as 2 candidates in no order were Shri Ponagini Bhuvneshwar from BRC Mumbai and Miss Kirti Pathak from RRCAT Indore. Shri Ponagini Bhuvneshwar is working in IIDD BRC, and he has worked on deuterium compensation in SSR cavities for LFD and helium pressure variations. He has also worked on both software and SOC FPGA based hardware in RF power monitoring systems in LIPA Klystron system. He has also developed feed-forward system for regulating RF power of Klystron in LIPA. And Ms. Kriti Pathak at RRCAT Indore worked on solid-state RF power amplifier modules and high power systems and their testing. Also, she developed AT setup for testing all CIV boards and developed software in LabVIEW. She developed GUI for fault diagnosis of high power RF amplifiers, which helped in debugging of problems during commissioning of 650 MHz SSPA delivered to Fermilab, USA. Also, she worked on inclusion of TCP and Modbus TCP in RT control of 650 MHz SSPA for DAE and Fermilab deliverables. So, congratulations to both the winners.
Now I request President ISPA to announce the Best Poster Award. We will have Arup sir is there, or he has left. Okay, sir, आप ये वाला award announce कर दीजिए. If he has left, then next will be after this the Best Thesis Award, which I will request Binit Kumar ji to announce that. Yeah.
I didn't actually.
Poster
Well, so we are having a separate student poster session on 25th of the evening, in which around 18 students participated. Mostly of them were from outside institutes, not related to DAE or HBNI, and then few were, many of them were also from the HBNI. So we had to take a balance, because from the HBNI and other places they are getting much better guidance and then practical experience compared to the students who are working in the institutes. So based on that, we have tried to decide the best student poster award has been, and then committee has recommended a number of best poster student best award to promote them. So let me announce the first one is the poster ID number 928 by Ram Prakash. It's the RF loading effect of field emission current in SRF cavities. Right, okay. Second one is the poster ID 850 by Mustafa Saifi. His title was Development of State Space Compensator Auto-Tuning Framework using Neural Network and Model Reference Adaptive Control. The third one is the poster ID number 743 by Rimsa Arif, Beam Optics in Achromatic and Isochronous Transport System. Then there are 3 consolation prizes. Poster ID number 750 by Miss Niketan Jakar. It's a particle in cell simulation of laser weak field plasma acceleration. Other constellation is poster ID 751 by Adarsh Ramtel, magnetic field symmetry and its correlation to magnet center for magnetic field analysis in cyclotron. Then other constellation is poster ID number 898 by Shruti Verma Koikal, 2D and 3D simulation of a standalone swift heavy ion radio frequency quadrupole accelerator. So we have announced 3 this first, second, third, and 3 consolation prizes. So this is the detail, and we'll be providing certificate and award during the concluding session. Okay. Then क्या भी करेंगे? Okay. Then next वाला क्या है? ये complete हो गया students का.
अच्छा. अब poster.
Then poster का वो भी अभी अनाउंस कर दें.
पोस्टर का अनाउंस भी कर देते हैं.
ओके यार ये थोड़ा प्रॉब्लम है, इन्होंने प्रिंट नहीं दिया है. Well, so we could not get the enough time to make it poster and presentation here. So I'll read out the name of this who are the best poster award winners. So
read the name.
So name I'll read that, and there is we are not categorizing as best poster. We are giving the 10 awards. So out of these 300 posters, 10 best posters. All 10 are best poster awards. So then first is the poster ID number 997 by Janvin Itira. Its a topic is thermal analysis of cryo-cooled superconducting magnet for SSR2 cryo module. He's from BRC. Then other is poster ID number 909 by PK Sahni. Radiation damage in insulation of quadpoles bus bar at Indus 2 is from RRCAT. Then next poster ID is 652 by Rinki Upadhyay. AC power distribution of 40 kilowatt 650 megahertz solid state RF amplifier. This is from RRCAT. Then next is poster ID number 662 by Santanu Sahu. EPIC based control system for e-Linux in RIB facility at VCC. Then next is the poster ID number 1019, Akashdeep Garg, development of interferometer based electron beam size measurement system for Indus 2. He's from RRCAT. Then next one is the poster ID number 720 by Chiranjeev Das, design of beam line for neutron and gamma spectroscopy at K500 superconducting cyclotron. Is from VCC. Next one is the poster ID number 950, Ajay Kumar Soni, design and development of bellow integrated beam position monitors and compact BPM for infrared free electron laser setup in RRCAT. Next is the poster ID number 729 by Pallavi Priyadarshini, design, development and characterization of retarding field analyzers. Is from BRC. The next one is the poster ID number 887 by SV Kokil, development of second sound-based quench detection diagnostic system for SRF cavities being processed at RRCAT. Next one is the poster ID number 718 by Dr. Rajesh B. Hariwal, beam diagnostic in high current injector at IUC Delhi, present and future. Well, so it was a very difficult task for the committee to decide out of 300 the 10 best posters, but they found that lot of posters were equally good, and they have this all the researchers and scientists have contributed nicely. So it was a very difficult task, but they had to select 10 only. So we cannot give more than that, but it was a nice competition and it was a nice presentation by all the candidates. So it's congratulations to all who have participated in INPAC 2022. It's a big win for them also.
So the only award left is the Best Thesis Award, which I request Vineet Kumar ji to come over here and announce the Best Thesis Award. After that, we will have a 10 minutes break and then we come after tea and conclude the session. है ना?
इसको दो इस फोल्डर में
फोल्डर में अटेंड करो
ठीक है, ऐसे ही बता दो। मैंने मोबाइल में भी तो आपको मैं दिया था ना, वही पढ़ देता, वही दे देता, वही दे दे।
So we had three thesis presentations, and all of you must have attended, and it was really very good. I mean, they were all very good quality work, very useful work, and with good publications, etc. It was really very difficult to choose the best out of that. So after a lot of deliberations, I'm reading on behalf of the chairperson, Dr. Aru Bandyopadhyay. We ultimately decided that the best thesis award goes to Seri Rosalie from BRC. And the title of the thesis is Study and Analysis of Gas Jet Based Profile Monitoring for High Intensity Proton Accelerator. I must say that the other two were also very good, but since we had to give only one, the award is given to Seri, and congratulations to her. Thank you.
So with the permission of President, we are closing this session and we request you to assemble after 10 minutes for final concluding function. So high tea is there at the upstairs. All are requested to take ISPA high tea. We found one laptop. If somebody can come and किसका है वो अपनी पहचान बता के ले जाए.
सर पैसा निकाल दे रहा
आप पूछ के रखो ना।
ठीक
अरे सर आप थोड़े चले जाना ऊपर पहले। हाँ तो आप ऊपर चले जाओ जरा। क्यों? वो टीवी उतार रहे हैं जरा मैनेज करते हैं। मैं जा रहा हूँ, मैं आ ही रहा हूँ मैं। अरे ये हाँ बोलो। नहीं नहीं ये इनको बोलो टीवी बंद करें सब प्रोजेक्टर टीवी। ये प्रोजेक्टर और ये कंप्यूटर इसको इनको ये कंप्यूटर वाले हैं। आप जब होगा अच्छा
ये माइक ऑफ कर दिया कीजिए ना।
चल
दो है ना, एक स्टूडेंट वाला एक नॉर्मल।
All are requested to come. We are starting in 2 minutes. All are requested to come to Homi Bhabha Auditorium. Thank you.
अरे व्यूअर में खोलो, काय में खोला तुमने? पहले स्टूडेंट का खोलना है, उसको रोटेट करके ओपन व्यूअर खोल लो ना। क्या है ये? तो वो है ही नहीं, फाइल ही नहीं है वो तो। क्या डाउनलोड करा है?
ये है ना सर, यहाँ पे
ये रहा, यहाँ है इमेज।
Good evening, friends and participants of InPAC 2025. In the concluding session, you are all welcome here. Now, I request for the concluding ceremony to begin with the summary of InPAC 2025. The conference summary will be presented by Dr. Vineet Kumar. I request him to kindly come on the dais and present a summary of the conference proceedings till now.
डाउनलोड करा हुआ है
Rishi.
Thank you. It is a pleasure for me to present the InPAC 2025 scientific program summary. Actually, I am not sure whether in earlier InPACs we have done this kind of exercise, like discussing once again briefly what all we discussed, but I think it is a good idea. And we had not planned to have this kind of presentation earlier, just 2 days. I mean, yesterday this idea was given. So this is something which is present which has been prepared in hurry. But I feel that maybe next InPAC and onwards, we should plan for this kind of thing in advance so that we have a good summary. So this slide shows the general statistics about the presentations. So we had total 11 technical sessions, and 8 were plenary and 3 were parallel sessions. So that way we had 9 plus 8, 17 total number of sessions. And in addition, we had 3 poster sessions also. So if you look at the number of oral presentations, we had total 142 presentations. 26 were invited talk. We had 32 contributed oral, and we had a lot of contributed oral posters. This is something which we had started at when the InPAC 2018 was held at RRCAT. Some selected poster presentations, the presenters were allowed to spend 5 minutes, present their work in 5 minutes to all the community members. And the basic idea was to give the opportunity to younger colleagues to make a presentation in front of all experts. I mean, that helps them to sort of improve their presentation quality and gives them chance to sort of speak and get feedback from the audience. I also prepared a table. I mean, this exercise we had done before the InPAC. I mean, we had total 360 abstracts we had got. 3 were withdrawn. So 363 we had got, and so out of that, this was the distribution. Since this InPAC is held at RRCAT, we had more number of papers from RRCAT. So we had 53%, 192 abstracts from RRCAT, 53% BRC, and this I had just added. So we had 21% from VRC, from VCC 11%, IUC 6%, and others which included universities. We had, I mean, quite a good number of abstracts submitted from the IITs, universities, and other places. I mean, Samir is also included in this because the number was small. So this was the percentage of contribution. And when the abstracts were received, we got it reviewed by the SPC members, and also we took help from some people who were, other than SPC. And we had an idea about we have slots for these many oral presentations, these many oral posters, etc. So accordingly, they did the review. And finally, we also, checked that the representation of these centers, these units in the contributed oral presentation and even in the oral posters was roughly the same. I mean, if we had 53% contribution from RRCAT in the contributed oral also that was reflected. So that is something which naturally happened. We had to do a little bit of tweaking. I mean, that is something which normally one does during these conferences. And this table shows the category. I mean, in the abstract booklet, we thought that we will put all the contributions belonging to the same field together so that people will have it becomes easier for people to find the abstracts of their interest. And same thing we applied for the posters also. So you must have felt that all the posters related to the beam dynamics or RF structures, they were sort of together so that somebody who's interested in a particular field, he or she finds that they are just together. So this shows also the contribution from different fields. So beam dynamics at 13%, RF structure and components 10%, RF source 5.5%, and like that. So this gives an idea about, and actually it was very difficult to find sort of separate categories. So a lot of things we put in accelerator operations, installations, instrumentation, development, experimental studies, and utilization. So here you have a lot of contribution. And here also we found that the representation in the contributed oral and oral presentation, that was sort of proportional to their representation in terms of the abstracts submitted. So this gives you an idea about like in which field, how many papers were presented, etc. Okay, so this is the slide which I'm not happy about. So I just prepared what all did we discuss here, and this has been presented in hurry. I just tried to discuss with people and find out what all we have discussed. And I think this is very important. Next INPAC on inverts, we'll do it in a better way. So from the presentations from IUSC, I can say that there were presentation discussions on, this was there in the presentation by Director IUC, the application of swift heavy ion in biology. This was a new thing I found that this year, that has a lot of applications for the biology research that was discussed. The latest status of HCI injector, they have transported the beam up to DTL 5, 6, and they are ready to go for higher charge by Q ratios, etc. They have some issues with the RF power related things. They also discussed about the recent enhancement in their SCRF capabilities, which was discussed in today's contributed oral presentation, and also update on their FEL project. So these were discussed by IUSC. From RRCAT, since we had large number of presentations, so you can find that this list is larger. So a lot of updates about the INDUS upgrade and particularly progress on the superconducting wavelength shifter multipole wiggler, which was a new thing presented in this INPAC. And also the plans for the HPSRS, all the capacity building thing, and a lot of prototyping which has been done for the HPSRS related thing. Progress on the FEL project was discussed, and also on the proton accelerator activities, the progress on the RFQ, DTL, ion source, etc. were discussed. On the SCRF cavity front, I think in this INPAC, this was discussed for the first time, the RRR 300 niobium development, niobium 310 cavity work, plasma processing of niobium cavity. Also the SSR2 development carried out at RRCAT, progress on the HTS, and good progress on the industrial LINAC, materials for the accelerator, which was presented in Abhay's presentation today, and also accelerator related technologies, all the power supply related, power converter related technologies, alignment, etc. From BRC, the progress on the LEHIPA and the plans for the MEHIPA was presented. Since last INPAC, the progress which happened in LEHIPA in terms of going from to 20 MeV, that was discussed in this INPAC for the first time. And we had interesting talks on the role of accelerator in mutation breeding program. And by Dr. Raghavendra, there was this talk related to the material testing accelerator, ADS accelerator requirement. These were actually new dimensions this year. these things were not discussed in the earlier impacts, and it is good that the community is now sort of, especially the younger people, are more aware about these things also, which are very important. From BECC, the progress on the medical cyclotron, a lot of progress has taken place in terms of producing the medical isotopes, which is done sort of almost on the daily basis, except I think 1 day in a week. Progress on the RIB accelerator, and the progress on the superconducting electron linac for the RIB. These were nicely discussed in the talks by Director VCC and also by Dr. Arup Bandyopadhyay's talk, and the other talks during different sessions also. From Samir, we had talk on the progress on medical linacs and the future plans. But most important, I will say that there were a lot of interesting presentations by younger colleagues. The contributed oral presentations which we had from all the centers, many of them were quite interesting, quite educating, and many new things they have started working on. I forgot in the earlier slide, I had not mentioned here the thesis presentation, and also the details about the other poster presentations which took place. And about the poster presentations, actually the timing was 4 to 6. But I do not remember, know when it ended, because up to 6:45, 6:45, I used to be there. And there were at least 20 posters, and it was filled with at least 20 people. People were discussing, even very senior people were there discussing all those things. So that was very nice thing. I was overwhelmed by noticing that. Only Vikas mentioned that one day he said that it was up to 7:20. I don't know other days when the poster session actually ended. So it means it was really very successful. And a lot of interesting presentation by the younger colleagues. And that is something which we should be happy about and should encourage the younger colleagues on that direction. So that is all I have to say. But I must say that I must have left many of the things here. It was just an attempt to just show that these are the things which got registered in my mind. Next time we should do it better, and it will be good to summarize this in a better way. So I would like to thank all the SPC members who worked for this, and also the auditorium committee. We had these sessions ongoing by our joint effort. Yeah. Thank you. Thank you.
Thank you, Vinit Kumar sir, for nicely compiling in a very short time the summary report. Now, may I request National Organizing Committee Chairman Shri Tushar Prantampekar sir, Convener for the National Organizing Committee Shri Lad sir, Chair of Local Organizing Committee Shri Chokse, Convener Shri Vijendra Prasad ji, and Secretary Shri Vikas Jain to please come on the dais for the plenary session and feedback session on this. And for the student award function, for the poster award and the best poster award functions. Now, I request to start giving some feedback from the National Organizing Committee Chair and Secretary.
So again, all the delegates present here. Dr. Vinit Kumar ji has already presented the summary of the INPAC 2025. So we see that all the important topics related to our accelerator program were in various across various institutes in India have been covered. And as far as the feedback is concerned, what I suggest that one thing this time particularly I saw there is a good some presentation was there on good serious efforts on indigenization of the imported components, which is a very important step towards our Atmanirbhar Bharat that we are targeting. And what I suggest that in future, in next INPAC, if there is a session, technical session, particularly dedicated to this aspect of the import substitutes, so that it will present, it will also foster, I think, collaborations also. If I know that what other institute is doing. Here also it was covered in some, but it was part of that talk. So rather if we focus, that is just my suggestion, we can think about it. And as we see that our accelerator community in India is now very quite vibrant. Activities are going on in various institutes. And now we are now embarking on very ambitious projects which were also presented in INPAC, like our HBSRS industry, then MEHIPA, then ANURIB, and medical cyclotron facility, indigenous medical cyclotron at VECC. So for this ambitious projects which we are going to take up, naturally this forum of ISPA will be very useful, particularly in I think bringing together our development R&D community who is developing and industries, because such big projects, the role of industries will also be very important in multiplying the technologies that we develop in our institutes. So maybe ISPA can also think of some how we can increase this interaction among industry and R&D institutes where we can take up such big projects in future. So with this, I compliment all the team members who had worked really very, very hard, tirelessly last few weeks to make this a grand success. And the participants who have come from outside, whenever I interacted personally, everybody has said words of praise for this INPAC. I hope we'll also listen to the feedback also, of course. But from my side, I compliment all the complete organizing team and all the volunteers also who have really worked hard to make this event a grand success. Thank you.
Thank you, sir.
Yeah, I was telling Rajesh that since we are already late, we need not to each one of us speak on the same thing, which Tushar has very explicitly mentioned. So anyway, he said one line. So I will say one line. Thanks to all the, especially National Organizing Committee and Local Organizing Committee members, volunteers who have worked hard for the last even months, not these 4 days to have accomplished this INPAC. People have worked, and kudos to all the convener and the members. And I request all the award winning and all the younger colleagues to work and with the full enthusiasm and zeal for our future mega science projects, whatever DE has been embarking on. And award winning also, congratulations to them. Thank you.
So this is 12th conference, and I have attended all 12 conferences actually. I have not missed any INPAC, but I can say that this is one of the best. This thing. It's not that we are part of that, but it was nicely organized, and one change right from beginning. Earlier, now we were more offline, but this time Vijen Prasad ji has from day one has taken the responsibility of designing the website, so that even our PPT and all everything, everybody was database management, everything on background was very good, which was my observation. And with ISPA, since we have all involved from since long, I can say one thing actually, because of this award thing, na, that from accelerator PhD where actually fees is very less actually, with a lot of attempts, multiple time, whenever I go home, I used to again flash, because when we see that nominations are coming very less, तो मैं विकास को बोलता था एक बार और डाल देता हूँ मैं घर जा करके, तो फिर बार बार लोगों को कि भाई आप लोग नॉमिनेशन चाहे थीसिस के लिए हो चाहे कुछ हो डालिए, बिकॉज बट आई कैन से दैट वी शुड हैव मोर PhD थीसिस इन दिस फील्ड एक्सीलेटर, जो 2 साल में आए थे वो थोड़ा सा और बढ़ाना चाहिए एक्चुअली. And membership, we should target for at least 1,000 by this, after this impact, means जो लोग कुछ बने हैं अभी और कुछ बनना जरूरी है, क्योंकि अभी भी थोड़ा सा एक्सीलेटर कम्युनिटी को should have more membership actually. Thank you.
Okay. So, well, anyway, we could not get enough time. Just only one thing as a convener, I can say that we need to have a calendar of the INPAC. Calendar of the INPAC means actually we decide that okay, the next one will be held at this institute, but we do not prepare the calendar. As a president ISPA, and even in coming days also, if the new executive committee will be formed, I will instruct at least to prepare the calendar in advance, because normally it is declared in very short time, like 2 months, 3 months in advance. And even if we declare in advance like 6 months, then participant can get enough time to prepare their abstract, manuscript, quality will improve, participation will improve, and then everything will be much more smoother. So like IPAC or IPAC or other IPAC, they declare at least 1 year in advance, even before that, this. So in our case, actually what I found as a convener, that the time, like normally this 3 months, even 2.5 months is a very short time. So that was the one problem for us. Anyway, we could manage. That is one thing. Second thing, in the coming days, like NLS and other conferences are hosted only one website. So next time I'll try that this website is always hosted only on ISPA. That's the impact. Last year, the INPAC 2023 website was hosted on ISPA, and we did this hosted on the same. So the number of users, the registration and everything remains same. So they have to just log in and then upload their presentation. They can get all those mail from the same account, same thing. So then it becomes easy for them to identify the mails and other things. So that is one of my major suggestion for the coming INPAC, and we'll try to declare the schedule in advance. That's another. So that is bit feedback from my side as a convener. Rest is participation and everything has been fantastic. The works done by all the committee has been fantastic. They worked very enthusiastically whole day and night and made this successful. So I'm thankful to all.
Yeah, Dr. Vikas, kindly give your comments, brief comments, please.
Yes, thank you. मैं सिर्फ एक बात बोलना चाहता हूं कि हम लोगों ने कोशिश की कि बहुत अच्छा हो जाए, लेकिन फिर भी कुछ त्रुटियां अगर हो गई हों तो हमें आप छोटा समझ के या अपना भाई समझ के माफ़ कीजिए. तो ये मेरा मेन था. लेकिन सबसे अच्छी चीज़ है जिसके लिए मैं लाड जी को बहुत धन्यवाद देना चाहता हूं कि जो 385 पे एब्स्ट्रैक्ट आए वो एक रिकॉर्ड है, और मैं चाहता हूं उसके लिए लाड जी और पूरी टीम के लिए बहुत बहुत तालियां डिजर्व करते हैं. बिकॉज ये पॉसिबल नहीं था जिस हिसाब से उन्होंने बोला था कि यार टाइम कम बचा है, कैसे लोग आएंगे, लेकिन लोग अपना काम दिखाना चाहते हैं. ये दिखता है कि एक्सेलरेटर में लोग अपना काम दिखा के करना चाहते हैं. सिर्फ एक कमेंट ये था कि क्या उसमें क्वालिटी है कि नहीं है. तो वो चीज़ जो है हम जैसे जैसे ये करेंगे कि जब थोड़ा सा उसका रिफाइनमेंट करेंगे, मैन्युस्क्रिप्ट का भी रिव्यू होगा, तो उसमें क्वालिटी भी इम्प्रूव होगी. और एट सम डे, आई एम नॉट श्योर, एट सम डे वी शुड बी एबल टू कॉल institution like IEEE or
some other NIM or to host this conference in their journals. So that is what is my wish list. So thank you very much.
Now, I request from the audience, if any feedback from the audience, please. Ma'am, yeah, Mr. Dr. Vishwas.
Rajini gave a proposal to start the newsletter. So what I am saying is that if you link it on your website, anybody can post in the newsletter, has to become a member of ISPA. So it will automatically link membership of ISPA to reading those newsletters and expand the user base to all the universities.
Secretary may please note this. And I again request, now that we are for the feedback session on INPAC 2025, kindly give the feedback. Anybody who is interested to give, yeah, you can come forward, please. In the meantime, Dr. Archana Sharma, may I request to have one-liner feedback? Please.
Sir, when I have seen earlier impact proceedings, so in that only the page number are given. So if you give the in the bottom of the every page that it is impact 2003 proceedings like another proceedings do, so that will be helpful for a student to individual their paper they can upload so somewhere for referencing, because currently what happened, the first page is mentioned detail and the all other page have only the page number. They have not, there is no any mention about what is, where it is presented, and so.
Yeah, that's a good suggestion and we will take care for it. Yeah, please, Dr. Archana Sharma.
Thank you for giving the opportunity. अभी मैं मतलब ट्रिपल आईटी की तरफ से ऐसे बोल रही हूँ, वहाँ पे एक्सीलेटर मतलब सिर्फ उन लोग को गाड़ी का एक्सीलेटर पता है ना, तो मैं रियली मैं चाहती हूँ कि आप एक्सीलेटर को थोड़ा आउटरीच प्रोग्राम से ऐड करके लोगों को बताएं और आईएनएस के साथ जोड़ें. इवन आईएनएस वालों को पता नहीं था क्योंकि इट इज़ ए न्यूक्लियर सोसाइटी और रिएक्टर के पैरेलल एक्सीलेटर आ चुका है और रिएक्टर को तो बहुत सारे मतलब अप्रूवल चाहिए, सैंक्शन वो चाहिए, ईआरबी का. एक्सीलेटर इज सच अ सिंपल सिस्टम कंपेयर टू रिएक्टर और सिटी में इसकी ज़रूरत है. आपने जैसे जिष्णु जी का सुना या मेडिकल का सुना या हमने वेस्ट मैनेजमेंट का, कार्गो स्कैनर का, इतने सारे यूसेज आ चुके हैं. तो इसको अभी स्कूल के बहाने या किसी के बहाने आप आईएनएस के साथ जोड़ के भी इस प्रोग्राम को, आईएनएस का एक मुंबई इंदौर में चैप्टर खोल लीजिए और एक्सीलेटर रिएक्टर को एक साथ बढ़ाइए. तो वो मेरी आपसे जस्ट एक फीडबैक है. और मैं कॉलेज में होस्ट करने के लिए छत्तीसगढ़ में आई विल वेलकम एनी टाइम. यू कैन कम एंड गिव वन डे प्रोग्राम, थीम मीटिंग, है ना. थैंक यू सो मच फॉर गिविंग द अपॉर्चुनिटी.
Thank you. Any suggestion? Yeah, Dr. Deshpande.
Thank you so much. I'm very thankful to all of you, especially organizers, to having such a beautiful, wonderful conference. We really enjoyed all the 4 days. Vijendra ji ने बताया था कि we should have a calendar, and we would also to request that we should be given an opportunity to host the next impact when it comes at Samir Mumbai. We are a small group, but Samir is there, BRC is there, TIFR is there, IIT Bombay is there, and we're doing a lot many accelerator activities. So from our side, I would like to, eventually I'll put a formal proposal to the committee. So we'll be very delighted if we are given an opportunity to impact in Mumbai, where we'll be able to welcome you all. IIT campus has got a huge auditorium. We can have a 700 hall and 6 meeting rooms simultaneously, and a huge setup is around. We are doing astronomy conferences. I host astronomy conferences for 300 to 400 people. It is a good facility. So that will be a formal request I'll submit, but I thought because we are having a feedback session, request this to the committee. Thank you so much.
Yeah, Dr. Gurnam Singh, please. Hey.
Yeah. Yeah. See, for me, coming to RRCAT is like visiting Makkah. So this is the place where actually I get rejuvenated and energized. I first of all thank ISPA and the organizers for inviting me. And I have gone through many presentations, especially on Indus, free electron laser, and of course proton accelerator also. So the impression I got is that the way the progress has been made is really unprecedented and unparalleled progress. And for that, I think I would like to congratulate the entire team which has been working and seeing the way they have worked and the way they have operated the performance. I am sure actually the next source which we are going to make, in fact, the papers which have been presented, they are highly involved. They have done very detailed calculations, they have detailed studies. I'm sure actually this team is competent to take up this project to a successful end. So this is what, and regarding the conference that I can say that almost all aspects of the accelerators were concerned. The quality of papers was very good because I happened to be the convener of the first conference 2003, and that was the first attempt on our side. But this has been a sort of eye opener for me, the way things are being developed in India, the way the accelerator technology and science has progressed. It is really, I can see that the people who are leading it, they are much more competent than what we have been. So it is a very inspiring experience for me. Yeah, thank you.
Thank you, sir, for your kind words. Now, Dr. Akhilesh Jain, please.
अभी जैसे हमारे पुंतांबिकर सर ने, जो माननीय अतिरिक्त निदेशक भी हैं, उन्होंने जो सुझाव दिया है कि इसमें इंडिजिनस डेवलपमेंट को महत्व देना चाहिए आत्मनिर्भर के भारत के तहत, तो इसी के तहत एक अनुरोध है इस्पा से कि अगर हम इंडिजिनियस डेवलपमेंट के लिए कुछ अवार्ड जैसा कुछ घोषित करें तो डेफिनेटली अच्छे टोन में ऊपर हमारा ये जो रिस्पांस जाएगा, ऊपर प्रेषित होगा ये, तो हमें अच्छा इसका एक प्रतिसाद या एक रिस्पांस फ्यूचर में मिलेगा। थैंक यू।
Thank you, sir. I think is there any more?
सिर्फ
Yeah,
एक
please.
लाइन का हमारी जो RRCAT और ISPA की टीम है, उन्होंने किस तरह से पूरा मैनेजमेंट किया और जो भी है उसके अच्छे और कुछ ब्रेनस्टॉर्मिंग रिलेटेड जो भी होगा वो हम इंटरनल करेंगे। पर मेरा ये इम्प्रेशन है कि बाहर सभी लोगों को ISPA का पूरा सारा कार्यक्रम बहुत पसंद आया है और इसमें शायद हमारे इंदौर की संस्कृति का भी हाथ है।
धन्यवाद बख्शी जी। Yeah, can you just introduce yourself, please?
This is Kumud from BIRC. So I would just like to congratulate the organizing committee of InPAC 2025 because the technical content of all the invited talks, as we were discussing, all the accelerator aspects were covered, starting from the even survey and alignment and the advanced technology, plasma processing technologies, the reactors part, the material testing, accelerators. So those all aspects were covered properly, and it was all 4 days, all the invited talks and the oral contributory oral presentations were extremely good. So it was a very high technical content, and it was new also. It's not because considering after 2 years the technology is progressing so fast that we are able to have these many presentations. And additionally, I would also like to congratulate for a good hospitality for RRCAT for hosting InPAC 2025. And as database management was being considered, there was hassle, there was no pen drive moments. It was hassle-free presentation upload whenever manuscript, abstract, whatever we were submitting. At the same time, the mail, we were receiving the mail that manuscripts has been uploaded, presentations had been uploaded. So those are actually, from the organization point of view, for a large conference, it is very extremely helpful. So to have these all aspects in the presentations.
Thank you. Now, without any delay, further delay and any formality, I would just start the presentation ceremony, and we will give the best student poster award. The award first name is Rimsha Arif. May I request her to please take her best poster award? Rimsha Arif, if she is here. No. The next next best poster award is to Mr. Mustafa Safi. May I request him to please come on the dais to receive the award? As we are running out of time, will just request the next best student poster award is Mr. Ram Prakash. Please be. The next best poster award is to Mr. Shri Ram Prakash. He is from RRCAT, but he is a HBNI student. Now I request Sherry Rosalie for the Best Thesis Award. Please come onto the dais if she is here. So. Yeah, you can come on the dais to receive that award. Anyway. On behalf of Sherry, she's going to receive the award. And now, after this, I will be starting the Best Poster Awards. Committee has already decided 10 numbers of Best Poster Awards. The first name I would request Shri P.K. Sahani to come forward and receive the Best Poster Award. Next name is Mr. Kokil. Please, because we are running short of time, I'm just making it very fast. Kokil. Next is Mr. Kokil. Yeah, Mr. Kokil, please. Next award is to Mr. Shantanu Sahu. Please come forward, please. Yeah, please give a big round of applause for Mr. Kokil. The next award is Mr. Shantanu Sahu. If he is here, please receive. Next is Chirangan Das. Sorry. Chiranjeev Das. No. Sorry, because we are already late and most of the participants have left. So next is Akash Deep Garg. If Akash Deep is not here, I would request Anil to receive on his behalf, or anybody from BDS, Beam Diagnostics Division. Yeah. Next is Srimati Rinki Upadhyay. Next is Ajay Kumar Soni. Next is Rajesh V. Hariwal. Please come forward and Mr. Rajesh. या यशपाल जी ने एक कमेटी में भी बोला था उस कॉन्फ्रेंस में, ही वाज शेयरिंग कि टालियों में कोई कंजूसी नहीं रखें कृपया, क्योंकि बेस्ट पोस्टर बनाने में बहुत टाइम लगता है। पल्लवी प्रियदर्शिनी, if she is here, and Janvin Jitira. So with this, we are on the closing remarks. May I now request the President, may I now request Chair NOC, National Organizing Committee. Yeah. ISPA Organizing Committee has asked that the Young Engineer Awards and Scientist Awards will be given in a different ceremony. And with that, we are now to the closing ceremony, the concluding remarks. May I ask for the concluding remarks, if any, from Chair NOC, National Organizing Committee? Any concluding remark? You have already completed. So with this, I think it's over. So with this, I would just take this opportunity.
I would request Agrawal ji to give vote of thanks.
Yeah. देखिए, समय की महत्ता इतनी बड़ी होती है कि सभी को भागना है, तो समय बहुत महत्वपूर्ण है और विकास जी ने मुझे जिम्मेदारी सौंप दी है, तो मैं उसका लेते हुए बहुत शॉर्ट में कंक्लूड करूंगा कि इस पूरे कार्यक्रम को, 4 दिनी महोत्सव को संपन्न करने में आगे और पीछे, स्टेज के आगे और स्टेज के पीछे, कार्यक्रम के दौरान और कार्यक्रम के पहले और शायद कार्यक्रम के बाद भी अनेक लोगों ने अपना अमूल्य समय योगदान दिया है। मैं उन सब के लिए अलग अलग नाम न लेते हुए सबका आभारी हूं। सभी के प्रति तहे दिल से इनपैक्ट ऑर्गेनाइजिंग कमेटी की ओर से और इस्पा की तरफ से अपना और कमेटी का शुक्रिया अदा करता हूं। ये कार्यक्रम उन सभी के सहयोग के बगैर संपन्न नहीं हो सकता था। और जैसा कि अभी बख्शी जी ने भी बोला, ये इंदौर की संस्कृति है। यहाँ इस मानव धरती पर पग पग नीर और एक अमूल्य प्यार बरसता रहता है। लोगों के दिल में एक दूसरे के प्रति बड़ा सम्मान है और यही कारण है कि हम लोग एक मिलजुल कर कोऑपरेटिव वे में इस कार्यक्रम को सक्सेसफुल कर पाए हैं। तो सभी का बहुत बहुत धन्यवाद। मैं किसी भी कमेटी का नाम नहीं ले रहा हूं, किसी भी व्यक्ति का नाम नहीं ले रहा हूं, उसके लिए क्षमा चाहता हूं। सभी का धन्यवाद। Now may I request all to please stand for